Is that working? Okay, you want to look at it for a couple of minutes here, and then we'll start talking about it. There's a number of unnecessary parts there that were actually put in there because people expect to see them. Actually, on this, you can take everything back this way and take it off of there, and it will work just fine. You can also take the spark gap off of it, and it will still work just fine. And the reason for that is that in the coils, they have their own specific resonance due to the fact that they have both capacitance and inductance. And when you cross that on a chart, you find that that particular length of wire will have a specific frequency, and it will load and unload by itself, and you don't need spark gaps or you don't need anything else. Your Tesla coils can be built the very same way. This is a Tesla coil device. The Tesla coil in this case is in number 7. It's potted inside that laser module. And that laser module is about 3 inches long and about 1.5 inches wide there and about 1 inch deep. So that'll give you some idea of the size of them. I'm going to show you after a while, when we get into the actual core part of this thing, some little modules that are about the size of a calling card, and they put out 1,000 volts. And they don't look at all like what you think a Tesla coil might look like, but they're still, that's exactly what they are. Okay? Anyone is okay to go ahead and move it? Okay, the one you're looking at there can have a very wide range of voltage. It can be up to 5 million depending on the parameters that you build into it. The one that you're actually seeing there is the one that was on the board this afternoon, which I showed you, the larger one. That's the device right there. Except that it's got fewer windings on this L2 thing, and it's also wound in a spiral way. Okay, we'll just sort of take this as it comes here and see what happens. We were talking about in resonant circuits that your impedance or your resistivity or whatever you want to call it, which takes the place of ohms, becomes 0, and therefore you're at superconductor conditions at that point. The little statement over on this end where it says resonant energy explains it all, and we'll go into it in some detail in a little bit. Okay, basically what happens when the volts and amperes become equal, you're into what's called a volt VAR system, volts amperes reactive. And you can look in as many radio books as you want to, and you're not going to find hardly any of them that will give you an explanation of that. And if they do, it's misleading in almost all cases. But basically what it means is that your system resistivity becomes 0 at resonance, which means that you're at superconductor conditions at that point, at room temperature. Excuse me. Okay, shall we do something else? Okay, in over unity devices, the statement at the top of this particular slide. Ma'am, push it farther up. Okay, I'm sorry. Is that better? Okay. A real fine example of over unity would be the fact that in induction, the rate of induction is directly related to the cycles per second. So if you want to establish a reference point there, at 60 cycles a second, square that, and then if you want to see the relative position of, say, 220 megacycles, square 220 megacycles, and compare the ratio between the two squares, and you've got the ratio of improvement with the higher frequency. So if you look at that from a standpoint of over unity production, you'll see that on this curve here that you've gone from a certain level of under unity type situation down here, which is what is normal to most things, and then all of a sudden whenever you get into the above 20,000 cycles per second and start climbing up between that and 200,000 cycles per second, the curve does this, just above 200,000 cycles per second, and it stays that way all the rest of the way. Okay? Well, we're talking about if you, like you made a chart and you showed the efficiency of the device, and the efficiency of the device as far as induction is concerned at 60 cycles per second is here, and the efficiency at 200 million cycles per second is up there somewhere. The ratio between those two is telling you your efficiency. Okay? And that's one of the reasons why I built this device, to get out away from the ranges which the Tesla coils normally operate in, which is down below 200,000 cycles per second. And their Tesla coils are disruptive, and they have other habits which are not enduring. And if you get up into the radio frequency, you've got a device which is not harmful to humans, and you can handle it with millions of volts going through it, and you won't have anything happen except maybe the hair on your hand stand up a little bit. And you can also hold light bulbs and light them and that sort of thing. And the reason is that radio frequency, the electrons are running around on the outside, and they do not penetrate to any depth. And that's one of the reasons for the high efficiency rating. In the lower frequencies, the electrons are running through the wire, and they're bumping into things as they go, and they're not functioning very well. They're under unity. Once they get spinning outside the wire, then they're kind of free to do their own thing, and they don't have anything diminishing their effectiveness. Okay? Okay, did we talk about dominoes this afternoon? Yeah. We did, okay. Okay. And we talked about Ohm's law, and we also talked about how to recognize over unity. I'll put this back on and let you look at it a little bit more if you want. Let me step out of the way here. You can see where the envelope is set up and where the thing has passed outside the envelope there, and it continues even greater distance outside the envelope as it goes along, and it gets out to a certain point here, and it collapses, and then it comes back and starts the whole thing over again. That's radio? This is a particular resonant circuit that you find depending on how you work your shunt on the resonant circuit. If the first one, there were three of them, if you remember. The one at the top is the one which you normally expect to see. That's where your dampening effect happens when you're seeing these things on the oscilloscope screen, and it's showing the analog, or whatever you want to call it, showing the cycling. And it starts out with a certain amount of energy, and that gradually diminishes. Okay, the second one there is another setting on that same resonant circuit, and with a slightly different adjustment, and it shows an envelope of energy very similar to FM carrier. And And FM, you have a compression of these cycles, which takes the place of in the analog system, where you have various modulations on it. But and the third one is a particular arrangement of the grounding shunt, which means that its ability to communicate with the electron source, which would be your grounding, and the resistance there is like a dam on a large body of water, and it lets the electrons through, and they get caught behind this dam. This whole device is like a pump. All it's doing is, like the dominoes we were talking about, is tripping the electrons here, and that electron's tripping the next one, and this whole bunch of electrons in all directions are being tripped, and each time one of those would be tripped, it gives off a magnetic impulse first, and then when it comes back on that infinity loop, it gives off an electrical impulse. And this just goes on perpetually. The electron is never diminished in any way. It's giving you light and a lot of other things, and that is also an over-unity device if there ever was one. So if the physics books have a problem with that, so be it. Okay?
Mr. Smith, did you say you had a book that had, have you written a book that incorporates that information?
Yes.
You have written a book?
Yes.
It's in the bookstore?
Well, I'll show you what it looks like. I've got one right here.
Okay, is it in the bookstore?
They are getting some printed up just now.
Okay.
And they may have them before we're finished here. And they may not be quite as nice as this one, but these I did myself. And you remember they have nice colored photographs in them. And that sort of thing. So that was the actual device you were seeing this afternoon. One of them. Okay? Okay, let's see what else we have here. Okay, I'm going to take the speech, which I didn't get to make, and I'm not going to make the speech. I'm just going to check and see if some of these things I didn't talk about. Okay, whenever we get into how we get these magnetic flux measurements, we go back to years 1777 through 1855, and about the same time for another fellow. We're talking about C.F. Gauss and H.C. Oersted. And they were both trying to establish the electrical background field for the Earth with the external influences removed. So as it turns out, one of them did his measurements at night and came up with he came up with 50,000 volts, and the other one did his measurements during the day, and he came up with 100,000 volts, and that's per square meter of surface area. And this is above the ground with the ground influence removed, and it's a normal, natural electrical charge that's in the air at that point. Now, so there's a huge amount of energy out there, and you need a device which can pump it or move it from one spot to the other and make these voltage differences so that you have a potential. If you have the same voltage here and the same voltage here, you don't have any potential difference, so nothing's going to happen. Yes, sir?
In the schematic that you showed of the coil, or approximately of the device that you had on,
yes,
it showed a capacitor connected to ground.
yes. Okay, that is a blocking device. It could either be a resistor or a capacitor or a variable of either one of them.
Is that grounding device the source of the negative impedance?
Well, see, you've got two coil systems there that are working, so you have to tune one of them to make, you have to have one of the coils with a tunable device on it, so the grounding, you can stick it in the grounding end of it, or you can put it somewhere else, but it's convenient to put it into the ground.
Well, you mentioned that the source of electrons for the system
Would be coming from the Earth.
Right. Is that the source of the effect that you get in your system?
Yes.
To show a negative.
If the electrons are not coming out of the ground, they're coming from either an air grounding or an earth grounding.
But there's no other device that you require on your coil.
No, it's very simple. As a matter of fact, when I started building these things, I put all kinds of things in there that everyone thought should be there, and which the books on coil building and Tesla coils and everything said, well, we need a spark gap, we need this, and so on and so on. And when I realized that a wire has its own induction and capacitance and that sort of thing, well, that told me immediately that I did not need a spark gap, because it's going to load and unload based on the frequency that's attributable to that piece of wire.
You need to put it in a...
The spark gap is not a necessity.
You need to put it in a particular geological area?
It started out that way because of these high concentrations of negative electricity in certain areas. And the problem in the very beginning was how do you get, you've got these two areas of different potential. So how do you turn that into something useful? And it became obvious that you were not going to be able to put a cable between the two, because a cable of any size, regardless of how large, was going to vaporize like a flash bulb whenever you grounded it. So another way of looking at this would be that if you take a room full of ping pong balls and you get them all going in many directions, and they're bouncing around, there's a certain amount of energy in that room. But if you line these ping pong balls up, and you can do it magnetically, and then all of a sudden you've got a tremendous amount of energy that was not present before. And this is what resonance is. It's what superconductivity is, and that sort of thing. Okay, I'm going to draw you a diagram of actual working unit that was presented on the device this afternoon that you saw. Okay, I'll do it with a block diagram first, so it'll be real simple, and then I'll do the individual components. Okay, what you need basically is a power source. Whoops. Okay, and that will be a battery. It can be anything from, say, a 1.5 volt battery up to, say, 12 volts, or anything you want it to be, just about. And you can control your output somewhat by the amount of voltage that you're putting into it. Okay, the next item which shows up in this would be, in our case, we have simplified it. We go into the Tesla coil part, but I'm using a laser module which shows up in the Xerox machines, and it takes care of the step up in the voltage for you. And basically going into that, and then from that we're ready to go into L1 out here. Okay, this is your tickler coil, or the kicker coil, or it's the one that's going to set things up for you so the other coil will know what to do. And say that you have over here 12 volts. Okay, it comes through this device here, and say that it's coming out 8,000 volts. And immediately someone is going to say, well, that's 8,000 volts, and it's at, say, 30 microamps. So there's nothing there. Okay, as we found out from Ohm's law, when you get into this type of device, that dissipation, ohms and amps are dissipation, and they're after the fact. So if they're putting microamps in here, it's simply telling you the amount that's being thrown away. It's not telling you the amount that's there or was left. This is the 12, let's see, 30 microamps, okay, is the amount of dissipation that occurred when it went through that step-up coil. And that primarily occurred due to the resistance of the wire. The wire in this type of device is about the size of your hair, and there are many, many turns to it.
Now, what is the second thing?
Ma'am?
What is the second box?
This one right here?
Yes.
This is a laser module.
Power supply laser?
Well, they show up in Xerox machines. They show up in laser printers. They're a little high voltage module. They show up in all kinds of interesting electronic devices. It's any type of device that needs a high voltage source.
What frequency is it?
It might, something very similar to this may show up in your bug zapper or your electric fence or all other kinds of devices that work on voltage step-up, yes.
What frequency is it?
What frequency?
The output.
Okay, the output frequency is going to be determined by the length of this wire right here. The highest frequency that you have represented in any of the components is going to be the dominant frequency. That's going to be set by the length of the wire, huh?
Is that then a little high voltage DC supply?
Well, actually, in the laser module, you're correct. Actually, you have one output, and then you have the ground deal here. In some of them, this ground deal comes back. Here's your input over here, which would be, excuse the expression, plus and minus. One is higher, greater negativity than the other. So this comes back, instead of being earth grounded here, will come back and ground into the so-called plus deal.
So would it be possible to use a coil from like one of those disposable flash cameras?
Any step-up coil. It doesn't have to be a laser module or anything else. I'm going to show you just a little bit examples from automobile transformers and a number of other sources.
I was more concerned with the output because most of those can't put out more than 400 volts.
Well, yeah, I have them that put out 30,000 volts, and then you triple it from there, and then you're just then getting into the L1 coil, and then you take it from there. So this is going to be our L1 coil here. Or,
Is the voltage output from the laser module area, is that critical? Or?
it's not critical. In any event, you're going to have more voltage than you want. There's almost no way to do this and have the voltage that you really want to end up with, unless you're wanting to make big sparks. And that's not the object of what I'm doing. I'm trying to tame it and bring it down to where you can do something with it which will be useful.
How many turns on your L1?
Okay, you get into a division or multiplication situation. So once you know the length of the wire, you know what frequency you want to run it at. Well, you cut that wire so that it matches the wavelength of that particular frequency, and then your inductance and capacitance will take care of the off and on deal, which you would expect the spark gap and some other things to take care of. So you put, say that you have coming into it, for example, say 8,000 volts. We just let that for convenience purposes. Okay, we put 4 turns. Say that we put 4 turns over here. 1, 2, 3, 4. Okay, you divide 8,000 by 4, so each turn there will have 2,000 volts on it. Okay, the next coil that we want to do, we can put 1 turn or we can put hundreds of turns. But what we want to do basically on that second coil, say that this one, this piece of wire here is at 4 point something feet, which corresponds to 220 megacycles. Okay, whenever you get into wave type arrangements, you have half waves, quarter waves, eighth waves, and so on and so on. So basically what you want to do on any turns or whatever you put on your second coil, they should be a relationship such that it will be either a multiple or a division of the same frequency. The second coil is going to run at a different frequency because the wire length is different. Coils are actually antennas that have been coiled for convenience. They work just fine as a piece of wire. But when you start putting them in a winding them, you're doing that more for convenience than anything else, and it's going to change your inductive characteristics and a number of other things, but it's not going to be detrimental to what you're doing. Yes, sir? I thought I saw someone with a question. Okay, once you've got this thing divided down and you've got 2,000 volts on each turn here, then you're ready to go to your L2 coil, which will be the second one. In many cases, that is going to be a great many more turns than the L1 coil, but it may be one turn. So if you want to, say, 2,000 volts instead of a great deal more, then you've made just one turn, and make it so that it's a division or multiple of from the length of the other coil, so that they will react from a frequency standpoint properly. Now, you can get computer programs where you can figure these things all out on the computer, and you'll end up with the same answers. If you do it the way I'm doing it here, you can do it off the top of your head, and there's really very little mathematics involved. It's not that complicated. As I mentioned earlier, this is one of the things which I teach the Cub Scouts to do. So if they can do it, you can do it. If you got them and you give them, you've got a group of these kids and you give them the parts and tell them what to do, and they do it and take it home and Dad, here's my over-energy device. Okay, we've gone to the next step here and say that we've got one turn, and on this deal it makes one complete circle here, and it's has to be grounded in order to pick up the maximum effect of the electrons. And in order to ground this thing, see, we've got two different coil sets there. Now, anytime you add a capacitor or any other device or resistor or anything else into this circuit here, it's going to lower the frequency, so the highest it can be will be based on the length of the wire. And then if you add something else to it, well, then it's going to lower the frequency. Okay, we've got two coils, and they may be very slightly out of tune, not precisely tuned. So you need a variable device here, which can be a variable blocking device, which can be a variable capacitor, or it can be a variable resistor, or a number of other things. And you have to do this by experiment, and don't put any real heavy resistors in there. I mean, any high resistant deals. Put some that, say, like down below 500 ohms, maybe around 100 ohms or something like that. And this is going to be that shunt that's in the resonant circuit that we were talking about a little bit earlier. And it's going to be the dam that's going to hold the water behind it, so to speak. Okay, at that point, we've got 1,000 volts in a radio frequency setup, which is absolutely useless unless we do something else to it. So at this point, it's not an eraser, is it? It is? Okay. Well, it works. Okay, we're going to pick up where we have the one turn here, and we're going to take it on to the next steps. We've got one turn here, and we've got it grounded with a variable device on it so that we can fine-tune it. And at that point, we've got, from this deal, we've got an output out here, which is in an oscillating type, alternating current type situation at radio frequency. Yes?
One quick little note there. That ground symbol, could that, in alternative, be the negative of your...
Yeah, that is the shunt in the resonant radio frequency configuration that produces the dam that keeps the energy. Once it gets to oscillating inside the system, if it can come in, but it can't get out unless it is hooked into another system.
I guess what I'm saying is whatever L1 ground is, or
Yeah, well, it's simply a blocking device which keeps your resonant coil system, which normally you have a capacitor and a coil, and you've got them like this. Well, in our case, we've put both the capacitor and the coil in one wire, and we've eliminated some components that are subject to fail. When we do that, capacitors are subject to fail, so you've actually made a device which is less likely to fail. It has greater longevity. So anyhow, we're going to be throwing pieces away as we go through here and see how we can still end up in business. Okay, we've got 1,000 volts here, and it's a radio frequency, and we need to get it into conditions so that we can run something which is 120 volts at 60 cycles. Oh, yes, sir.
Just to clarify, L1 ground and L2 ground are...
Well, they're grounded in different ways. L1 grounding can be grounded back into the laser module itself, or it can be grounded into the earth or into the same common ground that L2 is actually grounded to. You'll notice in the Tesla coil books that frequently both those coils have the same common ground. Okay? Okay, we've got 1,000 volts, and we're going to go to a lower voltage which we can do something with, at a waveform which we can do something with. So at this point, we're going to have to go through a diode bridge. Let's see. Okay, we're going in for the alternating current, and we're coming out to DC and DC. Okay, at this point, we've got something which we can take through one or more steps, and we're where we want to be. We're very close to where we want to be. Okay, we take off from the DC here, and we come out like so, and we're going to inject a coil in here, which is actually 2 Tesla coils, bottom to bottom. This is the middle here. This would be the base of a small Tesla coil, and this would be the base of a small Tesla coil. At this, yes, sir. I can hardly hear you.
Do you have the DC to AC?
Yeah, we've got DC coming out here, so we've got to pulse that in order for this coil to work. So what we do, we put a capacitor in parallel there, which gives a pulsing effect or an off and on effect, which will cause the magnetic field to be, or induction to pick up in these 2 other coils. Do what?
I think what he was referring to is your bottom end of your AC. You're hooked up into the bridge. Into the
Well, actually, I'm trying to get around that. Let me come across here and do that sort of thing. Will that be better?
Okay, now the other one?
The other one, I got to do the same thing. I got to lump it in order to get over there.
Both at the same point.
Well, I'm going to have to erase it and start over. I'm going to do it on a larger scale. Okay? We'll do it on a larger scale where I can get my lines in there properly. Okay, we've got our diode bridge here, and we've got AC, and we've got AC, and we've got DC and DC. Are we okay so far? Okay, we're going to turn these diodes so that the cathode end of it is pointing towards DC right here, and we're going to turn this one so that the cathode is pointing towards DC. Okay, the 2 coils, the 2 here, the cathode is pointing towards the AC, and here it's pointing towards the AC. Does anybody know why we do that? What we're going to end up with is basically a SPAC, a DC. A DC, of course, if you've got your reference point here, you've got alternating current, which is doing that sort of thing. Okay, in DC, you're going to be on just one side of that reference point, which will be the top side or the bottom side. And you're going to be on just one side. So at this point, the waveform coming out of here is going to be a DC SPAC. Okay, and we're going to change that. When we go through this thing right here, that's going to change to, say that this is 1,000 volts up here. Okay, we've got a DC SPAC with 1,000 volts on it. When we go through this system here, we're going to have a DC SPAC above and below. It's not going to be DC anymore. It's going to be alternating current. And it's going to be double the voltage that you had here. So we've gone through a voltage doubling maneuver here. And we're coming to the waveform that we're really looking for now. We're getting very close to the waveform that we're going to need in order to run our 60 cycle device. Okay? Okay, and this double Tesla coil thing here has a variable blocking device on it, and it's grounded. Two bases of the Tesla coil are grounded. The top of each Tesla coil will be these ends right here. Okay, at this point, I'm going to have to race this in the center because I'm going to superimpose something. Okay, you just have to keep in mind that you've got a double Tesla coil there that's oscillating, and it's forming a double SPAC deal, which is very close to what we're going to go for. Okay. I'm going to turn this around a little more. Okay? Is it safe to say that everybody can see it? Okay. Yes, sir. There are 50 turns on each end. The diameter of the PVC that I wound it on is 1 inch, 1 1/4 inches. There's 50 turns on each end, and add an extra 2 on one of the ends. And the reason for that is that you want one end to be delayed just slightly more than the other, so that you're going to have an offset on those spikes when you see them on the oscilloscope. Did I hear a question?
Could you say that again?
Okay. On that coil, we've got 2 spikes, one above and one below now. And we're getting very close to the waveform that we're going to be wanting. So at that point, we assume that the grounding and other things and the bases are still there. Okay, at this point, we've got 2,000 volts on this arrangement right here. Okay, now say that we want 100 volts instead of, I'm going to round it off instead of saying 120, which is going to create a mathematical problem shooting from the hip, so to speak. So I'm going to say that we want 100 volts. And in order to do that, we need 20, let's see, divide 100 into 2,000, and we need 20 turns there. And what we're going to do is come in from this side with a piece of wire, and we're going to, it's going to be loosely looped around this. It's going to be very informal, and it's going to come off like this. And once we're off out here, then we have another wave shaping maneuver that's going to occur. And at this point, what we want to do is round those spikes off so that we get what we're looking for out here is a normal sine wave thing. And we need to delay the time a little bit there so that when it's up at that top there, that it's going to spread out in this top area. And when we do that, we end up with this type of thing. Now we're at the waveform where we can do something. We've got 100 volts, and we've got the proper waveform. Now we're at the point now where we're going to set the frequency. And there's going to be another maneuver at this point. And basically, this is where we go back into the over unity thing. So over unity people will be happy about that, maybe. We're going into a resonant iron core transformer system, and this is where we're going to end up with all the amps and the other things that the electrical people would like to see, maybe. So say that we go into an iron core transformer here, and we're working off of it. And this device is going to, it's self-resonant transformer. It's a self-resonant isolated transformer, which means that the other side of it, which I'm going to put up in a moment, is not connected in any wires. The only connection is through the induction. So we're running it through this thing that's going to set the 60 cycles at this point. Okay? And then we're going to take the one which we're going to come off of, and here's where a load is going to be added. This is where the wall plug in the house is. So we have a magnetic flux field on this one, which is driving this one, and the self-resonance of that particular transformer is 60 cycles per second. And I've got one over here on the floor I can show you. It works at 4,000 volts. It's a real heavy looking, kind of block of iron looking deal. Let's see. Yeah, that's it. Okay, this one is good for 4,000 volts. You see there's two different sets of coils here, one sitting on top of the other. This is an isolation transformer. And do what?
Was the ratio 1 to 1?
No, this one is, the top coil is set for 4,000 volts. The bottom coil is set for 2,000 volts. So in our case over here, both coils are set for the same. So you can either step it up or step it down. At this point, you can, depending on what kind of output you want. If we want 440 or 6 whatever, or 220 or that sort of thing. So if the two units are equal, you will end up with an equal amount of, say, 100 volts. Sir? How did you guess? Well, the price is right. That's what it is. I had a neighbor who was an electrical engineer who knew what I was doing, and he and his son switched out their microwave oven, and they were curious as to what was inside, and after they tore it apart and found this thing, they came bouncing over to my house and said, well, we think you need this. This was about 6 months ago, and I didn't know that I needed it. But whenever I got to the point where I knew that I needed to do something like that, well, I realized I had this thing out in the garage, and rather than go out and spend $400 buying one, I already had one. So this can drive a very substantial output of electricity.
Question, how can you be assured that it's going to make exactly 60 cycles?
Because the resonance is built into the transformer. You don't see it here, but there's a capacitor that goes with this. You see, this has a certain amount of induction, and there's a capacitor that you put with it that forms your resonance circuit. Okay?
In series or in parallel?
Well, in this case, it's in parallel. Almost all the things that go on here will be essentially in parallel, because when you put them in series, you get a degradation.
Would it be on the beat side or on the load side?
Where is this? Okay, if we're talking about the one that we have here, we have 4 sets of wires. You notice that with these little snap-on deals here?
Yep.
Okay, well, those are the output deals, and these other wires, these 2 heavy ones, are the input, and this is the grounding.
So you put the capacitor in parallel?
It's going to be in parallel.
On the input?
On the input. Okay, at this point, we've got our 100 volts, we've got 60 cycles, we've got the correct waveform, and we're in business. Yes, sir.
On your back-to-back Tesla coils, how many turns did you have?
There's 50 turns, and on one side add 2 additional, which gives a delaying effect on the second SPAC there, so that you get an offset on it.
So you have 50 and 52.
52 on one end and 50 on the other. It doesn't matter which end. Huh? Go ahead.
And the Tesla coils are wound in...
One is wound clockwise, and one is wound counterclockwise. And that is part of the slowing down of the electrons so that you end up with the waveform that you want. Okay? Go ahead. Over here.
Are you going to demonstrate the system now?
We will see it just a little bit.
Yeah, I had a question. You had the primaries together on the back-to-back Tesla coils, and then that coil that's going to the isolation.
Well, remember now, what we're working with is a DC SPAC going into those things, and what we're trying to do is get rid of that DC SPAC.
Yeah, my question is that coil going to the isolation coil is in addition to that, so that's the third coil around that. 20, is that right?
Okay, tell me when I get there.
That one, yeah, that right
This one right here?
The 23 you have in the center.
The 20 turns in the center is it's lowering the 2,000 volts. You've got a transformer there.
People with questions, I'd like you to step up to the mic because we want to get the questions on the video. We can't hear you.
Okay, by keeping this sort of informal, it'll make it a lot easier on me. This is the wrong time of day for me.
On the Tesla coil, is that close wound?
Close wound?
On the two, on the 50
so,
and 52.
Because you get a lowering and you get your Q factor messing you up a little bit, but the induction on this thing is so strong that you're not really having a problem. Yes, sir.
What's the amperage of the load?
The amperage of the load, it will be the same as the voltage until you put a load on it. And once you put a load on it, that sets your amperage.
I don't get it.
That doesn't make sense to you? Okay. Earlier, you probably weren't here whenever we talked about it, but ohms and amperage are after the fact.
Right.
And it's not until you put the load on there, or the resistance, or the dissipation factor, that you have ohms and amps. So you have 8,000 volts or 2,000 volts or whatever. That's how much you've got. And you have potentially the same amount of amps as you have volts if you work it correctly.
So you can run anything.
Sir?
You can run anything.
I couldn't understand.
You can run anything.
You could run just about anything you want to. One of the units I had up this afternoon will run a diesel electric train. You can disconnect the diesel part and put as many coaches on it as you want. And that unit, the induction, we were talking about the induction rate being so much higher than 60 cycles. Well, something millions of times smaller can produce the same amount of electricity as a very large 60 cycle generator. So that small unit would produce the amount of electricity that a conventional generator the size of this whole room would produce. I'm going to show you how this induction stuff works.
I'm wondering if you could quickly comment on the size of wire that's been used in this so far.
When you're working at radio frequency, you'd expect at very high voltage to have very large wires. Okay, that is very true if you're down in the lower frequencies. But when you get up into the radio frequencies, the diameter of the wire can be very tiny. It has to do with the size of the electrons and how they're spinning around and that sort of thing. So you can have a wire that's about the size of one of your hairs in your head, and you can have basically 1,000,000 volts on it, because the electrons are not going through the wire, and there's no dissipation factor, and they're spinning on the outside of the wire. So you can have this corona effect. See, I told you they were somewhere else. Okay, just put them on the table here, and whenever I get to them, I've got some magnets here which I want to demonstrate something for you. See, how much voltage would you think it would take to penetrate a quarter of an inch of PVC. It'd take a lot of it, wouldn't it? Maybe even a million volts. Okay, what I'm going to do here, I'm going to show you how the magnetic effect, it varies from okay, your induction is from magnetic effect. So you could take these wires, they can have a covering on them, they can be encapsulated, you can put them in solid concrete or plastic or anything else inside, completely insulated from everything. And these wires, when the induction effect starts taking place, which is magnetic, it doesn't see any of it. So that's why your induction works so well. And that's going to lead us right into what you were asking about. Everybody see that? There's magnets inside and on the outside. And that's the magnetic flux thing that we take a reading on for these maps that we were looking at with a Gauss meter or other kinds of magnetic flux devices. We can, by the reading, we can directly convert into the active electrical energy that's present. Anyhow, in my experience with this device, when I hook it up to it, it turns out that the L1 coil on this device has a 4-point-something feet of length of wire. It turns out that the wire which hooks onto the battery here has that same length. We're dealing with a radio device, so we've got an L1 there which is oscillating at the same frequency that this wire here that goes to the battery would oscillate at. So guess what? When I hook it onto this battery here, it's going to be generating electricity and feeding back into the device, and it's not going to be using the electricity out of this. And how I know that? These devices have been ran for as much as a month at a time, and with no lowering of the capacity of the battery. So if you're looking for an over-unity device, you've got one right there. And there's other ways of making it do the same thing. There's also a thing called a capacitor battery, which is a new invention which is on the market just this year, I think. It shows up in some of the computers and other things, and basically what it does, it stores electricity so that if the source misses a beat, it picks it up and keeps things going. So by putting a capacitor battery in parallel on these input wires here, you have an additional kick which would do the same thing as the wires were doing on their own. So if the wires were not the proper length so that they would pick up the radio frequency energy, then you would have your over unity type device in one case. In the case if the wires were too different length, you wouldn't be getting that feedback. They have to remember they have to be a multiple of or division of frequency which is there. They don't have to be the exact length. So if they had been 2-point something instead of 4-point something, that would still be a division of the frequency, so therefore it would still have worked. But with the fourth thing, you got more feedback. And that's one advantage of operating up in the higher frequency, because if you were run down below 200,000 cycles, this cable here would have to be maybe 400 feet long to do the same thing. So in the frequencies which I'm operating, it works very well, and it had a surprise effect which I only discovered after a certain period of time. I knew that something was wrong. My batteries were never running down. And the books tell you that that can't happen. So here I'm looking at the silly thing, and you're doing something you're not supposed to. What is it? But it turned out okay. And that I'm going to bring in now has 5, quiet please. The one I'm going to bring in now from the office has 5 1,000 volt lightning arresters in the circuit in place of the spark plug. And they're going to light up like a Christmas tree. So I've eliminated the spark plug and I've stuck lightning arresters in the circuit in place of it. I don't need them at all except to show you that the voltage is there and that things are going on. But for someone who's not sure these devices work, it's a cure for it. Yes, sir.
And you said you're stepping down 20 times.
Yeah.
From 2,000 volts
To 100.
But L2 has 1 turn, and your pickup coil has 20 turns. So you're stepping up, aren't you?
Well, when you're talking about L1 and L2, we're okay. Let me show you what's gone wrong there. This one right here is L2. This is L3 and L4. And out here, this transformer would be L5 and L6.
You got a 3rd coil over there on L3 and 4.
Point me.
There's a coil on your test.
Right here?
Yeah.
Okay, well, we should say that is L5 then. And this is L6 and L7. Is that better? Each one of those lightning arresters there, it takes 1,000 volts of actual real electricity, not diminished in any way, to trigger each one of those. So at that point, we know that our main coil system is working there, and we know that the outside coils are tuned to the same frequency. So if we have 40,000 volts on that inside coil, we have 40,000 volts on each of those outside coils. So this is built to show what an over-unity device in several aspects does. Now see the little 60 watt neon deal here? See? That's lighting up because of the radio frequency electricity that's running along my skin. That's actually 60 watts right there, and this battery is not putting out that type of deal. Sir?
Thank you. Can you put a bigger load on that?
You can put a load up to whatever the voltage is.
Could you do that? Can you plug the fan into it?
Okay, in order to do some wave shaping, actually we've got a situation here where we're going to be running the fan, but we're going to be doing it a little bit different than you think. But let me show you part of the components over here on what you're looking at, the actual device. Okay, this thing, you see the box is the diode bridge, and here's the system, but it's wound a little bit differently. As a matter of fact, I've turned this around backwards. I've got the windings on there a little bit different, but this is actually the mechanism that does the wave shaping that gets your double spike, that gets you set up for doing your waveform that you're really looking for. So this is one of the wave shaping modules. And the windings are, this thing is on there backwards. I've got it hooked up backwards. This is the resistor component, adjustable resistor component that works on the resonance circuit. Yes, sir?
Could you potentially run a home with one of these?
Run what?
A house.
Oh, yes. What we're looking at here is a great deal more than you would need for a house.
So one of those can
Yeah, well, what you're looking at running here will run a large office building. Yes, sir. Oh, sure. It's due to the fact that your induction is working at a radio frequency which gives you your higher efficiency of induction that makes the small device possible, because it's doing millions of times more efficiency and output in comparison to what's going in than your 60-cycle device would be doing. So that means that it could be millions of times smaller.
You just wire that into your house panel?
Well, you have to go through the wave shaping and set things up so that it matches the devices that you want to run on it. And then you're home free after that. Okay. Yes, sir?
I don't see an earth ground on here. Is it?
It's actually grounded in a way that you wouldn't suspect. It's in the ground. In this case, it's inside the module here, and it's coming back through one of these hookup wires.
But how is it getting to earth ground?
It's ground. You can ground these things into the air or into the earth. You have a great deal more efficiency if you ground them into the earth. If somebody will produce a metal pipe for me, we'll ground it into the earth.
Yeah.
Try your microphone.
Well, we need one that goes down inside the earth. And that's what this is all about. The inverter technology is what enables you to do what we were talking about. And we have a, let's see, oh, I forgot to turn it on over here, didn't I? Okay, how's that for 12 volts? So if we can do that with 12 volts, what can we do with 1,000 volts with an inverter circuit? Now this inverter circuit, I'm going to draw you what's inside this little box here. There's a resonant iron core transformer, which we were talking about. This unit right here is the main component of that inverter. There is this unit here. There are two transistors which are back to back, and I'm going to draw you that circuit. And when you put those things into this circuit here, when you couple them into it, you've got the same thing going. You can get rid of the battery there. But they have to be adjusted to the voltage which you're working with, and that device there is only made to run with 12 volts. We have inverter technology which interfaces between this device and any device that we're going to run. So that wave shaping deal that we were showing you over there, this device here with some other things added onto it is the equivalent of what's in that inverter there, except it's designed without the transistors. Okay, basically what you have here are two transistors, one on each side, and you have a resonant iron transformer in there which gives you your 60 cycles, and you have a couple of resistors, and that's the whole device. So what you do, you take that circuit and you convert it so that you can handle the output of a much larger device. So there's your inverter technology being adapted to work with the output of the test signal. Every time you go through a change of coils there, you're either going to have a step up, step down, or you're going to have an isolation deal where the same amount passes through. Basically, you have to have some way of storing the energy in order for it to become useful. And there's several ways of going about making it useful. One would be using a diode bridge. And the problem there is that most of the diodes that are available aren't high enough frequency or high enough voltage or amperage. You can get diodes that are above 2,000 amps, but generally speaking, the frequency rating on them eliminates the use of them. There's an interesting way around that, however, because the equivalent circuit of a diode is basically a capacitor with a resistor shunt on it across the two poles of the capacitor. And when that's in, yes?
Maybe we can just use the old vacuum tube diodes. They seem to be...
Yeah, well, you can use those. They'll get you into some higher frequencies and maybe even some higher voltage.
Higher amperage as well.
Yeah, and how to identify a diode that works at high voltage, the length of the diode has to do with the voltage, and the diameter has to do with the amperage that it will stand, generally speaking. Most people think that lots of volts and no amps, and that's the thing that try to get you with every time. However, volts are basically the water that's behind the dam. Until you poke a hole in the dam, you don't get any flow rate or amperage and that sort of thing. So whatever your voltage is whatever your potential is, and how you go about letting that thing through the dam is what's going to give you your useful energy. And in this case, the useful energy is accumulated in capacitor banks, and a megajoule range is not unusual at all. And I'm going to show you some things after a while that relate to this that are in place, and you can actually buy them off the shelf, so to speak. And they work for rail guns, plasma studies, and a whole slew of things. Most of the universities have these capacitor banks. And anyhow, once we get into the laws of motion and into the EMC square thing, it's real easy to convert that over to what we want to do, because basically in the energy business, you've got magnetic and you've got electrical energy. They're both the same coin, just different sides of it, and you don't have one without the other. If you've got electricity, you've got magnetic energy, and if you've got magnetic energy, you've got electricity. So that's going to come back in a little bit, and we're going to find out how to measure the large amounts of electricity that we have very safely. What that means basically is that your electrostatic voltmeters and other kinds of things that measure magnetic flux can be used due to Coulomb's inverse square law. It was Newton's before it was Coulomb's inverse square law, which means basically you take the remote reading and the square of the distance times the remote reading, and you've got a direct reading on the magnetic flux, which converts directly into electrical flux. So you haven't had to poke your finger into a 2 million volt device in order to measure it. If you try to measure it with the conventional systems, I'll show you some after a while. You'll have a resistor stacked as high as this ceiling here and then some, in order to divide the voltage down to where you can measure it with your instruments. And that gets to be very complicated. It's also very dangerous. So, it's much easier to use the magnetic flux, which is the actual other side of the coin, but it's not dangerous like the electrical flux. Whenever we start doing our conversion from EMC square to our formula, which we're going to use, remember now that half the energy is magnetic and half of it is electrical. So we're going to put this crooked. Okay. Half the energy is electrical and half is magnetic. So we're going to have to multiply our formula by 0.5, which is half, in order to get, say, the electrical energy, which is what we're actually looking for. So whenever we're going to let, in our case, energy, we're going to let it equal joules, which happens to be a universally convertible unit. And we're going to say that joules equal mass. In our case, mass is going to be coulombs or electrons or whatever you want to call it. And the way we're going to collect those things is in a capacitor. So our formula is going to read joules equal 0.5 times capacitance times, in our case, velocity is going to be potential or voltage. And those things convert over relatively easy. And the next thing we have to do in order to ascertain how much energy is there is to take the number of cycles per second. So we multiply what we have just got by cycles per second. In capacitance, we're using our farads. So we've got something like 0.3 or 4 zeros, and then we've got a number. And then we're multiplying that times the voltage, which say is 100,000 volts or more, and that sort of thing. And that's going to move the decimal point over some in your favor. And then that doesn't really amount to a whole lot of electrical energy at that point. But whenever you start multiplying the number of cycles per second times that, then all of a sudden you've got an awful lot of energy. And basically what happens at that point, you pump it on into a set of capacitors or a capacitor bank, and that capacitor bank takes it on from there. And one of the slides I'm going to show you in a little while shows you that in 1893 that's exactly what Tesla was doing. It shows the circuits for running motors and electric lights and that sort of thing. So he was actually doing the same thing then. So it's not anything new. It's how you go about doing it and the type of capacitors and a few other things that you use. Now, where you get into trouble on this sort of thing is the fact that you think a resistor is a resistor. Well, it doesn't really turn out that way, because most of the resistors are better capacitors, or they have more coulombs and more henries than the actual things that you want to get those out of. So you have to have resistors that are non-inductive and non-capacitive, and those are a little bit hard to come by. They exist, and if you go into a electronics store and try to buy that sort of thing, you're going to get a very interesting reaction, because they've been in the business for about 50 years and they don't have never picked up a resistor and measured the LC factor on it, huh?
Yeah, this problem presents itself very clearly in radio, where you try and dump a lot of power out of a transmitter into a load. If you use a large, say, 50-ohm wire-wound resistor, the inductance of that wire-wound resistor will present a different impedance to the...
Yeah, it messes up your impedance, and your device doesn't work, and a whole slew of other things. Now, since last year, there have been hundreds of people that have tried to duplicate what I did, and there's about 12, I guess, out of several hundred that were successful. And the main reason most of them failed was the impedance problem, because when they started putting capacitors and resistors and various other things in there which control the timing circuit so that the different coils could talk to each other, well, basically they blew themselves out of the water. And none of them, or very few of them, ever bothered to check to see if there was something there other than resistance or capacitance or whatever, or even in your L1 and your L2 coils. For example, some of the L2 coils I have like 300 or 400 microfarads, and that's not... Yeah, well, you can change that very quickly. Basically, what that tells you is that instead of having 400,000 cycles a second, you got 400 cycles per second, which actually that's kind of interesting, because that's down in the range where you can start running electric motors and such. So the potential exists there for going directly to the motors instead of having to go through several stages to get to them. whenever we talk about ambient and that sort of thing, we get into a situation where as the frequency increases, the magnetic lines increase, and it's those magnetic lines of force that disturb the electrons, which cause more electricity to become available to you. And that's basically what's happening on your L2 coil as you start from the bottom of the L2 coil and go towards the top of it. Each winding there has capacitance and other types of things, and those things start squaring as you go up towards the top end of the L2 coil, and the net result is that you have a tremendous magnetic flux field going on at the top of that coil there, and so that also presents you with some real interesting possibilities, because that's the end that you really want to get your flux off of in order to go ahead to your next stage. And a small coil, I'll give you a for instance on it. Say that that L2 coil has 100,000 volts potential, okay, and it's cycling, say, at well, it's normally going to be above 20,000 cycles per second. So in order to ascertain how much energy you've got available to you, you have to multiply it by the number of cycles per second. So you can see that with 100,000 volts output on a Tesla coil that you've got way into the high megawatts or megajoules. And if you've got a way of containing that energy so that you can get it onto the next stage properly, which that's your capacitor banks. And a real nice capacitor bank for a megajoule production deal, they're available, I want to say off the shelf. That's not really true, because there's no two of them that are ever alike. But I'm going to show you some in a little bit, and you'll see what the size of them would be. Some of them are about the size of that podium there if you double the height on it, and that would be approximately 1 megajoule. So, and it consists of numerous banks of capacitors that are in the, say, the 200,000 volt range and that sort of thing. And you might say, well, how do you get capacitors in that range? Technically, it's not as difficult as you might think. There's your dielectric or your separation deal that separates the plates there. There are several types of things. Kapton is one of them. It has about 7,000 to 8,000 volts per mil. So several mils on that, you're beginning to move up into the voltage, and by the time you get up to, say, a 1/16 of an inch or something like that, well, you've got real high voltage. Yeah.
What was the name of that material?
Kapton. It looks like mylar, and it's kind of amber color, and Dow Chemical Company makes it, and a lot of people sell it. It's not always used for capacitors. It's used for a lot of other things. Yeah, you can put printed circuits on it and things like that, and you can build a radio device that you can roll up inside something the size of a pencil that's equal to a large color television or something like that. You print your solid state devices right onto the circuit. And then on top of that, you put say another sheet of it, and then you press it so that they seal against each other, and the net result is the whole circuit is inside this very high voltage dielectric, which doesn't really, all it does is just protect the device. And what I'm showing here is the conventional power triangle in energy transfer, and number C on there is considered to be wattless energy or useless energy or whatever, and that's your volt amperes reactive part of it. Your A part there would be volts times amps, which is electricity that's in the wall that until you ground it by closing the switch is not useful. and at the time you ground it or run it through a device to an earth ground or whatever, then you've got number B there. So anyhow, in this power triangle, you can take a small power unit and you can power a much larger power unit. For example, an example of that might be an atomic bomb, because you use a small bomb to set off a larger bomb, which in turn sets off the atomic bomb. And in this case here, you can use a small power system, and you can pump a much larger power system. And doing that, you really don't have to pump it all that much, because like I mentioned a while ago, at 100,000 volts, you're into the megajoules range already. And 100,000 volts is relatively easy to obtain using a Tesla coil. Even a small one can do that. And the large ones, you probably have too much energy, and it's self-defeating after you get past a certain point, because even if you were able to contain it, the containment problems would be so great that you'd be better off to try to do it at a lower level, because you can use multiples of these units instead of one gigantic one. And if you need megajoules, for example, one of these units that has about 100,000 volts output with the proper capacitor bank and that sort of thing can equal Hoover Dam, which is about 500 megajoules. So you've got something that will sit on a coffee table that will equal Hoover Dam. Or it's larger, it's as large as maybe 2 or 3 atomic energy plants. And yet you're actually using a small amount of energy in order to activate a larger system, which in turn gives you off your potential, and the potential is captured in capacitor banks and that sort of thing, and at that point, well, then you can process it further. In our case, the electronic flux that we were talking about is you move from one unit of electronic flux to a larger unit of electronic flux. These things are squaring, and as the flux squares, the number of electrons that are being disturbed is squared, and the net result is that you end up with a lot of energy that you did not have there previously. I'm going to show you a device after a little bit that works like a radio station, where if you have one coil running at a certain level and you have other coils in the general area, if they're capable of responding to that frequency, that they will duplicate exactly what's going on in that first coil. So you can have one coil that's running at a certain energy level, and you can have dozens of other coils sitting around it, and they may be different distances, but the fact that they're being stimulated by this central source, they start reacting just like they were that original source. Okay, can you see it this time? And you'll notice that what happens whenever you have 100,000 volts of electricity, which I had mentioned earlier, and when you start multiplying it by the cycles per second and the other factors that enter into there, you can use much larger capacitors than I've used there. I've used relatively small capacitance, and you can switch higher capacitance in there, but your amperage is going to burn up your coil almost immediately. The moment you start raising that capacitance, your amperage is going up tremendously, and you may end up with 4,000 or 5,000 amps almost immediately. And it's obvious that the equipment that you have, including your capacitors, probably couldn't handle it. So basically what you would have hot spots on your coils, which would end up melting off the protective coating and maybe even melting your coil. And the capacitors would probably fail because the dielectrics and other things would be heated up so much inside that you couldn't build a capacitor which would function with that kind of amperage. So how you get around that, you have banks of capacitors in parallel, and none of them individually are loaded to the extent which would cause failure, but by the same token, all added together, you end up with a product that's very high, and you end up with an awful lot of amps and an awful lot of volts. You're looking at one there that's in the megajoule range. Basically, what you're seeing is a 12-inch PVC pipe that's been cut in a piece that's about, top piece is 16 inches or so long. The bottom piece is about 16 inches or so long. The larger round thing that you see there is a Rubbermaid drum dolly, which I took the rollers off of. And it happened to be 25 inches in diameter, which was in the acceptable range for the L1 coil. And what you're looking at down below, you're seeing this is an automobile ignition coil from a 1968 Pontiac. It's brand new, however, the coil is. And I've built a timing device which is built onto this particular deal here. It consists basically of an electrolytic capacitor that's I think it's 4,700 microfarads, and it's not very large. It came from Radio Shack, and I think it was maybe about $2 and something. And there's a shunt across the two arms of the resistor, two arms of the capacitor with a resistor on it. And it doesn't take a very large resistor because your basic cycles per second there are going to be the multiplication of the resistance times the capacitance that you have. And that works backwards, so that if you had, say, 10,000 microfarads and you had, say, 100 ohms, that's moving the decimal point in such a way that you'd actually multiply 100 times the capacitance there, and you'd see the number of cycles per second. Now, in this particular case here, since we're using an automobile ignition coil, we know that the RPM on an automobile is, when it's running at normal speed, is maybe 2,000 or more RPM, and you've got 8 cylinders there, so you would think that the times off and on of that particular automobile ignition coil at its normal frequency would be about, say, that 2,000 or more times of your capacitance. Let's see. So your cycles per second there is going to end up being like, say, 14,000 or 16,000 or something like that, which is not very many cycles per second. But it turns out that that's enough to make a dent in things, and if you multiply that times some of your other factors, well, you end up with a lot of energy out of this particular coil. So this is one that you can build yourself real easy. Yes?
How much energy are you getting out of that?
Well, this particular one, I used there's 2 computer programs which are available normally, and then I have a couple others which aren't normally available. And I used every one of them and ran the thing, and I came out with very, very different answers from each one of them. This one was supposed to have come out 400,000 volts at a fairly high cycles per second sort of thing, and whenever I got it built, it turned out that the capacitance by the large diameter and the capacitance between those wires, it came out with a natural frequency of 400 cycles per second, which a while ago I was mentioning that it's possible to build these coils so that they will run down in the range where you can get electric motors that are set for that particular cycles per second. Yes?
What kind of wire are you using out there?
Well, what you have to watch out for is the fact that voltage difference between 2 wires. So if there's 750 volts different protection on one wire there, between the two wires you would have 1500 volts possibility that you could play with, so that you could have a differential of voltage going as you go up of 1500 volts, and you'd probably want to stay at about 1000, which would give you a 500 volt safety factor. In this case, there's 130 turns on that thing, so it'd be 130 times your 1000, say, if that's what you put on each turn of your L1 coil, which would be this one. It has 3 turns.
Your L1 coil's got 3 turns?
Yeah, this one has 3 turns of number 8 wire. Yeah.
The L2 coil has how many turns?
The L2 coil has 130 turns on it, and it's number number 14, I believe. It's multi-strand wire, because if you use the solid wire, it's very difficult to control and make it look nice. The solid wire goes its own way. It's very difficult to make it. Sir? What type of wire? Yeah, it's not truly Litz type wire, because to be Litz type wire, each individual strand, when there are many strands, has to be individually wrapped with a little piece of cloth or something to be a true Litz wire. But it would qualify as a Litz wire under the terms that we would use maybe today.
Like grounding cable on a lightning rod.
Yeah, basically what happens is that these multi-strand wires are made for DC, generally speaking, which any sort of resistance knocks the DC down real quick like. So you're using a DC type wire, but you're using it with AC.
What are you using there on your secondary?
On the it's a multi-stranded wire.
Where do you get that wire?
I got that at one of the electronic supply houses, but I noticed that Ace Hardware and some of the lumber supply places have very similar wire.
What gauge is it?
It's number 14.
What voltages were developed in the secondary?
On the secondary, that depends on how much you put in from the input source and what kind of resistance you put between that and the other thing. Now, there's some diodes and other things that are in the circuit there that control what's going in. So the output on this thing was, even after you go through all the commotion here and that sort of thing, is like maybe 70, 80,000 volts. Uh-huh. Okay, kind of direct me a little bit. Here's the detail on this thing right here. So, well, the spark plug goes to the earth grounding. That is, you've already passed through all the circuits, and your timing is all set and that sort of thing. And as a control on the load that's going to be built up, your potential that's built up, this thing, it goes to an earth grounding. See, if you notice on the output coil here from it, there's only one wire coming out. Okay, somehow you have to get back to your negative pole on your battery or a ground plane or something like that. So in this case here, there's another cord that hooks onto this, and it goes to an earth grounding, which there's an earth grounding. It comes off of one corner of that high voltage coil there.
It's a small orange and yellow mechanism in a U-shape right behind the spark plug.
I couldn't understand.
On the terminal block, what is the small orange and yellow mechanism?
A small orange and yellow. Actually, what I've done here, you can't really see it, but I've got a circuit that's going along here with a capacitor on it and a resistor, and I folded it back. Instead of having a series thing looking at you that would go out like this, I've gone down, skipping the contacts there, and then I've come back to a certain point. So I've got
resistor and a capacitor in that deal. It turns out the capacitor is about this long and the resistor is about that long, so the net result is I loop back, and that orange thing you see there is my where I had a blank space that I had to bridge in order to get the circuit closed, and that's what that orange thing is. There's nothing magic about it. Yes?
I must have missed what that little square was back there. It looked like it's got writing on it.
I have trouble hearing you.
It looks like a large capacitor. Is that a capacitor, that white?
Yeah, you're looking at 10,000 volt capacitor there. It's reconstituted mica, and it's building up. That's actually what's it's working between the blue one here is the negative lead coming back from the L2 coil. The one that's white here is your positive lead going out. So between those two, in relation to your other things, you've got this 10,000 volt reconstituted mica capacitor, which how that happens, they take mica and they break it up in little bitty pieces and they mix it into a glass ribbon type deal, and that becomes your dielectric in this particular case, and they go to very high voltages. I'm going to show you some in a little bit that go to over 250,000 volts.
Yeah, this one here was what farad is it?
It's 0.01 microfarad at 10,000 volts. Yes?
Does this unit, do you have anything, any load on this device at all?
Well, before you can put a load on them, you have to put it into a capacitor bank and get your thing built up so that you have something to put a load against. If you try to put a load directly onto it, it's going to detune it and you'll end up with nothing. Okay, that's that particular device. Okay, here's one that I'm going to show you the schematic on in a little bit. The top one there with the yellow deal on it. Actually, your this is going to be your L1, this is going to be your L2, and this is going to be an L3. You remember I said that the lines of magnetic flux on the distal end are the busy end of the Tesla coil, are very large in number. Okay, well basically what's happening there is that this is the offtake that goes into the diode bridge that you see there. That diode bridge is built on the underside of a plastic case. One half of that plastic case, it's a little box that you build electronic projects in. And coming out, what you're interested in here, this is going to be your plus DC, and this is going to be your minus DC. These are your two AC things going into the diode bridge. Okay, at this point, this particular one is set up so that you get 60 cycles at a usable level where you can just plug directly into it and you're off running. And it's intended to go directly to without the capacitors and other things, and it works fairly well, but it would work a lot better if there was a nice capacitor bridge in there somewhere before you get to the area where you're using it. Now, from this you go from your plus DC, you come over to the center deal here where the jumper is, and that enters into this inverter circuit, which is the device that you see here is what you get down at Radio Shack that you plug into your 12-volt deal for running things from your automobile. It's 60 cycles at 120 volts. And the resistors there and those transistors you see, those happen to be very high voltage and amperage transistors, and you can see that they're on a heat shield type deal, which helps control them. And if you run it for any period of time, of course, it would probably overheat. So in order to get a practical unit which you can use over a long period of time, there's still some engineering to be done there, but the basic idea works. Yes?
What are the small knob-like devices on the lower picture?
Okay, down here. Okay, this is a system. I mentioned earlier that you could have individual coils sitting around that were tuned to a coil that was active, and that they will copy exactly what the other one is doing. Okay, well, in this particular case here, this is the one, the Tesla coil with your L1 and your L2, and it's the one that's hooked into the system, and it's the one that's active. Okay, the other three that you see there are simply tuned to that center L2 coil there, and they do exactly what the center one does. If the center one has like 30,000 volts on it, well, the other three will develop independently 30,000 volts, and they do not draw down on the power from the center one. It's the electrons are moving around, and the natural frequency of those coils, actually they have variable microcapacitors, high voltage microcapacitors on them, and they have also a variable resistor on it, so you can tune them individually. And how you know when they're tuned or when they're actually functioning, there's a little neon light that you get that's got one leg with a resistor, about a 47,000 volt resistor on it, and on one leg of the wire that's on this neon bulb, and then there's another leg there that just sort of sticks out like an antenna. And when this thing is functioning properly, well, that bulb lights up. So you know immediately when it...
Resistor in series with a neon bulb.
Can you use 1,000 ohm?
You said 47,000.
That I measured one of them, and that's what it came out. They didn't specify on the package.
That's pretty well standard for I think a 240 volt neon indicator.
Yeah, well, anyhow, the bulb lights up very brightly, and you have no trouble at all. It takes 70 watts, I think, to light the thing, something like that. I'm going to show you a thing in a little bit where you can order. As a matter of fact, it's the next slide. There's a company in Waldenboro, Maine, who manufactures a device which actually illustrates everything that we're talking about here with all the formulas and everything else, so that if you're interested in studying it, you can get this kit, and it's got the price on it, I think, there, and give you some ideas. It's not very large. It's a little bakelite tube that's about 2 inches or so in diameter, and that's what you've got here. And you've got a tuner deal on one of them, and the other one is already tuned. You've got a 1.5 volt battery, and the output it lights this neon 70 watt neon bulb. So if you have trouble, are uncomfortable with what's going on there, well, this actually illustrates your over unity. As a matter of fact, it was one of the first things that I knew about. If you want to see what was going on in 1893, here's some circuits here which are not at all different than what they would be today, except that you have better capacitors and other things. You notice there's not very many not very many parts there, and there's a tuning is built into these devices to a large extent. You notice on this particular one here, this is your L1 right here, and this is your L2 here, and you're actually tuning this thing by pushing the L1 backwards and forwards in there till it actually matches up with the tuning deal, and you've eliminated the possibility of having to put capacitors and a number of other things, because the capacitance is already built into the wire that's part of the coils. So you've simplified and you've taken out some stages there which would create a problem for you unless you just happen to have a lot of nice test instruments and you're able to match up your capacitors, resistors, and the characteristics of the particular coils so that you end up getting what you want. Okay, that's your number one drawing. Number two drawing there is showing the capacitors combined with the output thing, and the top one there is set up so that you can run a conventional transformer directly. And if the frequency of the coil is something other than what you want, on that number two, just slightly above where the number two thing is there, you can put a resistor or a capacitor in parallel across that particular coil there, and you can bring the frequency down to where it will match your transformer. Okay, the bottom number two there is showing how to light light bulbs, conventional incandescent light bulbs. How's that? Have you ever wondered how to light conventional light bulbs? You can light fluorescent bulbs fairly easy. You don't even have to plug them in. You can just hold them in the general area where this thing is activated, and their fluorescent bulbs will light up. But light incandescent bulbs gets to be a real problem. And the thing there that makes that possible is the capacitor, and we're going to substitute that capacitor with a capacitor bank in a little bit that has in the megajoule ranges. And at that point, well, we're off running, and we can produce any amount of energy, useful energy that you can imagine.
What's he doing on figure 2 up there at the top?
The top figure 2? The tall thing that's kind of in between there, that's a capacitor or a capacitor bank. See, these are actually Tesla's drawings. You're looking at something that Tesla himself actually drew.
What is the spark gap for?
The spark gap is actually control the level of energy that's passing through there. You can do it without the spark gap. I'm going to show you some fancy spark gaps in a little bit that can be used in real high commercial type spark gaps. Okay, come down to number 3 there. That is a device which I built a model of and demonstrated last year. And what it amounts to is that you've got a transformer, you've got your L1 coil, and you've got 2 L2 coils there, and the base of both L2 coils are hooked together, and a ground actually comes off of this thing, and you put a timing device on that ground there so that these 2 coils are activated for 60 cycles. And one of them is wound reverse winding, and this basically what it does on part of the cycle, when you got your conventional cycling, doing this sort of thing, well, one of these coils takes it up like that, and then the other takes over and takes it down like that. So you get your conventional sine wave deal at 60 cycles directly from a Tesla coil from base 1. And where you go to from there, depending on the amps that you want to be bothered with, you use a very heavy wire, maybe a size 4 or something like that, or maybe even size 2 or 0 or something like that, and you make these things quite large and heavy, and then you make your L1 coil out of rather heavy stuff also, and the net result is when you pump the capacitor bank with this, you've got so many amps that you have trouble controlling them.
This operates 60 cycles per second with no iron?
Well, remember now I said that on the grounding wire, that center one that's in the middle there, it has to go to an earth ground, and you have to put a timing deal on that earth ground, which will cause the two coils that you see there to actually, you have to do it 120 cycles, because 60 cycles up and 60 down, and the net result is that adds up to 120 cycles, and you come out with the actual full cycle is 60 cycles.
Question.
Yeah.
The device shown in 3, that's a two-dimensional drawing. What is the upper half of that? Is that a toroid? Are those toroidal?
Well, those are wound somewhat. You see the layers of wire going across it. It's not a true toroid. Exactly how to describe it, it's layers of windings on top of layers of winding. On a true toroid, you've got it...
right, but I noticed that he's got the representation of coil both above and below.
Yeah, well, what you've done, you've sliced through the center of it. You're looking at like a piece of cake, looking at the inside of a cake or something.
So that is actually a two-part coil.
Yeah, it's round coming out this way, and it's round going back that way, and it's got a round L1 that's being pushed in and out of the center there, which is tuning it in the same time.
A C-shaped coil, two C-shaped coils. In other words, coils like this, the windings here, and all the way around again, and then you've got the thing just...
No, the winding is, in each case, it's winding and it's coming across, and then it's going back and coming across, and it's layers on top of layers.
Right, I'm just wondering what the things above the L2 coil there are, because he's showing a representation of 12 volts.
Yeah, but see, this same wire that you see right here is the same wire that's up here. It just went around the thing. Okay, we go to number 4 there, and it shows another circuit for lighting light bulbs. And we go to number 5, and what you see there, basically, you know that Tesla had this thing rigged up where he could walk around the room with light bulbs, and they would light up. And you have grounding plates on each side of the room. And you have this high voltage generator here, which is running this capacitor deal, which in turn has got a step up into your conventional Tesla coil-like arrangement. These coils are actually not the way you see them. They're wound around each other. And of course that's going on, and that's causing the flux lines in the room to be so heavy that the light bulbs are lighting up without being plugged in. Okay, well, this immediately will tell you something interesting. If a generator can do this, and this is your Tesla coil here, then a generator and an electric motor are really basically the same thing. It's just a slight difference in the way they're put together. So if you can generate electricity and put it into something like this, then you can reverse that situation and you can run an electric motor. So this same circuit here, if you do the right things with it, will run your electric motor for you. Okay, I'm going to show you a different kind of spark gaps. Okay, I'm trying to get it to where you can see the whole thing, where you can see the dimensions. And those balls that you see in there are carbon balls, and the reason for that is that they don't evaporate like your metal ones do. They have a much higher capacity for electrical current and other types of things. So you'll see that there's all kinds of adjustments on these. For example, by screwing these, you can change the length on it. And on this one here, where you have the 3-deal, one of these is a ground. One of those 3, it would be an overflow ground, or one that would control the level of current, say that you have a great deal more voltage and current coming through there than you want to go forward. By adjusting those things, you can adjust it to the level which you want to go forward. And the size on these things is not particularly large. You'll see in inches down here the description of them. These are actually smaller than the other one. The first one I showed you there was about 9 inches long. So it was quite a bit larger than these. The top one there, you can use these with your Tesla coils also. Any questions on these? You see, these are made to go up to about 370,000 kV, and that is way beyond what you need to get a megajoule or a megawatt. You could almost go into the hundreds of thousands of megawatts with something like this. Since magnetic flux and electrical flux are part of the same coin, it's real easy to measure the magnetic flux with the relatively cheap instruments, hand-sized calculator size deal. You can measure the magnetic flux and you can convert that directly into voltage, and some of those meters that read the magnetic flux actually read in voltage. So if you're, say, 10 feet away and you're reading, say, 200 equivalent magnetic flux of, say, 200 volts at that point, then you have to square the 10, which would be 100, and 100 times your whatever, and then you see immediately that source had a rather large amount of voltage. You didn't get close to it, you didn't get shocked, and yet you got an accurate reading on it, close enough for whatever you need. So it would be recommended that these high voltage devices that we see there are more of a nuisance than a help, and they're terribly expensive. That meter deal that we're looking at there is $7,000, and the voltage divider things can run up to over $100,000 real quick like, and you can do the same thing with a $35 magnetic flux meter that's got a chart, it's calibrated in volts on the front of it, and by knowing the distance that you are from the source and squaring that times your reading, you can read the voltage direct without even getting close to the device. Because it's a two-sided coin. If you have magnetic flux, you have electrical flux, and they're both exactly related to each other. You don't have more of one than you do of the other. It's this exact copy. This is the one which I showed you earlier that had the yellow L3 coil on it, that had the real nice looking metal coil that was real shiny looking. So this is the one that you key on to and kind of give you an idea as to what some of these things do there. Of course, here's your gel cell battery. Here's a diode that you put on your plus side so that you don't get a kickback. If you get a kickback, it damages your high voltage module. The high voltage module is a laser high voltage source like you'd have in your laser printer or whatever. They're available off the shelf, and if you buy them direct, they're a couple $100 or $300 maybe or something like that. If you're lucky enough to find one in a electronic surplus place, it might be as low as $50 or maybe even lower. So needless to say, I've got pretty good at finding the surplus ones. I burned a lot of them up figuring out how to get things done, and this diode here was one thing that pretty well saves me. It prevents kickback, which destroys your high voltage laser module. It's on your plus side outlet of the battery. It does something else very interesting also. The wire, if the wire here and here is a component of the frequency, which your 6 is there, it loads up like a coil, and the current goes towards the battery. the electrons are trying to go that way, and the current is going the opposite direction, which goes to the gel cell. And what is it that charges your battery? Is current. So it turns out that through accident or otherwise, this may not be true of all kinds of batteries, but I know in the case where I have been using the battery for more than a year, and it hasn't changed one bit consistently over a period of a year. So that's a pretty good indication that something is going on there which doesn't match up. And basically what it amounts to, yeah.
I was just curious, you mentioned earlier that inverter is, the output of that inverter is fed by the output of that 6A coil up there going to the bridge. And you said that load reduces the output.
Well, what's happened there is that this 6A is detuned so that even though there's a tremendous amount of magnetic flux going on the busy end of the coil there, this 6A is detuned in such a way that it doesn't permit all the power to come through. If all the power was coming through, it would vaporize everything that's downstream from it.
Okay, but then it brings it down to some voltage that can drive that inverter.
Yeah, you've got voltage dividers. This is a frequency adjust deal here that if you need it, you may not need it. It depends on the input to the diode bridge. The diodes which I use are high voltage radio frequency diodes which show up in your television sets and things like that. And they start at about 25,000 volts and go up. And 100,000 is not uncommon. So you've got, say, 4 of them there at 25,000 volts in the system, and they're radio frequency, and they'll operate very well, say, at 2 megahertz or 4 megahertz or whatever. The particular ones that I've used are 200 nanoseconds, which that would be roughly about 4 or 5 megahertz, or if anyone correct me on that?
5 megahertz is 200 nanoseconds.
It'd be about 5 megahertz. So that's high enough in your radio frequency so that if you multiply 5 million times your output there, you can see real quickly that if your output was even low, like a few volts and partial amps, that all of a sudden you've got something that's much more potent than what it would seem to be.
What size of resistors do you use for a voltage divider?
Okay, you'll have to determine those experimentally, and again, as we were talking earlier with some of the people, resistors are not necessarily resistors. If you use your LCR meter, you'll find that almost 100% of your resistors have capacitance and inductance. And a lot of times they're much more better inductor or capacitor than they are resistor. In this particular case, the deals which I use here are 220 ohms. They're 1% accuracy and that sort of thing. And it turns out at 220 ohms, they've got about 30 microfarads each. And they've got some other characteristics which change it, but it turns out that, and also these transistors here have capacitance and inductance too. So if you're trying to balance up your impedance on something like this, you can be balancing all day long and a lot longer than that and still not get anything. You've shot yourself out of the water unless you just happen to look into it, and it gets to be very skillful. Now, the way you get around that is that there are capacitors and inductors and resistors that are actually just that and nothing else. And if you go to your electronic supply and try to buy one, you get very interesting response. I can tell you, because most of them, even though they've been in business for 50 years, won't know that. Say again?
There's some place to start with the value of those resistors, like the number 11s?
On the dividers, these voltage dividers here, well, what those are doing are correcting the voltage so that when you get downstream, you've got what you need for downstream. You notice there's one on the plus side and one on the minus side. And there's also capacitor in here to take the ripple out, because when you come through that diode bridge, you've got rippling DC. And how many volts are you dealing with when it comes out? Well, down here at this point you're at 60 cycles and 120 volts.
Before that, back up to that capacitor.
Going backwards? Okay, well, you have to allow for some degrading, but when it reaches this deal here, the basic deal here is the inverter that you buy down at Radio Shack, which you plug in your automobile cigarette lighter, and you get from 12 volts DC, you get whatever. Now, what I've basically done is tapped out of it and tapped onto this system and put those dividers in there so that everything is adjusted to what you want to have coming out at you.
With a small battery there, input, how much output can you get out of that?
This particular one here is about, I think it was about 12 amps and about 120 volts.
And how much is it?
You could get a much larger amount. You could get, you can probably get 30,000 watts or more out of it.
How much input, though? How much?
The input, that's a 12-volt gel cell. So it's doing things which, unless you know what's going on there, can't be done.
So it's going to be determined by the grid, which is your power supply, but it's going to want to sink a certain amount of power in that source.
There's a lot of things happening there, and you would have to have seen a speech I gave last year, or the book, which has got the details in it, which would explain that.
This is something anybody could build?
Well, anybody should be able to build it, but it doesn't always work out that way. There's not very many pieces there, and the source of those pieces is not very complicated. The only thing on there that would create much of a problem would be that number 3. The rest of it you can get down at Ace Hardware or your local lumber company or Radio Shack. Yes.
So theoretically, you can take the output of that transformer, run it through a 12-volt converter, and plug it back in and replace that battery?
Yeah, we can start all over again. You can put these things in stages and do all kinds of things, but you can actually have a much higher output than this. You can have up to, say, 30 kV from this particular device.
What kind of wire did you use for the L2 or the L1, 2, and 3 on this one?
Okay, the number 7 there is from Barker Williamson's in Pennsylvania. They make professional coil makers, and they were the ones that made the real pretty silver coil that was one of those earlier ones.
Okay.
And they make them up to 6 inches in diameter and normally about 10 inches long, but you can get them in greater lengths. The larger ones run into like $250 or more each, plus $50 setup charge. The smaller ones, like the one I was using, was about I think maybe $40, $50 plus the setup charge. You don't have to use those. You can build your own, though.
What kind of wire did you use for the L1 and L2?
Well, the other windings that you saw on there was basically a 750-volt multi-stranded wire like you would find down at the hardware store with a 750-volt rating. So between the two of them, that would be 1,500 volts. So as long as you keep the division there so that only 1,000 volts is on each turn, even though at the top you may have 100,000 volts, but the difference between the two of them is, say, 1,000 volts or less. The one that's next to it and that one, say, is 100,000. This one would be 99,000, and this would be 100,000. Well, you're okay. Okay, some more questions?
And you spark gap on number 5. You mentioned mill thickness of paper.
I think it was .0025 or something like that, wasn't it? I think it's written on the. See, number 5 there. I can't hear everything you're saying.
Can that run continuously?
Oh yeah, there's no moving parts there to wear out.
And you're not dissipating power anywhere in substantial quantity. The only thing I'd be concerned with would be 11 and 14.
Those voltage dividers, that's going to be tricky because, like I was saying a while ago, the resistors aren't necessarily just resistors.
Yeah, but given the assumption that you have indeed used pure resistance in those locations, dealing with the wattages that you're
in the particular instance that's going on here, we have to look out for about, let's say we got, did I say 20 amps or 8 amps or what?
I said about 15 amps or so.
Okay, well 15 times 100 would be about 15, that'd be 1,500, wouldn't it? Watts.
1,500 watts of energy.
Okay, so that means that on the resistors there, between the two of them, you have to have some way of containing that. So you have to work out the technical problem on that. Now, for the short period of time that I've ran the thing, I haven't, ran it over an extended period of time, just long enough to get a reading on it. Well, it works fairly well. I'm using very fancy resistors, though. They're the aluminum ones that are gold-plated with fins on them, and they're 1% accuracy and all that sort of thing. And they typically, you can get them up to about 500 watts or more, and they do cost a bundle. So.
Well, if you kept 14 low and you kept, I noticed you got two of them marked 11, one on the left and one on the right.
Well, there's two number 11s and two number 14s.
But it wouldn't necessarily mean that the two number 11s are identical in value, nor the two 14s.
Not necessarily so. What you do, you position them so that by taking off in between them, you've divided the voltage, and part of that goes on, and only the part that you really want to keep goes off.
Yeah, and then at this point, the emitter collector breakdown voltages of your T transistors become
well, these particular ones here these particular transistors are good to 2,500 volts. They're TO3s.
So you're using flyback type transistors.
Yeah, they're unusual, quite unusual. As a matter of fact, you'll spend quite some time trying to figure out where to find them at.
Numbers?
Well, they're Motorola, and I do have some numbers, but I don't know whether I've got them with me or not. And with that in mind, there's some other things I need to show you. There is one book which has your timing constants and a lot of other things, and it's the Sam's
Handbook of Electronic Cable.
Yes, it's the Sam's book, and Radio Shack used to sell it. Bookstop has copies of it, and it has your basic, all of your basic circuits and other types of things which you need in order to proceed.
Could you just look in front of that and read the ISBN number out?
Surely.
For us?
Okay, let's see. The ISBN number on this particular book should be right here. Oh, the darn.
Yeah, on the back label. I think it's got to be on the copyright page.
Well, I'm looking at the
Probably
name.
really small, so I can look at it.
Okay, I've got it here. Okay, the International Standard Book number is 0-672-22469-0. And with that in mind, you should be able to get the identical exact book. Now, there's some other books which are quite interesting, and it turns out you would think that there would be all kinds of books on resistors. There's really only two that are in print, and I've got about a half a dozen or more at home that are out of print. But this is one of the ones that's still in print. It's $27, and you'll have a terrible time explaining to the book people what it is you want, because they'll be looking right at the name and the number and everything, and I'll give you an ISBN number on that also. It is somewhat, as far as high voltage capacitors, it's not particularly helpful, but it has a lot of other things in there that are. The ISBN number on that is, let's see, I had it a moment ago, 0-442-01-558-5. those are kind of shear zones where the electrons are being disturbed. So anytime you disturb an electron, when you push it forward, it gives off a magnetic impulse, and when it pops back to where it was, it gives off electrical impulse. And this can go on forever and ever, and that electron is not diminished in any way.
Acceleration or deceleration of the electron causes radiation.
Yeah, when you disturb the electron, you're causing electricity. In a conventional system, you've got your coils and magnets whizzing by each other, and that's disturbing the electrons, and that's where your electricity is coming from.
Is there a particular frequency that seems to be best for coupling with that kind of energy?
Not really. The frequencies which conventional generation is set at are horribly wasteful and very, very inefficient. And I don't know whether that was intentional or otherwise, but if they intended to do it wrong, they succeeded.
Yes. Given the source that we believe we're tapping here, using a tickler, basically.
Yeah, they're just everywhere in large.
Mechanism so that 6A can couple into that energy.
You know, you're basically disturbing the electrons, and the magnetic flux lines are greatest up around 6A there, and so basically none of the electricity from the battery has ever passed through any of those coils. It's just by magnetic flux has transferred and caused the other coils to react in proportion to the amount of magnetic flux that's there.
Do some calculations on what kind of energy or what kind of frequency might be the best.
Well, actually, once you get the magnetic flux going, you can have coils that are not tuned to it that are in that magnetic flux, and they will oscillate at the resonant frequency that they're meant to resonate at.
Yeah,
so you can go from one frequency to another and still have your electricity there, because actually the electrons are not going through your system. They're just being disturbed by the magnetic flux lines of another electrical system, and that goes back to those power triangles we were talking about, where you can use a smaller power triangle to excite, let's say, a larger one. In your L1, your number 6 there is, say, the small power triangle, and your number 7 is your L2, which would be a larger power triangle, and that's just like in an atomic bomb we were talking about, where you use a small explosion to make a larger explosion, which makes a larger explosion. So that is, if you want to call it, is over unity, because really basically anything that's above ambient is over unity.
Factor there.
Yeah, well, it's squaring according to the law of squares, and you see that in Fibonacci series. You see it in all kinds of interesting things, like in human development, from one little cell and it splits to 2, and then 2 becomes 4, and 4 becomes 16. And by the time you've done this several times, you're to a million of whatever you start out with.
You might be able to look at the prime number series.
Yeah, well, your flux units will become so many of them that you can't believe it. And once those flux units are going, then you can transfer this over to another power source, and it won't diminish the one that's running. The one that's running will just maintain itself, but it will cause the other power deal to activate.
But we are under the assumption, Don, that we are tapping into an energy source here.
Yeah, well, that's the whole story, is the fact that the electrons, when you bother them, they give you useful energy, and it's beyond ambient, and therefore the snowball, you've carried the snow up to the top of the hill, the little snowball, and you've turned loose of it, and it's rolling down to the bottom of the hill, and it's getting bigger and rolling faster as it goes.
Do you anticipate dedicating much time to the mechanics of the coupling? I mean, the actual, I should say, the theory of the coupling.
It's best to think about that after you've got one up and running. The trick is to get one that's up and running and behaving according to what a Tesla coil is supposed to do, and forget about all these other things or where you're headed. Just get the darn thing going.
And worry about the miles per gallon.
Yeah, once you get that part done, well, then you can start worrying about other things that you might need to do in order to make it useful. Otherwise, you never get there. You get hung up on some problem along the way, and chances are you have a fair chance of getting there the first time if you're lucky.
Excuse me, does this relate to what I've been reading about standing waves in the Earth?
Standing waves, well, the Earth has its own, cycling, has its own resonant frequencies, and as a matter of fact, one of the offshoot inventions on this thing, you know how your MIR works, where you can take pictures of inside people without cutting them up? Well, you have a very large magnet that's coming off and on, and then it's disturbing the hydrogen molecules. And when they spin out of position and when they spin back, they give off an impulse, and you're photographing that impulse. Well, it turns out that the Earth is a very large magnet, and it's pulsing off and on. And with a simple coil of wire, you can do the same thing with the Earth that you do with the MIR. And you can see the rock formations, you can see the tops and bottoms of them, you can tell whether there's fluid in it and what kind of fluid's in it.
Actual devices exist?
It exists.
Yeah, in fact, Tesla had calculated the Earth's resonant frequencies fairly closely. They found out that they were slightly different.
Well, actually, they're quite a bit more than what Tesla did, and I'll tell you how you know this and why. It turns out that the Van Allen radiation belts are one side of a big capacitor, and the surface of the Earth is the other side of that big capacitor. So the Van Allen radiation belts are, the oscillation there is, say, between 2,000 and 8,000 cycles per second. It varies depending on the time of day and a number of other things. So the surface of the Earth starts out at whatever frequency the radiation belts are running at, and it goes down from that. As it goes inside the Earth, the capacitance picks up, and that slows the frequency down, so that by tuning in on these different frequencies as you go down, you listen to the noise level, and that tells you what depth you're at. You get into building the Tesla coils proper, basically what you're doing, you're energizing a smaller coil, which is your L1 coil, and causing a larger coil, which is your L2 coil, to react. And it's the exact same system there, except that it's put into a more compact and convenient system. Now, normally the L2 coil would be some distance, maybe 3 times the diameter of the L1 coil would be 3 times the diameter of the L2, but that's not really necessary. It can be smaller than. Now, one of the problems that people run into in building these things is getting the 2 coils to react with each other. You've got to have them so that they can talk to each other. So if you use like quarter wave system, your shortest wave will be the longest length of wire, and your shortest length of wire will be your higher frequency. So with that in mind, one of the problems that people run into immediately is tuning those things. Now, I'm going to show you in a little bit a slide that shows this exact same thing from 1893. It was one of the in the early radio devices, how they were able to tune them fairly easily. So this is your L1 coil, L2 coil, and the way we're going to do this is PVC, and I cut a collar here so that I could slide it on there and use it for a spacer, and put another one there as a spacer, and the net result is that this thing fits almost perfectly. It slides in and out of this particular coil here. Now, this is one way to tune these things without having to figure all of the other characteristics that have to go into it, which gets pretty complicated sometimes, and especially because resistors, although you think resistors are resistors, if you take your LCR meter and you measure the capacitance and the inductance of almost any resistor you're going to run into, you'll find out that the resistor is a lot better capacitor and a lot better inductor than it is a resistor. And those things vary considerably from one resistor to another, and the only way you can get around that is get non-inductive, non-capacitance resistors. And I can tell you, if you go to people who have been manufacturing resistors for 50 years, they won't know what you're talking about. You will have to find the sources pretty much on your own. They do exist. Radio Shack has a few non-inductive and non-capacitance resistors. Very few, though. and they're marked. So don't expect to walk into Radio Shack and tell them that that's what you want, because the people that work there won't know what you're talking about. But if you look on the packages, you'll see that there's a little square box, ceramic box looking deal that says on the top of the package that it's a non-inductive resistor. Now, if you're trying to tune these things by changing the resistance or the capacitance and you're adding these things in, you get into a situation where every time you get one thing corrected, you've got something else out of balance. And the net result is it doesn't work very well. Now, last year, a lot of people have tried to build the circuits which I presented last year, and several hundred people that I know of that have tried to do it. There's only about 6 out of all of those that were able to actually get it done. And I'm not quite sure how they were able to do it. Some of them I know the details and some I don't. But using this particular system here, you can correct for a lot of things that otherwise you're going to need an engineering degree to figure out probably. So this will simply go to your high voltage source. Okay, if you want to build a nice coil, Barker Williams makes a large variety of these coils ready-made. And they're copper, and they've been dipped in stannous chloride, which tin plates them, and that's how you get the pretty tin plate. They've used a heat process to embed them in Lexan slits of Lexan, and that's what the ribs are made out of. Now, if you want to make a real pretty Tesla coil, this happens to be the cap off of a sewer pipe. And they come in all sizes from about a couple of inch and a half up to over 25 inches. And if you look at it this way and you see this square thing on the bottom, the square thing on the bottom you can screw onto a piece of board or something very nicely, and you can wind your L1 coil very nicely. See the grooves on it? And it will stay exactly where you put it. And you can use some little clear ties and run a hole or two through it where you can run your ties through it, and all of a sudden you've got your very nice L1 coil, see? And this being a PVC, you can further take a piece of PVC pipe that's been cut to the proper length, and you can set that thing on it just like that. You can use PVC glue if you want to and glue these two pieces together, and then you can take your center coil here minus the orange one in this particular case, and you've got a very nice Tesla coil, almost ready-made. Okay, if you want to get into amps and other sorts of things, then we have to start using larger wires. And it's the flux lines that are reacting with these particular coils, the magnetic flux lines that are transferring the energy from one energy triangle to another. And if you get into heavy amperage and that sort of thing, this is welding cable, and it comes in all sizes. This happens to be number 8 welding cable, and it will make a very nice high amperage type coil for your L2, and then you can use even larger or copper tubing for your L1 coil. Okay, since we know electrons are a source of electrical energy, electrons do a lot of things. We get a lot of different types of energy from electrons, and I'm not sure whether you can see that or not. Yeah, dim those lights some if you can. Is that better?
Getting better.
You're getting better? Oh. Can you see it?
Yeah, now.
Okay, it turns out that electrons provide us with a lot of things besides, say, electricity. And this is sort of a brief breakdown on it, and there's probably other types of things that they provide us with also. But and the systems of storage there, for example, your capacitors would store the electricity, and your coils or your inductors would store the magnetic field. And you've got equal amount of each. Anytime you have electricity, it's a two-sided coin. You have equal amounts of each. There's no way around it, because when the electron moves forward or is disturbed, it's going to give off magnetic energy. When it pops back to where it was, it's going to give off electrical impulse. So you're going to see both of those. Yeah, I have a number of other slides, so we'll need to look at them. Okay, you're familiar with the power triangle and how that works. For example, here, the power triangle system 1 there is your L1 coil, and your L2 coil would be the power system 2. Now, the electrons are not moving from number 1 to number 2. As you noticed a while ago, the L1 coil is covered over with plastic, and that's just fine, because we don't want any of the electricity to be jumping around or sparking or moving. It's the magnetic flux lines that we're interested in. So in case of conventional energy, we've got atoms A and B there, and A would be your volts times amps. That's what's inside the wall before you turn the switch on. When you ground it, then you've got time which comes into it, which would be your volts times amps times time, which you've got watts or useful energy at that point. That's the conventional way of doing electricity. Now, on C there, we have resonant energy, which is not actually going anywhere or doing anything, except that it's resonating, and in the process of resonating, it's creating lines of magnetic flux. And your electrical people will tell you that number C there is wattless energy or useless energy. What they're not allowing for is the fact that at resonance you have a tremendous intensity of magnetic flux lines, which will transfer beautifully over to another electrical system. And that's what's happening between your L1 and your L2 coils. Now, once you get your L2 coil going, it's going to be moving from the base of the coil towards the top of the coil. As the magnetic flux starts building on each turn there, it's transferring over to the next turn, and it's carrying with it what it had, and it's multiplying by the number of by the flux lines that are being active there. So you're getting an amplification of the magnetic flux lines. These magnetic flux lines are building in intensity as they go towards the top of the coil, and they reach their maximum at or near the top of the coil. Now, at that point, you've got high voltage with not a lot of amps, but the amp business is not going to be a problem for us, because we're not going to be using the system that we have at the top there. We're only going to be using the lines of magnetic flux. And in a system which I'm going to show you in a little bit, there's a Tesla's third coil which comes into play, and it acts like the little receiver that did the light bulb thing that I showed you earlier, and it is situated in the highest density of magnetic flux, which means that it's reacting like a power system 3 there, and it's got the benefit of the resonant energy that's been amplified to a very high level. So at that point, what's transferred over into it becomes an entire separate electrical system. None of the electrons have ever actually gone from the L1 to the L2 to the L3. It's the magnetic flux which is reacting with the different coil systems, which is powering the next stage on, or the next layer of turns as you go towards the top of the Tesla coil. Now at this point, you're free of the power system that was present at the beginning of your experiment. And you've got a whole new power system with a whole new bunch of lines of magnetic flux which did not exist previously, and therefore you have gained in energy potential. And your potential at that point, you have a lot more energy than you ever had when you first started out. Now, if we look at the law of squares and the Fibonacci series and other things in nature, for example, if we take the beginning of a human being, we have one cell and then we have 2 cells, then the 2 turn to 4 and 4 turns to 16, and after that has happened a few number of times there, you've got 1 million things going for what you had initially just one of. And the same thing is true in the case of flux lines. And the flux lines are actually what will give you your energy back, because they translate back into the energy system as electricity. So we will get you some more overhead things in just a moment here, and see how things go from here. Okay? They don't necessarily have to be very close at all. For example, if you have a resonant system, of course the flux lines are determined by the square of the distance from the source, so they're diminishing in value as you move away from the device. So it's probably better if they're within a relatively short space if you want to benefit 100% from the flux lines that are there. However, with a resonant system, the flux lines will give you your energy that's totally separate. See, none of the electrons from the original system are actually present in the second or third system. So if someone tells you that what you get out depends on what you put into it, once you've generated those flux lines, well, you're into a different language system which will translate back into electrical energy, and since you have a lot more of the flux lines, you have a lot more potential than you had to begin with. So this law of square business, you see it. Here's a drawing showing what happens with the lines of magnetic lines whenever you start getting additional ones. And it goes to millions in just a very short period of time. When that thing flips over very few times, it's into the millions of flux lines. And at that point, you can disturb an awful lot of electrons. And that's what it's all about. Your magnetic flux lines will translate into electrical flux lines and that sort of thing. And then if you've got your coil system where your henries and capacitance and that sort of thing are all working for you, and you know how to hook into it, well, then you've got a lot more energy than you started out with. And there's no doubt that it works. There's all kinds of evidence for it. Okay, getting into the formula for finding what type of useful energy is available to you through this system. This will give you a little bit of an idea. And Joule was a English brewmaster who had all kinds of machinery that ran on steam and some electrical and this and that, and he had to come up with a system which would make translating one system of energy to another more universal. So that's how he comes into this. A joule is 1 volt times 1 amp times 1 second, which is a watt second. That also happens to be the definition of a coulomb and a whole slew of other things. So anyhow, these things all translate in and out of each other, and Joule was the one that came up with the system, and that's where we got the name Joule. So, okay, let's see what that can do for us in the case of a Tesla coil. Say that we have a Tesla coil that is running at 100,000 volts. Well, you might say, well, we're not going to get a megawatt out of something like that. But what happens is it's the cycles per second that come in on that. See, you remember a watt was 1 volt times 1 amp times 1 second. So if this thing repeats itself many times per second, then you have automatically got a lot more than 1 watt there. So this explains how 100,000 volts can become a lot more energy than, say, 100,000 volts. And what you have to do in order to collect this energy is that you have to have capacitor banks to collect it for you and store it temporarily in order to get on to the next stage. Because if it's not in a useful form, it doesn't really mean anything. Okay, you notice on this that we're going from 100,000 volts to into the hundreds of megawatts. And of course, the system has to be built to contain or to operate safely at whatever level it's operating at. But if you've got proper construction for 100,000 volts, you can pump forward many megawatts of energy. Now, I might say that Hoover Dam is approximately 500 megawatts, and I'm showing here that you can approximate Hoover Dam with a unit which will sit on your coffee table. And this hasn't been actually done yet. I've done it in at a certain level, and I know that it will probably work at that level. And I'm in the process of building a larger units with the welding table that goes up to about a size 2 or even a 0. And the way you do that, you use some of the technology. If you were going to build yourself your own welding machine, some of the mechanics that are involved in building a welding machine are also involved in building one of these things that will have very high amperage. I'm going to show you some devices in a little bit that they're related to this that have many thousands of amps, plus say 1,000,000 volts at 3,000 or 4,000 amps or something like that. So how many megawatts is that? Okay, I'll let you look just momentarily at some of the benefits of this particular system. And while you're looking at that, I'll get some more things for you. Is it okay to go ahead? Anyhow, this is in one of the books. Okay. Thought you might like to see what some of these systems look like. The one that you see there on your right, that's a 12-inch PVC sewer pipe. The top piece is about 16 inches long, and the bottom piece is an exact duplicate of the top piece. The center device there is a rubber-made oil barrel dolly with the rollers taken off of it, and it turned out to be 25 inches in diameter, and it worked out just fine for the L1 coil. And below you see a power system. I'm going to center it now so you can see that power system a little bit closer. What you're looking at here is an automobile ignition coil. And what you're looking at there is where the 12-volt electricity comes in on that connector block. Basically, I've used a timing circuit which is very common. You take a capacitor with a resistor shunt across the legs of the electrolytic capacitor, and you run electricity through it. You're going to end up with a timing deal. It's going to be cutting it off and on. So it's the resistance times the capacitance of the capacitor that tells you how many times per second this particular ignition coil is coming off and on. Since it's an automobile ignition coil, it runs at 12 volts. The timing system is set up to match the timing system which it normally accepts. If you have an 8-cylinder automobile and you have 2,000 RPM on the automobile, and that'd be 8 times 2,000 would give you your number of times per second this thing is going off and on. So, and also your automobile ignition coil is made to last for about 40,000 hours in some cases. So it has a longevity. It uses a common energy source. You don't need a complicated device to turn the 12 volts off and on, and you're off running. So I might say that the large coil, which we were looking at there, I tried to use the computer programs. There's 2 of them that are available through the bookstore here. In most cases they work real well, and try to use that on the larger coil, and it didn't quite turn out the way that the program said, but that's neither here nor there. It's a good guide to what you might expect out of your coils. Okay, the 3-coil system that you see is the center one here is the one that's powering it, and you have your L1 coil and your L2 coil. You have a high voltage system, and you have 3 coils that are around it there that are tuned to the same frequency. And remember the little model that I showed you at the beginning there? Well, actually this is duplicating that sort of thing. The center coil is putting out about 30,000 volts, and so that means that each of those 3 on the outside there are doing the same thing. So you connect those up just like they were batteries or such, and you end up with about over 100,000 volts real quick like. Say again, please. No, they're that whole board that you see there is about 14 inches square. So, and it happens that the coils that you see there are actually about 1.5 inches in diameter and about 4 or 5 inches long. So that will give you a perspective on the size of it. This thing was made to demonstrate over unity. Since people are real skeptical about over unity, well, this is intended to really mess them up. Okay, the device, this is, most of these things are in the book, in the bookstore, and the device which you're looking at now is this particular device here. And basically what you have your 12-volt battery. You have a diode which serves to protect the laser module from a kickback. This is a high-voltage laser module, and you have a capacitor that's in parallel there, and then it goes into your L1 coil and then comes back. There's a spark gap which helps control the energy level that's passing. The spacing on the spark gap there will control the energy level of the energy that's going into your L1 coil. Then, of course, number 7 is your L2 coil, and number 6A up there is Tesla's 3rd coil. And I'm going to show you something from 1893. that relates very closely to what we're doing here. These are useful circuits which I gathered up out of one of the Tesla publications, and if you notice, number 1 there is showing that tuning circuit which I showed you early on, where we slide the L1 coil inside the L2 coil, and you know when you've got it tuned because you start getting sparks. Okay, we go to drawing number 2 there. If you've ever wanted to know how Tesla lit incandescent light bulbs and how he powered transformers to run motors and do other sorts of things, you have the basic circuits for doing that. This particular case, the Tesla coil is built laying on its side, and the L1 coil is in the center of it, and it moves in and out. On the, you notice the up and down thing. This is a capacitor or a bank of capacitors. And whatever energy level you need, that's the temporary storage there that gets the amount of electricity that you need in order to do the particular job that you're intending to later on. Then we go to drawing number 3 there. The coil on your right is wound in one direction. The coil on your left is wound in another direction, and the L1 coil is run in and out. The layers of the windings, if you could see them, there's layers and layers of windings here on top of each other. Instead of having an extended coil, they're wound in more compact. And the L1 coil is moved in and out there so that you get it tuned properly. And that center deal, if you put it on a timing circuit and ground it, you can get 60 cycles direct from this thing on the first go around without going through any other sort of transformer or anything else. So you can generate 60 cycle electricity direct with the Tesla coil. And number 4 is another illustration of how to light incandescent light bulbs. The trick is knowing what capacitance to use and a number of other things, but this is actually how it's done, and this was 1893. You're familiar with how Tesla was able to take light bulbs and globes and things and walk around the room and they would light up. Well, this bottom drawing, number 5, is how he did it. He put sheets of metal on the opposite ends and hooked those into his high voltage system, and was able to get enough intensity of the magnetic field so that he could walk around in a rather large space and these light bulbs would light up. Now, if you look at this drawing properly, you see that we have a generator there that's generating electricity that's going through a capacitor which is running an L1 coil, which is powering an L2 coil, which takes it to a higher level, and that L2 coil is in turn activating those 2 metal plates which cause the lights to go on. You can take that same circuit there and use it in a number of other ways. Okay, let's see. How's that for a spark gap? From top to bottom, it's 9 inches, to give you some idea. And this thing is made to run at in excess of 200,000 volts. And this is going to fit into something I'm going to show you next. And there's a thing called a Marx generator, which all the things which people think are not present in a Tesla coil suddenly become available. The deals here are that spark gap that we just saw. And when you take this spark gap and you put it with capacitors, just a few stages, and you're into hundreds of thousands of volts with thousands of amps. Okay, I show you some other kinds of spark gaps. These are commercially available, and the ones that you're seeing in the illustration there go to about 370,000 volts. And of course, they make them for much higher voltage. If you had a ruler on there, the top one up there is about, from one end to the other, is probably about 6 inches long. And you have to pressurize these things, and you put a gas inside them in order to keep them from burning up. It's a sulfur compound of some sort. It's a gaseous form of sulfur. And the balls are made out of carbon. And they're made to last for a long period of time. And these things are commercially available, just like the other ones I showed you. Okay, in conventional measurement of electricity or high voltage, you have to use voltage dividers in order to get your instruments to work for you. Now, as the voltage gets higher, these voltage dividers get quite large, and in this case, in order to use conventional measuring instruments, this thing is more than 9 feet tall, and it's good for about, it's less than 1 million volts. So that means that you can measure the million volts, up to 1 million volts with your regular measuring devices by using this divider in order to bring it down to where your instruments can work with you. Now that's not necessary at all. If you remember that for each line of electrical flux, we have a line of magnetic flux. Now it turns out that your EMI measuring instruments or your magnetic instruments which measure magnetic flux, some of them are actually calibrated in volts. So if you have an equal amount of magnetic as well as electrical, so you can use a magnetic detector in order to read the voltage indirectly. And the way this works, you have Coulomb's or Newton's inverse square law, and the square of the distance times the remote reading will tell you what the full reading would be. So that if you're say 100 feet away or something like that, and you're getting a reading maybe 10, and so you have to square 100 and then times 10, and first thing you know, well, you're reading 1 million volts, and you've got this little handheld gadget, and you didn't have to even go near the device that you were measuring the energy from. So from a safety standpoint and a cost standpoint, for about $35 you can get the a device that looks like a little handheld computer, and it reads directly in volts. So you square the distance times your remote reading, and you know what the voltage would be from the device that you're interested in. Okay, I'm going to walk you through the different parts on this. This is actual commercial model, and it's 30 kVA, and it's not very large. It's a little bit heavy because of the copper in the transformer. But the transformer is driven by an inverter, which is here, which runs off of 12 volts and kicks it up to 112 volts, and then in turn comes through a variable deal that's very similar to what you have on the light dimmer in your house, except that won't work in this case. It's a special dimmer that's made for a neon tube to work with neon tube transformers. And you can vary it from 1 volt to whatever you have, like 112 volts. So that means basically that the forward going part of it going into the, you have a couple of 200 amp diodes here, one on each side. There's one here and then there's one there. And in this particular case, the diodes are not critical. They're silicone, but they're good for several thousand volts and 200 amps.
I believe you're standing in front of the projector.
Is that what's wrong? Does that work better? Okay. It goes from these diodes, it becomes pulsating DC at this point, and one diode will give you a sawtooth pattern. The second one there kicks in when will kick in and cause the other one to kick out at a certain point, so you have a continuous pulsating DC on a straight line instead of a sawtooth type arrangement. That goes to these 30,000 volt capacitors that are there, and they're set up to take hundreds of amps, and they're lifetime capacitors. They're self-healing, and I'll show you in a little bit the reading on one end of it. This is the transformer, and it may be dark, but you can possibly see what's going on. Okay, the closest to you here is your inverter. In this case, it's about 240 watts. The inverter, it goes into a 15,000 volt neon tube transformer. The neon tube transformer on each end here is kicking out the same amount where those knobs are. There's one on each end. Each one goes to one of the diodes. Okay, and the earth ground on this is here. So this fulfills something which we are going to talk about after a little while. There are many ways to wind coils. You can wind them where you have voltage only, or where you have very little amperage, or where you have 100% amperage and very low voltage. And the way the coils are wound will determine what you get. It has nothing at all to do with the fact that what you're putting in is, say, strict voltage to begin with. It's going to come out after it goes through a certain type of coil system, and with this center ground thing here, you're guaranteed that you're going to get amperage. Okay, there'll be a break at 10:15, and you'll have to let me know when that time comes, because I won't be able to watch the clock from up here. Okay, there's a lot of these photographs, so we need to. Let's see, we saw this one just now, or have we seen this one yet? What we're going to do is walk around this commercial we're going to walk around the commercial model and look at it from different angles. And you see the 200 amp diodes sticking through these cooling fans, and you see the takeoff from those two going up to the capacitor. So it's going to be a lot simpler than the one you're looking at on the floor here. Okay, here's the same thing from a slightly different view. And below here you see a radio frequency high voltage probe that goes into a meter that measures high voltage at high frequencies. And I'm going to there's about 20 of these sheets, and then we'll go to some other things. You see those? Okay, we're going to take a look at one end of them now. And if you got your glasses on, you can gather a good bit of information from this. You notice the point of origin there is Finland. So that gives you some idea where those capacitors came from. They're self-healing, if you notice, and they're also have some other characteristics. It's got the kVA written on there, if you can read it. But the combined kVA of those two capacitors is about 30,000. And the fact that the device that your input is about 12 volts at maybe 30 milliamps or something like that. And that goes into the inverter, and the inverter is tuned back so that only a tiny bit of that is going forward. So whenever you come to the output, you basically sent forward maybe 2 or 3 volts, and you're getting back, say, 30,000 kVA. So the computer program that I like to use with this type of situation, it won't work with this one, but it will work with that one down there, and we'll talk about it a little bit. But I sit down and for days run computer programs on these things before I even start building them, and then I correct as I go along. I start taking readings as I go along, and then I start building corrections into the device. And we'll see that in some detail in a little bit. Okay, we're going to the one that's on the floor down in front of us. And let's see what happened here. There we go. See that okay? Okay, the parts of this particular device here, up to this point right here, is what you're already familiar with. Now, there's 2 or 3 things that are built into this which are new and different from what you might be thinking about. Here's the inverter again, a smaller sized one. Here's the variable device on the end. It's coming into a neon tube transformer, which is here. That neon tube transformer has 2 high voltage outputs. Those 2 things are brought over to here and underneath here, and they're joined together by a couple of diodes. So the high voltage output is going through this one right here and coming in at the base of the coil that's inside the spring there. And it's coming out at the top end and coming back this way and going to here. There's a lightning volt protector here that's serving the case of the spark gap. So there's not a spark gap as anything that you would recognize. Okay. Once you get over to this point here, 2 things have happened. One, I calculated the L1 coil, which is on this sliding 2-inch PVC tube inside the 3-inch coil. It was calculated to be 1/4 the length of the wire that's involved in this L2 coil or the outer coil. And the reason for that is that coils have both capacitance, inductance, and resistance. And all those things play part in the tuning of the thing. But since you started out with about 1/4 length of the longer coil, you're pretty much tuned. You're almost tuned immediately. And as it turned out, of course, you have to put a capacitor on one of the 2 coils. The easier one to work with is the L1 coil over here. And you can put a capacitor in there that will correct for any slight difference that might be. And those things are usually into the like 1/10 of a microfarad or something along that line. And as it turned out, when I put that thing in and then I took a reading on the circuit, well, it turned out that I had a 6,000 volt capacitor that I could put over here, and I had an exact tune on this thing, even though sliding this coil in and out is meant as a tuning device. I could have tuned it by doing that. As it turned out, the thing was exactly tuned without even moving the thing, by using the particular combination of capacitors that I used. Okay, with that in mind, the next thing is that in order to have useful energy, you can't go directly from this coil system and use it. You have to have some way of storing it, and the storing options are basically either battery or capacitors. And as it turns out, capacitors are, we'll come back to that later, capacitors are probably the best option because they can be built to where they're self-healing, they can be built to where they have over 40 years of useful life that's known. They've tested some of them and they know that they will last 40 years without any sort of damage if used in the proper manner. So a battery has a useful life of about 1,000 cycles. So if you're going to use a battery system, you're going to be changing your batteries pretty often if you're going to be using a lot of electricity because you're going to be cycling them quite often. The capacitor, however, does not wear out. It cycles at millions and millions of cycles a second, and it goes well beyond 40 years. So that's the correct option, and I'll show you a chart later on from one of the battery manufacturers that backs me up on that. We're going to another photograph here, and that's okay. We're walking around this one. We're going to walk sort of a circle around it and see what's there. We were talking about the variable neon variable deal for letting the amount, making the tubes brighter or dimmer. It's made different than the dimmer switch that's in your house. So you can switch the tube, but you probably come to grief if you use the house dimmer. These things are maybe $30 a piece, depending on where you're at. Of course, here's the neon tube transformer, and it's built with an earth ground coming out on the other end there, so it's center tapped, which means it has capability of making amperage for you. Without that center tap, you wouldn't have the amperage available to you. As a matter of fact, as you lower the voltage in, the amperage goes up on this thing. So if you run it at less than 110 volts on this inverter here, and then you back it off again with the variable deal, you're going to end up with, in some cases, more amperage than the device can handle. You can melt it. You can see the outside coil here. The center part of it is missing some turns. I took the turns out of the center part of it, and basically the electrons are moving this way, and the electrons moving this way, and then the tail back there that hooks the two together and goes to an earth ground is where your amperage comes in. So whenever you take your amps and volts apart and you start bringing them back together, you get volts times amps equal watts. So that's your useful energy, and you do this as you go into the capacitor bank. So coulombs and watt seconds are all basically 1 coulomb, and 1 volt second is basically 1 volt at 1 amp at 1 second. So they're all the same thing. Sir?
Can I have a question? The neon transformer, is that solid state?
This one looks like it's solid state, but it performs as though it's not. Being solid state, I'm not quite sure what it would do to it, but I've used them, and for some reason they work. I don't quite know why the reason is, but I do know they still work. And this one looks like a solid state because that's 9,000 volt 9,000 volt transformer, the small one that's there. See that? That's 9,000 volts right there. And if you look at the label on this thing, you're in for a surprise, because if they tell you that there's so many volts in and at so many amps and so many volts out at so many amps, it turns out that this device right here is an over-energy device very noticeably, because if you look at the information on the one that's down here, you're looking at the one that's on the floor. So if you take the numbers off of the thing, the volts in and the amps in and the volts out and the amps out, that little device has produced noticeably more energy than it had going into it. So it's already beginning to behave as an over-energy device. And they actually stamped it on the label. They don't say that it does that, but just the guys that are curious can find out for themselves if they want to. So. Hey, we're going to move up closer on some of the photographs now and take a little bit closer look at some of the components that are on the device that we were just looking at. There you go. Okay, I have no way of knowing what you're seeing out there because I'm blinded by the lights up here. I'm simply trying to stay out of your way, so if you're not seeing something, you need to let me know. No, this thing is kind of, it could be that these lights back here are messing things up, but we can't really turn those off because they're making a tape of this, and if they turn them off, you'll just have the voice and what's here, and there won't be any speaker. So, anyhow, let's see. There we go. Okay, you see the L1 coil here. It's 3-inch Baker-Williamson coil. It's had the 4 turns taken out of the center here, and they're made into a pigtail, which forms the ground, the negative ground out, or the amperage end of the deal. On the ends here, they're coming off and going out and coming through. This is a series of very high voltage capacitors that are normally found in flyback transformer circuits and televisions. So we're into very high voltage on those diodes. And basically what they're doing is what the 2 diodes were doing in the other device. They're taking a sawtooth pattern and changing it into a flat pulsating DC at very high voltage. It's coming out of there, and there's 2 outs here. One is whipping around and coming across here to here, and then it's going to the output over here, which there's a coil system. You see a double coil system there, and it's going through this first coil system, and at that point it's smoothing it out is what it's doing. And then it's going on to the output block, which is back there. At that point you're ready to go to the transformer. Okay, this wire here has very interesting characteristics. It's extremely high voltage wire. It has a thick layer of silicone over it, and then it's got another envelope over that on the outside that looks like clear plastic. But it has some of these wires that I use have over 80,000 volts breakdown on them. So, and the bottom one down here is the same type of wire, same manufacturer, but it's a different color. And what it does is basically pick up. It doesn't come over to the device here. It really stops on this end of the device and goes this way, and then it becomes the output on the negative side there. So you've got your very high potential one, and then you've got you've got two of them. And the sense of plus and minus, which you normally think of, you really don't want to think of it here. You want to say that one area is higher pressure electricity and another area is lower pressure. And since the electrons are in an awkward position, they will try to get back to ambient. And in the process of getting back to ambient, they're going to be doing the things that you want them to do. It's just like water that rains on the side of a mountain. It's going to find its way back to the ocean. So once you get the energy balance working for you, then you're on your way. Okay. Let's see. Can we go back to the slide, or do I need to do it? There we go. Okay, we're looking at it from another angle, and you can very easily make these the complete system out of a 3-inch piece of PVC. The one that's on the inside here is a 2-inch OD PVC, and it's got the windings for the L1 coil on it, as you can see through it. And the reason for putting it on the slide deal is the fact that that becomes a tuning device. If your device is not properly tuned, which you can build it without taking any measurements or doing anything, simply by calculating the length of wire that's in the L1 coil and then taking 1/4 of that and measuring a piece of wire and then using that for your L1 coil. And you will be very close to the tune almost going into it without any capacitors or anything. But you're going to probably want to put at least a capacitor either on your L1 or your L2. It's much simpler to put it on the L1. But if you put it on both of them, of course you're kicking the voltage up in both cases. And it doesn't take, it takes high voltage capacitors, which are a little bit hard to come by. The ones that I have here were custom made for me by Cornell Dubier, and find them in a catalog anywhere. They're custom run, and the diodes are also not available that I used, except on the large ones, the 200 amp ones. Those are commercial variety, but the diodes on the machine that we're looking at here, there's no way on earth that you will probably end up getting those diodes, unless you get them from me. I've got quite a few of them. And you have to order a large number of them in order to get a run on them. And they stopped making this particular diode back in 1993. Yeah? Have a question back there? I can hardly hear you. I don't hear you, but a little bit later we'll open the floor up, and if you come back at me at that point, well, I'll give you an answer. Okay, you see something here which people say can't happen. If you notice the double coil system, this is the active one going through here and going out to the transformers. And this one is not hooked into the system except magnetically. And it has the same activity as this one, even though it's not hooked into them due to the magnetic flux working on it. So what that tells you is that this separate coil here is not using any energy, but it's generating energy which you can keep your batteries charged with, so that your batteries never run down. So this is one of about half a dozen different ways of doing that, recharging your battery. The way which I normally prefer is I calculate the length of the wire from the battery to the input into the device, so that it's 1/4 wavelength of the L1 coil. And for that reason, it picks up the radio frequency, and it is with the diode, kickback diode there, it forces the high frequency electricity back into the battery, and the high frequency electricity is charging while the DC is coming out, and actually it's doing a better job of charging than the outcome. So the batteries, some of the ones that I've used, I've had for more than 2 years and used them continuously with almost everything imaginable, and they measure the 12.97 volts exactly like they did 2 years earlier today. So I may not completely understand why that happens, but I know that it does.
What are your batteries? Your batteries, lead acid storage batteries?
I have trouble hearing to begin with, and if you'd like to come up closer, that may be the way to solve it. If you'll come up near the corner here where I can hear you. Okay.
Are your batteries lead acid storage?
They're calcium lead. They're sealed batteries. They're a very common sort that you find, and they're not one which spills out the material. And the idea that they can only be recharged 100 times apparently does not necessarily apply. We'll come back to that a little bit later. But the battery manufacturer says that that's what will happen, so, but I don't find it happening. Okay, we have another one here. Oop. Okay, you can see that one? It's a little bit better shot of the piece of PVC. Of course, I very carefully sand these things so there's no markings on them, and it looks like it doesn't look like PVC at all. If you notice, whenever you see the real device, it looks like it was meant to be what it is. And again, we're looking at the neon tube transformer with the 2 high voltage outputs, and then we're looking at the block here, which has 2 high voltage diodes here, and it has these capacitors here. The capacitors are between the where these two come together and they pass through the diodes is between that point and the negative, or the earth ground, which is on the end. There's a little screw on the end of this block, which is the center tap or the earth ground deal, and that's the thing that ensures your amperage whenever you get to that. We'll go into the various kinds of coil windings in a little bit and see what happens there. There we go. There you can see the block, and you can't, I don't believe that you can see the 2 diodes, but they're there. See? High voltage diodes. And there's one on each of these outlets to the high voltage side of the transformer. And then once it becomes DC, well, then I tie the capacitors across that DC, and where the earth ground comes back through here, and where the lightning arrestor is, where it returns to the, this is your earth ground right here, where it returns to the transformer. This is another angle of it. This is the variable deal, the plug socket, the inverter, the lightning arrestor, and the earth ground, which has to be tied to an external earth ground. And here's the point where it goes forward into the L1 on the bottom side, and here's where it comes back from the L1 on the top side into the earth ground. Okay, you can see where I cut holes in the device here. The bottom one goes underneath and comes up to here and then comes through and then goes around this thing and then goes back inside and then comes back through this one to the earth ground. Yes, sir?
Now, you did something just right after you put it on there that made it look darker.
Can you tell me what it is?
I don't know. You put something.
There's black and white and negative and automatic and whole.
You pushed the button there. Which one did you push?
The one that brings it on is over here.
Turn it back the way you had it. Start it.
Okay, would you like to come around here and show me? That one, we may not be able to use that one. It's too dark.
Which one did you do?
The one that's up there now. It's not showing any detail on it. Let me go back to the other one and now see if you can make it work.
Is that brighter?
No. Brighter before.
That one?
No. One brighter before you.
Will that be okay?
No.
Here, I really can't see it very well, so... Okay. Well, we're zipped right on through these, and we've got so many other things to talk about that you can't believe it. One of the things which we're going to be seeing is this device. And it's a 1/4 size version of the one that we've just been looking at. It's built in this suitcase. It actually only takes up the top half of it. The suitcase is mostly empty. Well, that gives you some idea of the size. It was just a little bit too long to put into an ordinary briefcase, and that's why I went to the suitcase. But the suitcase has wheels on it and rolls and has a handle that pops out, and that makes it real easy for me to carry with me when I go overseas and other places with this. Here you can see the handle. I guess, well, maybe you can. Okay, well, we're going on to something else. We have so many things to look at that you can't believe. Okay. Okay, there's it is standing up in the den at home. And I have 4 of these fans that I normally use, but due to space limitations, I only brought one. Okay, there's... okay, it's too dark. It's too dark. Okay, let's see something else. These are some of the... some of the tools sitting beside the large capacitors that we were talking about a while ago that came from Finland. Yes, sir.
What does the suitcase do?
What does what do?
What does the suitcase do?
This particular one, how much output?
No, how much output?
Oh, those instruments?
No, don't. The suitcase. What's that? The suitcase.
Okay, we're going to take the suitcase and play with it in a little bit. It has a complete unit in it that's fully functional and does everything that anyone would imagine. Basically what I've done is reduced it to an off and on switch, which is the level which seems most people seem to be interested in. So I'm going to accommodate those fellows in a little bit. And we're going to run some tests on it to see for sure that it's doing what I'm saying it's capable of. Okay, that may look somewhat familiar, but if you know the year that it was built before Tesla was actually building coils. And it has a huge amount of amperage. And it has the center tap, like I'm telling you about on my coil system, which makes it into an amperage, voltage and amperage type device. And they had a great deal of difficulty with the amperage because they were all the time. Hey, there's another version of this particular coil which was easier to manage. Okay, you see that? Your L2 coil is on the inside of this glass deal with oil in it. Your L1 coil is on the outside. It's not necessarily to have all of those turns that the outside coil had. It could have only maybe a 1 turn or 3 or 4 turns. Actually, by having fewer turns, it kicks the voltage up on the inside one. Instead of, say, having 30,000 volts coming out, if you reduce the number of outside coil turns to about maybe 3, you probably would have maybe 100,000 volts or more coming out of that inside thing. Okay, in order to get useful energy, you have to go from the high frequency, high voltage into some sort of storage situation. And in this particular case, the light bulb is being lit with what we would like to say is a Tesla coil, which is actually the Arsonville coil. So you can see that the Leyden bottle there is the capacitor, and you see the smaller winding and the larger winding, and then you see the air antenna on one end, and then you have the light bulb sticking out. When you bring your hand close to it, the light bulb lights up. This is evidence that Tesla knew that the coils could be wound for amperage. And I'll have to, there's 3 different illustrations here, but you see the center tap, the device in the middle, or the one with the H on it, is your armature or your spinning deal like you have in a starter motor or in a charger, say an electric charger in an automobile. The outlets there, if you notice, one of them, the center tap, is going to be your negative, and the other 2 are going to be the high voltage output. But what they're basically doing is storing electricity into the system in such a way that these high voltage arc lamps, which are the little over on D there, D prime, the little round things, those are all arc lamps. And you can put any number of them there, and it will automatically adjust to them. So what is happening in my case, I'm removing that armature there. I'm keeping the center tap, which is the negative, and the 2 output things, and I'm basically, that becomes my L1 coil. I take my L2 coil. The L1 coil I put in place of the charging device, which is in the center, and by the magnetic radio frequency pulsing of it, I'm running that coil system in the same manner which it's being ran with the generator, conventional generator. Except that what I'm doing runs at a much better rate, and it runs at over energy rates and things like that, which this thing, I don't know how you could calculate it, except that it does have output and it does run devices and do useful work. The center one here is a slightly different arrangement, but it has the center tap, which is important to getting amperage. It's wound, one part of the coil there is wound in one direction, one's wound in another direction. And that means that the one that's going the opposite direction is made to produce amperage instead of voltage. So the top part produces voltage, the bottom part produces amperage, and then there's a second or third way, and then there's about a dozen other ways, but the bottom one will produce huge amounts of amperage. It's got a double back on the thing. Yes? On the A on the top one? Top number on...
36961.
Okay, this is from a book that's available in the store here, The Complete Patents of Nikola Tesla. It's page number 8. So if you want to actually go look and see see that particular book. And it is not a Tesla coil in the normal sense at all. It does produce amperage and lots of it. I told you that I would show you a bit of information on batteries as to why batteries were not desirable as a way to store energy with these particular devices. On the very bottom down there, you have the very best type of batteries that are available. And they're the sealed nickel cadmium batteries and the sealed lead acid batteries. And those have, if you look out to the rack there, you see the recycle. They can be recycled between 100 and 300 times for the sealed lead acid, and from 300 times to over 1,000 times for the nickel cadmium. Now, even at 1,000 recycles, this type of device would use that 1,000 recycles up so fast you can't believe it. So you can pretty well forget about conventional batteries except for short-term experimental type things. Now, that is the reason why I have picked the capacitors instead of batteries for storing the energy in order to get it to do useful work. Last year, and I had a particular illustration which I used, which explained why over unity was possible. These are 3 different conditions under which you get resonant circuits. There are other conditions. The bottom one there is the one which you're really looking for, and if you can see it on your oscilloscope, and you can measure it, and I'm going to show you a more detailed breakdown on it next, and you can see that it's building energy, and it builds it up to a certain level, and then it cuts off, and then it cycles back. The resistor shunt in the middle there is basically what helps cause this cycling effect. It's part of the frequency in the cycling deal, along with the capacitor and the inductor, which would be your coil. When you look at that closer, you can see why, or see what each part of it is that's causing this to happen, what's pulling it out each time. This is your over unity looking at you straight in the face, and there's no way to deny it. This is one illustration that I used last year, and if you understand what's going on this, you can build any kind of useful energy device that you want to. This has the whole story on it. As a matter of fact, you even see the adjustable deal on the top there where the coil is inserted in it, which is what you see on this thing down here. You also see the capacitor bank, and you see on the number 2 there, you see an actual transformer out there which is changing it to whatever level you want it to be to go on and to useful working. Okay, the one just below there, the capacitor or the storage thing is that long narrow thing immediately after you come out of the coil, and that's helping feed those light bulbs out there. So a light system with any amount of light bulbs out there would work with that type of setup. The bottom one there to the left is basically the way to go. Excuse me, the center tap there actually becomes your negative, and the 2 output things on those coils become your high voltage thing, just like the earlier coil winding that we were talking about. And this type of device is actually the thing that's got 2 coils on it on my board right there. That's that very same device. So by putting the L1 winding in between those 2 coils there and hooking up the ground part of this and the 2 output deals, you've got immediately a working Tesla coil in a very good range with amperage and voltage. Okay, well here's Tesla's deal on lighting up fluorescent light tubes. He used 2 metal plates that were behind the draperies that you didn't see, and used the basic system that we saw on the top right a while ago to put charge on those 2 opposing plates. And by walking around over the stage, the fluorescent light bulbs and things would light up. And he also happened to be the inventor of the fluorescent tube. He had hundreds and hundreds of different. I'm going to show you a large scale Tesla coil, which I did. Okay. Okay, what you're looking at there are 2 18-inch pieces of 12-inch PVC. There's one on the top and one underneath there that it's sitting on. The thing in the center is the tub that goes under a whiskey barrel planter, which it has rollers on it. I took the rollers off, and it happened to be the right diameter to build the L1 coil on. And of course it was black, so I changed the color on it. And this particular one has an output of 400,000 volts, and it has quite a bit of amperage also. The instrumentation that you see below down there, you see the little 12-volt battery sitting beside it. So it's very obvious that if you take what's out and what's going in, that there's a very large difference between the 2. I'm going to show you one which was built to demonstrate over unity. If you have separate coils which are no way connected except through the magnetic flux that are tuned to the same frequency of the output one, in the center here you have the output coil, and you see the L1 and the ring around it, and you see the L2 in the center, and it's tuned. The tuning parts are right here. See the variable capacitor? It's a variable mica capacitor, and then there's a variable resistor here, which is in part of the circuit. So that goes back to the circuit I showed you the over unity thing a while ago, where you had a resistivity in there, but when this thing becomes resonant, of course the resistivity all becomes negative, and therefore you've got energy which greater than what you had to begin with. So anyhow, this thing behaves exactly like a radio broadcast station, a very simple radio broadcast station, about 18 and 11 or somewhere along through there. These other coils are tuned to the same frequency. So being tuned to the same frequency, this thing, say, puts out 100,000 volts at a certain amperage. Well, these, regardless of how many of these you put around there, if they're tuned to this one, they're not going to take away from the voltage that's there or the energy that's there. They're going to duplicate it. And the reason is that the electrons that are active here are not the same electrons that are active here. Through resonant frequency, those coils are tuned so that they react just like if someone taps you on the knee and your foot goes up, sort of deal. It's now 10:10, and let's see, I think we're scheduled to break at 10:15. People think that the electrons go from point A to point B. That is not true at all. The electrons are activated at point A, and electrons move tremendously slow speeds. So the electrons which are at the generating station in your village are not the electrons which are at your house. When you turn your house switch on, you're grounding a system that is connected, and the electrons at your house start acting up, and that's where you get your energy at your house. It does not come from the power company. You see it? Okay. Those of you that are asking what the basic circuitry on these things boil down to, well, this one is probably easier to understand than some of the ones that we've been looking at. But the basic idea is present in this schematic. You see your number 5 is your L1. The 3 there, or the first block, the large block that's up parallel with the number 5 to the left of it, would be your high voltage transformer, whether it's a laser module or whatever. And the spark gap, number 4 there, would be the lightning arrestor, which I showed on the other device. Then you have a voltage limiting device, which would be number 8 is the voltage limiting device on that particular thing to keep it down at a level which you can manage. There's only one diode showing in this case, which is sending forward pulsating DC, kind of a sawtooth type deal. By hooking another diode down on the bottom corner there and whipping it back up to the in front of where the number 9 is now, going towards the transformer, you would have smoothed out pulsating DC, which is what you really want to go forward to your transformer. Number 10 is matching the transformer to the frequency which you want it to run at. Once you've taken the measurements on number 11 there on the input side, you can calculate what number 10 will be, which will give you your 120 cycles per second, which is 60 up and 60 down, which is your 60 cycle electricity, which you're normally accustomed to. Number 12 is a voltage control to keep the thing from running away from you and burning the transformer up and those things. There are many, many different ways to go on this. Another way would be to go with toroidal transformers, and that's what I'm going to show you next. The same situation set up with a bank of toroidal transformers. And there's almost no end to the types of things that you can come up with, and they all seem to work fairly nicely. take a look at some of the measuring devices which are involved in you can see that it says that the device will measure to 1 million volts. It goes to 10 megahertz, and with the proper voltage divider, there's a 400 volt divider that's sitting beside it there. There are dividers which go up to about 5 million volts. That's the conventional way to measure it. My preferred way to measure it is with a magnetometer and electroscope, various sorts of devices that measure magnetic fields, and the magnetic field is directly related to the amount of amperage that's present. If your amp turns and your coil represent a magnetic field, and it's very measurable, and it's a very safe way to go. We were talking about the separate coil systems a little bit ago, where one was running and the other would copy the amount of power on it without depleting the energy from the first one. That's what this is made to demonstrate, and it's used in physics classes in high school and college. And what happens is that second block there, which is in no way connected except by the radio frequency, will light a conventional 60-watt electric light bulb. The input on this is 1.5 volts over on the left-hand side there. 1.5 volts input on the left-hand side powers that coil system that's on the block on the left side, and you can move this other coil some distance away, and you can hook an electric light bulb onto it, or 60. It comes with a 60-volt neon tube which lights up whenever you tune the frequency of the second coil to match the first coil. So that demonstrates one of the. There's the hookup information showing how the two blocks work. So that's your basic wireless transmission of energy device. Let's see here if we can do some zooming on this one. Okay, this is one of the early ones showing the transistor that's being oscillated by the capacitor, variable capacitor and variable resistor in the back of it. And the number 7 thing actually happens to be a high voltage transformer. That could be your the one from the television set, the kick flyback transformer from a television. It can be the transformer from an automobile, one of the early ones. And the number 6 down there is basically an off and on switch down at the very bottom in the middle. It causes coil, or number 9 there, to react, which in turn number 11 over there can be tuned by the grounding capacitor, so that it will match the number 9 deal, and it will become active, so your energy will be coming out on number 12 there at the top, and the bottom one down below. Now you can center tap this thing, and you'll have your amperage, and hook it up like we were talking about. This is the one that postage card size one that will run an automobile from say maybe a 6-volt battery, flashlight battery, not automobile battery. And it's one that can also recharge the battery, so that the battery basically never runs down. we were talking about voltage dividers. This one I'm going to have to put it on in more than one position because you can see the man down below. Okay, I'll turn him sideways and so you can see it. The thing is over 12 feet tall. The man is 6 feet tall. So that's used in your megavoltages. You don't have to use that at all if you use my system of magnetic fields and electrostatic and electromagnetic field measurements. You don't have to use that at all. Okay, this is something that we can thank Romania for this. This is from a translation from a book in Romanian, which I have or had, that tells what happens in magnets, and a Tesla coil or the center tap on the Tesla coil behaves just exactly like this magnet. The block wall system there becomes the negative or earth ground, and that's the place where the electrons are getting organized, and on one side they spin right, on the other side they spin left. And you can take your hand and cusp it, and the direction of the apparent direction of electron movement would be like in this plane, and the spinning would be around that particular plane. And then on the other end of it, you have to reverse it. And that would be your north. This would be your north end. This would be your south end on this particular thing. Now, coils behave exactly like magnets. They have a more or less a north end and a south end. And as far as I know, this has never been published in the English language. This was actually a Russian publication in Romanian from back in the 30s. And we're going to see how that ties together with some of the other things. Okay, this is can you see that okay? What I've done there, I've taken the Tesla coil with the center tap on it, and I've shown what actually happens when electrons move in one direction. The amperage part goes the other way. As it turns out, there's two types of electrons. There's one that's a little bit smaller and weaker than the other, and it becomes when it spins its direction, it becomes the amperage part, and the stronger of the two electrons spins and makes the voltage part. And in nature, they are coupled together. And that's the reason why they're inactive and floating about in space without anything happening. It's whenever you disturb them or knock them apart that they try to get back together, and that's where you get your useful energy. And they're relatively easy to disturb. You can do it either by electromagnetic methods, or you can do it with the conventional coils and magnet system, which is also electromagnetic. But it's much easier, much more efficient, and the rate of disturbance determines the amount of energy that you end up with, which means that 60 cycles, generating at 60 cycles, you're wasting your time. If you're generating, the amount of energy output is directly related to the square of the cycles per second. So at 60 cycles, square that, then square 218 million times a second, and you will see that the efficiency on my device has gone up unbelievably. As a matter of fact, it's gone on the chart. It's gone straight out of the sky. And these electrons, when you disturb them, they are not in any way diminished. They simply will go back to their normal habits the first chance they get, and they will be there, and you can use them over and over again. You're not disturbing the environment or doing anything which is harmful to human beings, depending on the frequency you're running at. If you're down in the lower frequencies, say down below the radio frequency, which is below 20,000, the lower you go, the more harmful the environmental effects are from electricity. The frequency that was chosen to be the standard was probably the worst possible frequency imaginable. A better version of it is the 400 cycles per second, or actually it's 400 up and 400 down, which is 800, which would be considerably more efficient and better than the 60 cycle way of going. And we see it in the electrical vehicles and the wiring systems in the airplanes and the servo mechanisms for controlling the airplanes, the wheels and all parts of it, including a lot of the service vehicles that they use at the airport. They're running at 400 cycles a second, which means they're running at a higher voltage. They're running like 440 at 400 cycles, and the lower the cycles, the more the heat and the wasting of the energy. So the higher the cycles you run at, the less harm to human beings, the environment, and other things, and the greater the efficiency. So as you go into the higher frequencies, it's real easy to trip over into the over-unity systems, which we're seeing here today. This illustration is in the current issue of the Tesla magazine, which they have some copies in the bookshop in case you want to look closer at it. The electron is a very useful thing. It produces a number of things which we normally don't think about. As you can see there, we have two basic types of related energy. We have the resistance or the impact and the light, the heat deal, and then we have the electromagnetic reaction, which is up at the top. There's methods of storing this energy without disturbing or destroying the electrons. And the whole idea behind how this thing works hinges around the fact that you can take the energy without diminishing the electrons. Okay, the basic storage formulas are these, and you'll notice that part of the formula gets squared, and this takes you directly back to EMC squared, or the things that led up to what Einstein later put into a statement which he gets credited for. The idea had been around quite a long time. As a matter of fact, if you go back to Maxwell and the people that were working early on, or sort of, not real early, but sort of early on, their ideas about electricity are almost identical to what I have. In reading the early accounts, Maxwell would have no trouble at all agreeing with everything that I've been saying. He doesn't agree with what is taught in the physics books here. They quote Maxwell all the time, but they only quote him out of text, and they quote him in such a way that he's saying something which he would not have said if he was personally, physically present. And how do I know that? I've been reading the documentation done by the people that actually worked with Maxwell, and some of his actual writings. The book that you see that's accredited to Maxwell was not written by Maxwell. And he probably would have had some difficulty with it. Now that we know that those formulas exist, let's see what they really can do. Okay, a joule, a watt second, coulomb, a farad, all those things are 1 volt at 1 amp at basically 1 second. They're all the same thing. They're used in different statements and ways that appear to make them be different, but really they base 1 volt at 1 second, or 1 watt. So that's a joule, a watt second, a coulomb, and a farad. So with that in mind, half of the energy is in magnetic and half of it is in electrical. So the 0.5 there is taking care of the fact that we're using the electro end of it, and it's half the energy that's there. The other half is in magnetic. So with that in mind, we have a capacitor which has a certain portion of a volt. See, that's like if it was 1 volt, it would be 1 with the decimal point, but the capacitor is showing 3 sets of zeros basically there with the 1 interspersed, which makes it 10 microfarads. Okay, then the 100,000 would be the voltage. It could be any voltage. It could be 100 volts, 1 volt, or 25 volts, or whatever. And then if you square that, and then you have to further go to times the cycles per second. And after you've done all of that, that tiny charge that was there, each time it cycled, it adds up. It becomes cumulative. And that's why your capacitors, even though they don't appear to have a lot of electricity in them based on the fact that, say, they're 8 microfarads or whatever, if you repeat that enough times in a second, it becomes cumulative, and all of a sudden you have hundreds of thousands of volts that are available to you. And they're available, you're outside of the system which you were to begin with, so the amperage at that point depends on the degree to which you ground that capacitor to the earth. If you should touch it and touch the earth ground at the same time, it will cook you on the spot. So you don't really want it to unload at a very fast rate. So what you do, you choke it back with dividers so that only a limited amount will pass through the load which you're actually wanting to do the work for you. And at that point you have useful energy. The device which you see here in the small suitcase requires an earth grounding. So I've got a 1-wire deal that goes into a 3-hole plug back there, and it's using the center plug or the earth grounding. If anyone has any doubts about it, they're welcome to come up and see that there's no energy coming from there.
I notice on the unit on the floor,
yes, sir.
It appears as though the secondary is all wound the same direction, and that's different from what you were talking about.
I saw the drawing a while ago that I put on the coil. You can wind it in a reverse direction on the bottom half or forward either. If you want to emphasize the amps, you wind it in a reverse manner. If you want to make a transformer which produces amperage basically only and not voltage, take a, well, let's see if we can find something here. I'll show you how to make one real quick, like one that will do just amperage and nothing else. And you can drive this amperage thing with your L1 coil. Okay, see, take this thing right here and loop it back, and then you wrap it around wrap it around the coil form so that both your in and out are down on the bottom part. And at that point, where these two are running parallel to each other there, it cancels out the voltage so that only amperage is there and it magnifies. So you can make your L2 coil there. If you wind it correctly, you can get only amperage from it and no voltage to speak of. Just like you get, say, 30,000 volts, or you get 30,000 amps. But you don't want that because the device would melt on you to begin with. Okay, some more questions?
If the ground cable is removed from your suitcase, will the unit still operate?
Yes.
It will.
You notice the screws on the top here, that's where the thing is bolted in. And it actually takes up just the top half of the suitcase.
Okay, but if you pull the actual ground cable off, that small black cable, will it still operate?
The ground cable is actually necessary for it to operate correctly. If you take it off, it starts building up heat and other things.
Okay. What else could be used for ground if this were to operate a car?
It is grounded into the air as it is, but if you use it for any period of time and it's ungrounded, it starts building up heat. And there was no heat from what we were doing.
Okay.
What category? It's a resonant induction energy transfer. Resonant induction energy transfer. Your magnetic changes to electricity, your electricity in turn changes to magnetic, and that's how they talk to each other. And depending on what the electron is doing will determine whether you've got electric or magnetic.
Would you have anything against the camera? Scanning that so it can be put on the video, people can see a good shot of that?
You want to see it on the video? He can zoom in on it. What I'll do is take it, and it's a little bit heavy, but we'll take it here. Which way do you want me to turn it?
We'll bring it to the camera so you see all the information on the...
Yeah, well, he can zoom in on it and come in any detail he wants to, I'm sure.
I'll hold it up there if you want.
Well, I'll turn it around in a little bit and turn it some different angles. I'll hold it for just a little bit and say this position, and then I'll turn it at a different angle so that you can see it.
There's a lot of printed information on the devices you're using. It's not going to come.
Yeah, well, the printed information on the capacitors won't do you any good because they're custom run for Cornell Dubier for me, so you'll have to find your own, but they won't be custom run.
How about the transformer and all that?
The transformers, you can find that at any supply for neon tubes.
Well, I know.
Yeah, I'm still waiting for that person to come up and calculate what's reading on the label of the high voltage transformer. Because it's actual printed and it tells you that it's an over-unity device right there. It doesn't say that in words, but if you calculate what they put on there, they have printed their test results from that high voltage transformer, and it comes out considerably more than what went in. Yeah. Okay, I'm going to put it down, and we can continue with the questions if you like.
Yeah, since approximately 1850, 1875, the days of Maxwell, Henry, and Faraday, the electromotive formula has been written I is equal to E divided by R.
Yes.
Your device clearly suspends the balance of that equation. My question to you is, how would you rewrite the equation to explain the excess energy that's being produced by your device?
If you read the early printings from Cavendish Laboratory in England, the people there were connected with Maxwell, and if you read the books and the printed material that was occurring at the time that Thomson did his work on the electron, and that Hertz did his thing, and the other people, you'll find that Maxwell actually didn't think the way that he's presented at this time. That Maxwell, actually the thinking of Maxwell is almost exactly what I've been telling you in my written material. So what Maxwell supposedly, what they put in shorthand form to illustrate what was happening was very much in doubt at the time that it was done. There was serious doubt, and I can show you in print where a number of people who were headmasters for in Cambridge, who wrote the books and things at the time that Maxwell was coming along, expressed serious doubts about the shorthand methods of which things were presented.
When I realized that the components in electrical field has an alternate component of magnetic field, and that they're equal and opposite, and that's your Lorentz or your equal and opposite EMF opposed sort of thing, and they do not appear separate. And being in the field of geology, there were electromagnetic maps which were available, which told me that the Earth's surface had a tremendous amount of electricity in it that was useful. And in trying to resolve that in regards to the activity of electrons, I realized that energy is everywhere at all times in great amounts, and that it's dormant until you disturb it or cycle it. And the cycling would be the resonant activity seen in radio devices. So you're moving electrons and you're creating electro and magnetic fields, and by being able to capture these fields at their higher levels of excitement, you get greater you have a gradient that's greater getting back to ambient, so therefore you have a greater amount of energy.
Is this similar to what Nikola Tesla was trying to achieve with free?
It is a spin-off. Basically what I have done is pick up where Nikola Tesla had reached, and I've put myself inside his mind, and I've expanded and extended what Nikola Tesla was doing.
Now, do you think you've actually figured out what he was doing? Were you
Yeah, I can read his mind almost perfect. From the first moment that it was going to work and how it was going to work.
Really? Were you trying to build something specific at the time?
No, all I was trying to do was disturb ambient.
Really? Now, tell me something about these radio frequencies. I understand you're using radio frequencies to achieve this.
Well, the electron, when you cycle it or move it, you get a magnetic field and you get an electrical field. And the faster you move the electron, the cumulative effect of that magnetic and electrical field becomes greater.
Okay.
So if you're cycling at, say, 60 or 120 cycles per second, you get the same amount of electrons, and then you cycle, say, at 1 million cycles per second, the curve on the increase in the amount of magnetic and electrical field there is doing this. And when it does this, and you capture it at one of the higher points, you capture it at a higher point, you get a lot more energy from the same amount of electrons than you had at the lower point.
Okay.
So this, to some people, would be would say that you're getting free energy.
What would you call it?
I would say you're getting what's there.
Just finding a new way to
you're getting what's there. The term free energy is a bastardized terminology that's used by sour grapes establishment.
Use term
So the electrical flux, when you start measuring electrical flux or magnetic flux, which is the other side of the coin, you find that the Earth has an enormous electrical field. No, I had the conclusion before I ever started. It was what got me into it to begin with.
Really? So this is sort of what keyed you into what was going on.
Yeah, I knew that there was an electromagnetic. You can't have one without the other, and it flips. And when it flips, at that flipping point is where you have your useful energy. And the more you flip it, the more you have useful energy. Everything in nature, and everything in nature is of course simple, so all the other things, including molecules and everything else, they all attach themselves to each other. So in the case of electrons, it's unreal to believe that a single electron will be floating out here without interacting with something else. So as it turns out, there's good evidence that some electrons have more negative charge than others, and that by being more negative or less negative, that's the same as being plus or minus. So therefore, the electron with a weaker charge will attract one with a stronger charge, and they will be orbiting in each other, and they're relatively easy to pull apart. So the electrical and magnetic charge of the electron, of course, when you spin them right, you get a magnetic field. When you spin them left, you get an electrical field.
Okay.
So when they spin apart, you're getting a benefit of both of those, and then whenever they come spinning back together, you're getting the volts and the magnetic field coupling again, which means your amps times volts equal watts, or you've got useful energy.
What do you call it when you capture this wavelength? Do you have a name for it?
When you capture it?
Yeah, like obviously...
Well, you can temporarily store it in capacitors, batteries, coils, or various other systems temporarily, and then you can convert it to some other system that is useful to the device which you need to power.
So the energy just doesn't tear around wildly?
No, it's not just running all over the place. Sometimes it gets loose in the form of sparks or spacks or whatever.
Is this over here?
The devices which I have invented, which there are a number of them, they all actually accelerate electrons.
Okay.
They're electron accelerators, and one of the outcomes I might mention of the multipactor thing which Farnsworth had, which is a over-unity device without question, is the magnetron in your microwave oven.
Okay.
So all patents are related to magnetrons, multipactors, diodes, and all related patents are over-unity patents.
Fantastic.
And there's no way to deny it. If the person has any, even slight degree of intellect, they will know immediately that that's the case.
So this has been sitting in front of us the whole time?
Yeah, it's been here since 1920s and 30s in grand form. Before we go to the other devices, this is a component which shows up on some of the devices.
Okay.
And can you read the reading on it?
Give me just a moment here.
I'll bring it even closer if you want so that you can actually read it. The reason I want you to read it is because calculate the input which the manufacturer specifies.
Okay, go ahead.
And then calculate the output which the manufacturer puts on there for that same amount of voltage, and you'll see immediately that this thing is putting out more energy than it was put into it.
So
the manufacturer actually states the input and the output, and it's on the label, and they have tested it, or they would not have put it on there.
So it exists.
Here's an over-unity device looking right at you.
Okay.
And there are a lot of them that are that way if you bother to calculate the input and the output.
Great. Okay. What is this?
Okay, this is one of many devices which I have built. I would say one of several hundred. And this is one of the sort of intermediate ones.
Okay.
And technology present here is largely 1800s.
And well, what is this here?
What is the device?
Yeah, what do you got here?
It's a resonant electrical energy generator.
Well, what does it do?
Basically what I do, I take a low voltage, 12 volts at about 7 amp hours from a battery, and I run it through the device. The first thing I do, in order, the high voltage module here has to run off 120 volts. So since I'm intending to use a 12-volt battery, I have to bring the voltage up so that the high voltage module can run.
Okay.
So this is an inverter here.
Okay. And this is just a Radio Shack part.
Yeah, yeah. It's everything you see here except these. Most anyone could get, and these. Now this and this, unless you get them from me, you don't get them.
So these are your homemade ones here.
Well, they were special made for me.
What are they, Art? Can you give me an idea?
Well, these are 10,000 volt capacitors.
Wow. And what's the
this is a 9,000 volt high voltage module that is similar to the little one that I showed just a moment ago.
Okay.
And this is from the same people. This is about 6,000 volts, and this is 9,000 volts.
Okay.
This is essentially a solid state device, and so is this.
Okay. So how does it go here?
Where does what go?
Where does it start?
Okay, it comes in here.
Okay.
And comes from a 9-volt battery.
Okay.
There's a cord that's calculated to a certain length because it's a frequency that works with it's a quarter wavelength of this coil here.
Okay.
The physical length of the input from the 12-volt battery. And the reason for that is that it will recharge the battery if it can communicate with the radio frequency magnetic field that's in the area.
I see. So it's just constantly recharging.
Yeah, the magnetic field from what's going on here will recharge the battery faster than it's being discharged.
That's great. Besides that,
how do I know that? If you take a light-emitting diode, electricity can only flow in one direction in a light-emitting diode. Take two of them and reverse them and make a pigtail and put them in the line that comes from the battery to the device, and depending on which one's lighting up, you know which way the electricity is flowing.
Okay.
And when they're both lit up, you're taking out and you're putting in at the same time. And the reason you can do that is that they're different frequencies. Okay, we've got 12 volts coming in. We have a kickback diode here, which prevents a kickback from the inverter to the battery.
Okay.
And we also have on the input where the 12 volt comes in, we have this pigtail set of light emitting diodes which tell you that you're charging your battery at the same time that you're using it.
Okay.
And once we get past that point and get into this inverter, this is 9,000 volt high voltage module, which would be, it's a version of a Tesla coil, except it's a solid state version.
Okay, okay, that makes sense.
It does the same thing as a Tesla coil, except it's solid state version of the same action.
Yeah.
So anyhow, in order to control that, since we don't want to use the full 9,000 volts, I have a neon tube transformer control here, which controls the amount of the 110 volts that comes out of this into this.
Okay.
I can use the whole 9,000 volts, or I can use any part of it. And the reason I have to cut it back is because what's over here cannot take what's over here. Well, I'm going to end up with a lot more voltage than I can manage. So I have to reduce it. It's easier to reduce it on the low end. Once it gets to the high end, you have trouble, special equipment and a lot of trouble varying it.
Okay.
So I vary it on the input on the low side.
Yeah.
Okay, I get to the high voltage module, and on neon tube transformers they have two output wires. So I have to take the electricity that's on the two output wires and put it back together as one source of electricity. And then I have to pump it through the L1 coil and then back into the system. And then I have the capacitor bank here in order to help regulate that.
And that's, I'm sorry, you said that was 100,000?
No, these are 10,000.
Okay.
Or maybe 15, I don't recall just at the moment, but they're more likely 15.
Okay.
But they were done special order by Cornell Dubier for me, and they were free.
Well, that's nice.
Because most of the companies like that have a department where they will make up samples for you if you're doing research and development, and you need something which they don't have in the catalog. They will make them up special for you, and that's exactly what happened here.
Really?
Okay, once we get to the this is the broadcast end of it, or the part that sets the electromagnetic field into oscillation.
Now, how do you do that? Is it sending a radio wave through it?
Well, it's when you pulse something, and you pulse it through a coil like this, a magnetic field builds and collapses.
And that's all you
It's a collapsing, building and collapsing off and on that spins the electrons. The magnetic field and then the magnetic field off, and they'll spin back to where they were. So you've got the coin flipping with the electromagnetic component flipping. And once you've got it flipping, then you're in business.
So that's the whole trick to this. Is just
Yeah. Once you've got it flipping, then you've got to have something to collect it with. And then the rest of this is the collector and storage part.
So what do you have, just a couple of capacitors there? And
No, those are, actually there's 8,000 volts worth of capacitors there.
Are those special made?
No.
Really? What's the little tube on the end there?
Which one?
So the little yellow...
The yellow one?
Yeah.
Okay, that has a double meaning. In this case, it has no meaning because I've already charging the battery from over here.
Oh, was that used to...
But the energy coming from here before it goes out to the transformer is passing through this one, and that's building a magnetic field. This one is not connected to this one in any way except through a magnetic field. So this becomes a generator of electricity, and you can charge batteries from that.
That's great. That's a great system. How much energy would you say this little system could produce?
This one? What's the output on it?
Yeah.
It's about 16 kVA.
Great.
Which is a lot of energy.
Yeah. And
it could go higher than that. That's with this thing turned down on low.
Wow. Now, does it, like, run itself out?
No, there's nothing here to wear out.
Wow. So there's no...
the capacitors are self-healing.
So this is it. You've got a closed-loop system that charges itself and kicks off enough energy to...
once it's going, it's on its own. No, this is sort of an intermediate model.
Yeah.
And there's a larger one sitting over here, a more commercial type. This one actually, the one in the suitcase calculates out at about, I put in the book a little article I gave you, I think it was 27 kVA.
No kidding.
It's it's about half the size of this. So this is capable of probably around 50 kVA.
Now, is this something that you give away as far as selling plans to people or showing people how?
Well, the plans for some of these things are in the publications.
So this is not any great secret. This is out there.
No, it's looking people in the face. A commercial model, and the absolute output level on it I don't know, but some of the components in there would probably limit it to about 35,000 volts at probably about 200 amperes, and that is an enormous amount of electricity. So you can see that it has the same components that the other device has. They're just scaled up somewhat.
Have you used this one here?
I've had it. I've started it, and I know that I've tested it, but I haven't ran this particular one for any extended period of time, except to just start it.
So this was just sort of an experiment to see if you could build a career?
Well, basically it was just to see how the components fit on the board, was what it was.
Great.
Because I did the schematics and passed them on to other people, and they're building them.
Okay. Great. Use that on this device?
Actually, I'm going to show you how to make a simple one.
Okay, great.
Most of the things that are in my devices which I demonstrate were put there because people expect to see them, not because they need to be there.
Okay.
Okay, so this device, which I had turned upside down.
Okay.
Okay.
Great.
Is the high voltage module here. So we come out and we need a L1 coil here. That's going to be our L1 or input coil, and we're going to run this. Since this is alternating current, it's neither plus or minus. It's going to be what it's going to be doing is coming over here and into here and coming back just like that.
Okay.
So we've got our high voltage device and we've got an L1 coil, and it's all working just fine. At this point it's running at 35,000 cycles per second. Okay, and we don't, the method I'm teaching you here, you don't have to know about tuning. The fact that the length of the wires that go on this coil here are basically irrelevant because it's being pumped by the high voltage device here, and that's going to set the frequency. The length of the wires are not going to have anything to do with it. So you don't have to know how to tune it to do this.
Okay.
Okay, the next thing is that we're going to have an L2 coil here, and it's going to have coils on it, and it's going to be out, and this is going to be your minus, and this is going to be your plus down here at the bottom, and electricity or electrical field always moves from the highest of concentration to the lowest. But in this case what's happening is each coil there has a capacitance and inductive characteristic. It's magnifying. For example, say that this is 3,000 volts here, and we have 10 turns here. So this is volts, and we have 10 turns. Okay, we divide 10 into 3,000, and that means that each turn is going to equal 300 volts. So each turn on a L2 coil here, each turn on there will have 300 volts on it. So if you have 30 turns, you've got 300 times 30, which would be, let's see, 300 times 30. Okay, and that's going to be 0, 0, 0, 9. So you're going to have 9,000 volts on your L2 coil.
Okay.
Okay. And it's going to do that irregardless of the amount of turns or the frequency or whatever. What we're doing by forcing the 35,000 cycles per second onto this first coil, we're forcing that second coil to duplicate the same thing as long as it's an even division of or multiple of the wire length in the first coil.
Okay.
So we've got, at this point, we've got 9,000 volts out, and we probably will want to put a spark gap of some sort in here so that we can, and this goes to your earth ground. Okay, the center part of the spark gap will go to earth ground.
Okay.
Okay, and this is going to limit the voltage so that it's within the range which you can handle it with whatever device you're going to load this with.
Okay.
So you can go directly from this into your transformer out here, and it'll be an isolation transformer. And at this point, what you have to do, since you've got a frequency which the isolation transformer cannot use, you have to correct the frequency. So in order to correct the frequency, you put a resistor across the two poles there. In order to determine what resistor size you use, you go to either the American Radio Relay League chart showing capacitance and resistance and other types of things, which will tell you what approximate frequency you'll end up with. Now, in the case of American Radio Relay League, you're going to be off the end of the chart, and you're going to have to take a little piece of paper and make the grid and extend the chart over about an inch or so and about an inch or so down in order to get, say, 60 cycles or 120 or whatever it is you want. But you can do that real easy.
Okay.
So anyhow, we've got through our 12 volts, and none of the electrons from the 12-volt battery have left the high voltage module. The high voltage module has excited electrons in a separate, just like your transformer here, where you have the two sides are separated from each other so that none of the electricity on this side actually goes through the system. And what it does through induction, it excites the coil on the other side, and your electricity over here is coming from the earth grounding, and your load is going to be in between the earth grounding and the other pole of that transformer. And you're going to have to also put some sort of voltage control on this thing here, and that will be a varactor, V-A-R-A-C-T-E-R. And what that is, like on your computer where you have a voltage control thing that keeps the spikes from coming in, it looks like a little capacitor, but it's not.
Okay.
But it basically will limit the voltage to some level which is okay for the device that you're trying to run. Now, what I have shown you here, you don't have to know how to tune it. That takes care of itself for you, and you have to make only one correction in the frequency, and any coil and resistor or any coil and capacitor or any combination of those will give you a particular frequency. Now, Radio Shack has a book on electronic tables and such, and you can use the charts in it.
Okay. Is this the smaller, simplified version?
No, there's some solid state versions of this where all of this is thrown out. But I'm not at liberty to talk about them just now.
Would you like to give us an explanation of the far unit?
Roger, why don't you go right up to them and...
Okay, you want to know about these devices?
Yes, give us an
okay, early on when I started first studying electricity, the first device I'd like to show you will be this one. Okay, if people say that you can't get more out than you
put in, this is a good example of it. It runs off of a 7 amp hour 12 volt battery, and this is a Tesla coil here with the L1 and the L2, and it puts out about 30,000 volts, this central Tesla coil here. So that magnetic field that we were talking about over here, it's all over the area. As a matter of fact, you can go anywhere in the neighborhood, and if you have another coil that's tuned to that same frequency, it will generate the same amount of electricity as the one that's in the center here. So if you notice the little neon tube bulbs here, Radio Shack, okay, what they do is when you tune these other coils to match this one, due to the fact they're slightly different, you have to tune them. And when you do that, those little neon tube things light up. And I'm going to have to use a handkerchief. I had several strokes, and I don't have good control of my muscles in my mouth. So anyhow, you have basically 3 receivers here, and you have one that's producing, and so each of these will duplicate exactly what's here. So we've got 3 times more energy. Well, actually, we've got this one, and then we've got these 3, so we've got basically 4 times what we're putting in coming out. And it's undeniable. And it's if you can build 1 Tesla coil, you can build 3 more just like it, or 100 more like it, or you can fill the whole room up with other ones that match the same frequency. And so that should answer the question whether you can get more out than you put in. But actually, you're not getting something for nothing, because it was all there to begin with. All you're doing, you have a generating system, and you have a collection system, and you disturb the magnetic field around it, which is enormous, and it covers a large area, and anywhere in that magnetic field, it's going to equal whatever is coming out of this one. So if you want to build something which is relatively simple, which answers the question as to whether you can get more back than you originally put in it, this should blow anybody away that might not like what you're doing. So this I built about 15 years ago, and it's survived up to now, so you're getting to see it. Okay, we have a lot more to talk about than we have time to cover. Okay, I want to ask you, does this look familiar in any way?
Tom Bearden,
Okay, this is Tom Bearden's device about 10 years before Tom Bearden knew that he could do it. And this is the one that was in the black suitcase in the 1996 presentation at the Tesla convention in Colorado Springs. It did, there were engineers in the audience that had their instruments with them, and they tested it as producing 120 volts at 80 amps. So this is kind of small for something that's coming out of a 7 amp hour 12 volt battery. So these things become self-sufficient when that happens, because all you have to do is have an extra tap off of the thing there, and that will produce more electricity than is required to run the device. So once you get that initial ignition going, it's self-sustaining. And there's no moving parts here, and if you stay within the tolerance of the parts, it will probably last for a very long time.
Okay. Am I right if I think that one bar is positive?
Oh, you see the one that extra wire that's in there? That's something that Tom Bearden didn't have. But how that happened was I used the wire that you use to hook up speaker systems. The reason for it was the fact that it was multi-stranded. And I thought, well, I would just have to pull these apart in order to get a single wire so that the thing will work. So I decided to leave the second wire in there and turn it into an antenna system for whoop. It's running right now. Anybody care to come up and touch it? It's kind of like touching a thing you poke cows with.
Am I right if I think that one wire is on positive and the other wire is on
Well, what it does, it boosts the ambient background that it's exposed to, so it supercharges it. This thing puts out, well, Bearden was getting a 1.8, I think, on the return on it. Well, this one will get maybe about 20 or 30 times that. And it's probably due to that little antenna wire there that I just accidentally touched. So it's high frequency, that's why it didn't kill me.
Is that a battery on the left? What do we have here on the left?
What's the circuit?
Say again, please.
Battery? Is that a battery?
No, it doesn't even have a battery on it right now. It's running.
Transformer.
It's running at full force. I mean, to tell you, it's like getting hit with a cattle prod thing.
Okay.
And no battery.
I was just.
If anybody cares to test me on that, well, they're entirely welcome.
Clip a million volt to it.
Could you explain the components?
And how this came about, I won't be able to hear you very well, so you'll have to get me later with your questions. But how this came about, you see the toroid that's in there? The United States government bought a lot of those things out of Alamogordo, New Mexico, and they paid about $10,000 a piece for them. And I found a whole box full of them in a surplus place. I didn't have the slightest idea of what they were or what they were used for, and I didn't know what met glass was at that time. No one else did either because it was highly classified, and when Signal and the other people declassified it, well, that's the first time I realized what I actually had, because what they what this is, it's a toroid, but you make it with tape of, it's a metal tape, silicone steel type thing, and you wrap it around a form, and you get any size or shape or form, whether round or square or oblong or whatever, and that's how you get the toroids. I have some of these that are 14 inches in diameter, and they probably cost the government probably $500,000 a piece, and I've got 6 of them. And in my website, you'll see a large round toroid that's on a little push cart, and it's got a Tesla coil built on that thing. Well, what happens there when you do that, it's a cyclotron type deal, and once you get the electrical field circulating in that closed system there, you can put other coils around it, however many of you want, and you're not taking electricity. None of the electricity that started out in the system ever gets through it. It's the point A and point B thing where you get electrons jumping up and down at point A, and they do not go from point A to point B. At point B, they jump up and down in resonance to the ones at point A. That's your resonant energy type thing. So once you get the resonant energy type thing going, and you get the magnetic fields going and that sort of thing, well, you can tap off of that system without taking away from it. And you can take off as many other coils as you can get into the area or onto the system. You can take that much off, and it's not affecting what's being put in any respect. And it's highly obvious, and it also people will tell you can't do this sort of thing, but you've already seen one example here when I got shocked just a minute ago. And in a coil system, like in a normal Tesla coil, they're normally high and skinny and that sort of thing. That's the wrong way to go if you're wanting amps and stuff, because the length is volts and the diameter is amps. So if you get the right combination of this versus this, then you got plenty of amps and plenty of volts. So, and also, depending on how you tap onto the coil, will determine whether you get amperage. But there's the same amount of amps there as there are volts, because in the magnetic system that's driving it, it has to be equal and opposite. That's your Lenz's law, you know, it's equal and opposite. So that means that your one of those is your magnetic or your field, and the other is the electrical field. And the magnetic field is amps.
Okay. And what about bipolar coil?
On the
bipolar coil.
Bipolar coil.
How does it magnify? What's the ratio? Okay, whenever the center of the pancake coil is a certain size, and the outer ring is a certain size, and then the L1 coil is maybe a couple of turns on the outside of it. So the ratio of the diameter of the inside versus the outside turn on it is the improvement or the advantage that you gain by doing it that way. So in the one that's in the picture in the book there, the ratio is 1 to 5. So not only do you get the L1 and L2 gain, you get 5 times that. So that's the advantage of pancake coil.
But they are one wire or B wire?
The outside, well, the L1 wire should be an even division of whatever the length of the L2 is. That way they're able to talk to each other. The frequency, if you worry about the frequency, don't worry about that. Just build the thing so it looks nice, and make an even division, even multiple or even division of the lengths of the wires that you want to talk to each other, and they'll be talking to each other.
What's the ratio?
The ratio in the case of the one that's in the book is 1 to 5. So it's 5 times what, plus the fact that it's a normal Tesla coil. Your normal gain times 5.
Do you ever do quarter of the wavelength like Tesla did?
And what?
Do you ever do quarter of the wavelength like Tesla did for his coils?
They will be able to talk to each other, and you can calculate the wavelength because you take the speed of light and divide that by a certain factor, and that will tell you how long the wire will be for a certain frequency. What I did on that particular one, I used about 200 megahertz, which meant the wire was going to be about 18 to 20 feet long. I think it was 18 something, and then once I had the main frequency set up, then I made the other coil. So, and as long as it's a even division or a multiple of, whichever way you go, they're going to talk to each other, and that's all you need. Okay, there are a lot of different things. This thing's a little bit heavy, and I see it's got a lot of sawdust on it because it was sitting. Let's see which way to turn it. We don't want this to fall out. Can you see it okay?
Yes.
Okay, you notice that this main coil there has the center part of it cut out, and the two cut things are brought over as your ground deal. Okay, and the ends, the electrons are spinning one direction going this way, and spinning the other direction going that way. So you got electricity and you got amps. And when they come together, then it continues on. So you put the two together, and you've got more amps than you know what to do with, and more electricity you know what to do with. So it has to be cut back. This is a diode bridge here. You go in and out of these inverter systems. Since this thing has to run on alternating current at 120 volts, in order to get to that from the battery, I had to use an inverter, and people make fun of me because I use Radio Shack inverters, but in this case, the high voltage thing there has to run off of 120 volts at 60 cycles. So that's how I get to there. Now I've got a rheostat here where I can raise and lower the input so that over here it comes out the correct amount that I want. And on the this is 8,000, well, it's 2,000 volts each. So it ends up being like 8,000 volts. So I have to be careful not to get beyond that. And they're 8 microfarads each. Now I have some 50 farad capacitors, which are newly available on the market, and they actually go up to well beyond that. But the trouble, the way they manufacture them today, they are down in a voltage level which is too low. So by paralleling them and other ways, you get up in the voltage range that you want.
So you use a supercapacitor?
Yeah, I have several of them, and I use them in some of my larger units. And I mean, tell you, one like this, if you stick a screwdriver in there while it's running, about half the screwdriver evaporates. I know it makes a noise, it'll unnerve you and the whole neighborhood. You'll have everybody in the neighborhood for blocks around. They're running outside to see where the explosion was, and you'll end up with a screwdriver with a handle with just a little bit of metal left on it.
Why do you have the cap, the white cap on one side of this?
What is he asking?
Well, the capacitor on your LC.
Why that one there?
It seems symmetrical.
When I got to that point, it was out of tune. So I had to do some tuning on it to keep it going on. And the reason for this is it's also a tuning mechanism, but it turned out when I got built, it didn't really need very much tuning. So I never really had much. This is your old slide radio thing, or your tuning antennas, and the L1 is the red that's on the inside there, and this is your L2 system. But it's a double one set up so that the amps and volts and everything are in there in a proper order. And this one I built in 1994. So, and there are over 200 of these different devices in existence right now, and the more recent ones are subject to business deals and things, so I can't show you them. But the idea is to try to fix it so that you can get the idea and you can build your own. And actuality, I had something in my briefcase that I wanted to give you because everyone wants schematics. And this particular one was so simple that it was ridiculous. And what I'll have to do is just give it to Bruce here and let him post it. Because I actually ran out of ink printing the darn things up to bring over to you. And then I apparently walked off and left them. And I had a lot of help this morning in getting here, and that's why I was late. But anyhow, how are we doing? We have how many minutes? We have
60 minutes.
Another hour? Okay, well, we can still do it. So this is, let me tell you about these. People were asking me about them, and they're not something that you can buy. They're not in a catalog anywhere. And when I called Cornell Duvier and asked them, do you have this? And they're very high voltage. If I remember correctly, they're about 10,000 volts. And they're 0.5, if I remember correctly, 0.5 microfarads, which by anyone's, they're difficult, they're impossible to find. That's what I'm leading up to. So Cornell Duvier asked me what I wanted them for, and I told them I needed them for research and development. And they said, well, how many can you use? And I said maybe a dozen or so, and they said, well, they're I think they were $300 or $350 each, and they said, well, fine, you'll be hearing from us. And I forgot about it, and about 6 months later they showed up in the mailbox and for free. Compliments of Cornell Duvier. So I've found out how to work that system now, and so I've got a lot of things which don't really on the market exist. They exist in people's minds, but they're not. There's not a demand for them. So that'll give you some idea about it. Now these diodes here, again, like I said on the Tesla coil, the length is the voltage and the diameter is the amperage. Well, the same thing holds true on diodes, and it probably holds true on a lot of other things. So these diodes are long, and these are 25,000 volt diodes. So they give you some idea. So everything that's in here is probably an overkill, but the results are real interesting, and it does work. So
the device right beside the cap, is that the spark arrestor?
Right, the device beside the cap.
what that is?
Yeah.
Okay, a lot of your electronic devices have things which control the voltage, you know, like spark gaps. That is a radio frequency spark gap. It's used for lightning arresters on computers and things that are sensitive to voltage. So if lightning hits, well, anything over a certain amount will go to ground. So that's the ground post on that high voltage thing there, and so I'm grounding it back into itself. So when it's running, that flashes. You see the flashes in it all the time. That's like my little neon things that I use to check the circuit with, so that a lot of times I'll put them in different places, and I know up to that point that everything is okay, because when it's running they light up. So that's getting pretty heavy about now, isn't it? Okay. this device that you see on the slide up here, and all of these things, you have a dipole type deal where you have minus and plus and so on and so on. So if you have a situation like that and you interfere with that with some sort of collection device, then you've got a generator. So you'll notice that there's nothing, no input on this except the ambient around it. And if you go back to Faraday in the very early days of the Faraday generators, they were basically magnets with some sort of something that would interfere with them that would cause them to kind of go off and on. Well, in this case, the plus and minus are on the poles of the magnet, and you're interfering with them in a certain way, so therefore you're getting 700 volts. And this is straight out of the air with no, you see the little antenna things like that second wire that I have on my other device? Well, that winding up there simply is taking from the air, the ambient background, which is enormous. If you do the calculations, Seraway's university textbook for professionals in college physics, Seraway, and whenever you're attempting to intercept it or intercede, and of course, in order for it to work, you have to have more of something, and it has to be less somewhere else. So, and you have to, the leg in between the more and the less is the active system which you're going to be using to get your useful energy. Because as these things are working right now, the energy is not useful, but you have to do certain things to them, and you can measure what's going on here, but you have to have there's 3 or 4 different components that have to be in there in order to bring this down to where you can actually do something with it. And you can work it either from the backside into it. If you know what you want, then you can back engineer it through the system, or you can come the other way and put controls on it so that you can control the output on the other end. And also, you need instruments that will work with radio frequency. The reason for radio frequency is that the more of these up and down things you have, it's whenever it changes direction there that it throws off either a magnetic or electrical wave. So on the electrical side, you're pretty well boxed in, and all the rules and the books and things, you're in Ohm's law and all that sort of thing. If you're in a closed system and you're boxed in, Ohm's law works, but if you get over, and that's on your electrical side, but when you move over onto the counterpart of it, the magnetic side, none of those laws apply. Right. And it's a whole different system, and most of the critical information there is missing intentionally. So, in effect, what you have on the magnetic side, you can make as many copies of it as you want without depleting the source. And that's where your units that you're interested in, when they work. If you know that, then you can just turn your nose up at those people that are trying to make it on the electrical side, because they require very low temperatures and a very complicated situation, and it's got you where you can't really do what you need to do. So if you're intent on doing it, stay off of the electrical side as much as you can. Grounding works in several different ways. People think of earth grounding as being something that goes into the earth. Well, the Earth's atmosphere is also part of the earth, So you can have air grounding, or you can have ground grounding, and in citizen band radios and the ones that are in the automobiles moving around and things like that, they frequently are grounded into the metal body of the automobile. So, or if they're not that, then in actuality that antenna that's sticking up there is grounding into the Earth's electrical system, and that's why you can pick up the radio station a long way off, because it's interfering with the magnetic system and it's sending out these waves that are different than what's normally there, so it's upset the electrical and magnetic balance, and that's why your receiver out there is receiving it.
So then we could just you see, the next one I have is like, where you're working on anything to produce a fuelless aircraft, but that relates back to the ground. But if you don't have a ground, then you can use the car as a ground.
Well, when you're flying in an airplane and they have electrical systems, they're grounded into the metal parts of the airplane.
Right, and to drain off the stack and everything.
Yeah, and it radiates off of that. Yeah. So grounding is a relative sort of thing. It's that there's more of something here and less of something here, so it's going to move between the more to the less of something, and it's that leg that's in between there that's your useful energy.
Okay. Now,
see what goes on here.
Don?
Okay. This is a piece of material like same kind of chemical composition, say as met glass or piezoelectrical type material, or what, maybe a rod, and of any size. It might be this size or this size or whatever. It depends on the amount of energy that you want out of the thing. So I'm working backwards on this. Okay.
10 kilowatts, enough to run a house.
In order for the system to work, you have to have off and on. It has to turn off and on. So what we're going to do is put a this is not exactly the symbol for it, but it's an NPN resistor, and this is the base. Okay, and let's see, I forget which way the arrows point here, so I'm going to leave the arrows off of it. But what happens, this is your input here, and this is your output here, and it comes over, and well, this is not going to be very pretty, and then this comes back here, and then okay, on the base down here we have a resistor which is controlling our timing device, which opens and closes the gate on this transistor, so that what's coming through here is going to be a certain frequency. You're setting the frequency there, and this is the first coil. Okay, there's a second coil or a number of other coils which are up here. Okay, and what's happening is the magnetic flux in this piece of metal here is set up such that any amount of coils you put up here will duplicate whatever's being put in here. So we have our input. I think it comes like this, and we have this one. There's another deal here, and this is going to be your negative side, and this okay, no, this is a negative right here, this is plus, and this is plus here. So this negative one here is coming back over here, and the output, this is your output here, and this is your main input here.
I have a question. In this, you have these two shorted together. Is that the right? Or does this end up going?
And this one goes around that one, and this one. Let's see.
Yeah, I just want to make sure because this looks like.
You want to know where the.
Well, it's interesting that this is shorted together up here. That it's completely shorted to this plus.
I won't swear that this is 100% correct, but the one that you will see later is. But I think it may look illogical there in a place or two, but I think that's pretty close to correct. But you'll know later.
So have you come up with any new devices other than...
I come up with about 3 or 4 days. I don't often have time to put them together. But I can say that once you get off onto something like this, that every one of them leads to something else. There's no such thing as one of them. It's kind of like a cat that wanders up at your house. There's no such thing as one of them. But at this point, someone had some questions a little bit ago that wanted to come up and ask them. Do we have someone else that would like to come up? Okay, where do you want me to stand? On this one over here?
This one has L1 and L2.
The smaller one that's larger around is the L1. The middle coil is the L2. Okay. And that's just for convenience in naming them so that you know which one is which. And it's very possible that this thing is not tuned into that. That's the reason why it's not acting up. What made this one act up was this silicone steel toroid there.
Is there a magnet inside, like in
No, it's the toroid in there. It's a toroid that's been flattened. Instead of being round, it's kind of rectangular. But how you make those, it's made that shape because it will fit into a particular component in some device. If it's big and round, it's going to take up more space. So by making it shaped like that, it will fit into, they will bite you, at least they were a while ago. I don't know whether they're doing it now, but it definitely bit me.
What is the frequency of this device?
What is what?
What is the frequency?
Frequency of it? Of this particular one? I think it's 55,000 cycles per second. Is that the question?
Yes.
Okay. Frequently, when you build something like this, you end up with a frequency that you hadn't planned on, and when you work it out on the electronic programs, it will frequently turn out something different than what the program says, but they do kind of haunt you, so they're nice to have. Okay, we need probably, please come up. No. I bet you have a question. I'm sure I haven't answered everybody's question.
Well, I have one myself.
Okay.
I've been really curious about this since you showed this leg
right. What I've done there, two of these wires here normally come off to another system. So you're not seeing the complete system. You're seeing the main part of it. But I build parts of these systems on different little blocks, and then when I hook them up, well, I've got the whole system there. Now this has all of the different components on it, which sometimes, say this part over here, and and this part will be on different blocks because I can use them interchangeably with other things I'm doing.
Is there a reason for this leg being disconnected?
Yeah, well, you notice that those two are loose. That's probably why it quit sparking there. This thing was, whenever I sit it down in a certain way, well, it closes the system. And I noticed that when the fellow came up just now, it wasn't doing that, apparently. But whenever I tested it, it did.
These windings on the inside are...
If you look close, you can see that's like it's metal tape.
Right.
It comes on a roll, and they roll it around a form to get the shape they want, and then they dip it in shellac or something, and it stays put.
These coils, are they mirrored to each other?
Well, they're layers just like Scotch tape.
Right.
You know, they're and when they dip it in the lacquer stuff, well, they put it in a form and they keep it there until all that dries. And when it's dry, well, it's ready to be used.
This is something similar to this right here?
Well, they all do the same thing. They look very different, but basically it's your bucket for dipping the water.
Okay.
Is that it?
Going back to the circuit here, yes, input and output. Can you make a comment on the number of turns used?
The output will be a ratio of the number of turns on the first one versus the other one. So if you had like 2 or 3 on the first one, and you put like 10 or 20 on the other one, the output improvement would be the ratio of the first one versus the second one.
So there's no magical number, say 1 to 5, or there's no magical number, say 1 to 5 that works better.
Yeah, well, the thing is, you want to make as few of them as you have to, because it's real hard work, you know, winding those things. And not only that, you want to do it in such a way that you can slip that rod out and use it with another device. If that one doesn't live up to your expectations, after you make the second device, you've got 2 points to work off of, so you know which way to go for the third one, and the third one you should hit pretty close to your target.
Thanks.
Okay.
Build the circuit, or any of us build the circuit you show there with the 1 transistor? Okay. We can't use this to...
you can use it to a certain extent. What you do, you run that... You can set your own frequency on that transistor.
Right.
By the base deal there. The timer that you use on the base deal is opening and closing the gate there.
Yeah.
And you can pick whatever frequency you want. So you can run it at frequencies which are in your test instrument capability, so you don't have to go out and buy a radio type test.
Just lower it down.
Yeah, just lower the frequency into the range that you can handle, and you're in business.
I can handle 60 hertz.
Do you advise that?
You got it.
That's what I want.
Okay. Actually, by these quick swings of alternating current and that sort of thing, the flux, the magnetic field switching off and on, and they're actually into that right now, and by using square waves and pulsing them, they get a very noticeable change in weight of any metal device that they feed that into. So they're actually getting heavy pieces of metal lifting up and moving around. Okay, I think I dropped something there, but I don't know what it was, but it doesn't matter.
On your circuit, the base of the transistor, were you driving that with a square wave?
Well, it depends on the transistor. There's about 9,000 different ones, but they will give the characteristics of that particular transistor. So whenever you look at a chart of them, you'll be able to pick out an ordinary NPN will work on the square.
Was that a square wave you're driving it with?
Yeah, it's just actually a square wave is just simply this with the things chopped off. So it's actually the part of the energy there is being chopped off of it. So it's still this, whether it's square here or square here, and so. Yes. Oh, that's what it was. It's still hurt? Okay. Yes.
Okay. You got a part number for the transistor?
NPN is all you really need to know. You go to Radio Shack, and that's a generic description of it. And the N means something in each case, and the P means something. So NPN means that it simply will work with alternating current.
How about the resistor value? The value of the resistor?
Well, as long as it will work within the voltage which you're going to propel it with, and it says on the package it's good for 25 volts or 100 volts or 3,000 volts or whatever. And as the voltage goes up, the price goes up. But you can get them for any amount and that sort of thing. Basically, if you take basic system, would be like a north-south deal, like in your Tesla coil, where you have a north-south component, and take a right angle off of that, which would be similar to the rings of Saturn. And off that, you take two plates, one aluminum and one copper, and put spacers between them, and you can copy your energy directly from your Tesla coil in large amounts.
Don, when you say large amounts, you have a figure?
Well, on the experimental ones I did here, I used plasma tubes for my north-south component, and I was getting 65,000 watts off of that. There was milliwatt in and 65,000 watts out.
Wow, that's really incredible.
You know, it's basically unbelievable, but what people don't allow for is the fact that in your electrical system, it's dead on arrival, so to speak. It's absorbed immediately, but the magnetic flux elements are perpetuate basically forever in great quantity, except when you have lower frequencies. So you have to run the frequency up like Tesla coil maybe, and then you bring it down into direct current from the system with the rings on it that I was talking about.
So the output is high frequency at first, and what you're doing is convert it into direct current, and then you could probably put an inverter on there, say?
Well, the north-south component is electrical, and the east-west component is your magnetic flux, which, when it's captured on those rings, changes back to electrical.
And it's based on a dipole system. Could you explain maybe the transformer and how?
Well, the invention is called dipole transformer generator. The dipole is a north-south component, and the generator part is your Tesla coil deal, and the other part, you have a generator and you have a receiver type deal, so it's a generator receiver.
Do you have any designs or drawings that are available? I mean, did you submit a patent application?
Basically, as simple as I've described it here, you don't really need anything else. It sort of explains itself when you put it together. Do a simple Tesla coil, and at right angles, like the rings of Saturn, place these my mind's going sideways. You have to place the plates on the ring knot deal there, and separate them so that they're not shorting out, and then measure between the two plates.
Okay, and when you measured the total energy output, or the power, what you claimed was the power output was 50 kilowatts, what did you use to absorb that? Did you absorb it into like a dummy load, for example?
First of all, you have to change it. It's a radio frequency, and you have to change it to pulsating DC, and once you've done that, then you can use it just like ordinary electricity.
I'd like to ask, what is the function, and what can you describe what really happens in the spark gap?
What's really happening and why it works?
Well, specifically, I want to know about the spark gap.
The spark gap is a very important thing. That's why the Tesla coil thing can be part of it. You have to have the off and on component present in any situation where you're switching between magnetic and electrical flux.
So is the
if you're not switching there, you're although you're getting an electrical component which is used up almost immediately, the magnetic component has no bounds on it. It's an open system where the energy can, depending on the frequency, can travel throughout the universe. And at that point, you need a system to harvest the useful energy, which would be the magnetic flux, which when it passes an electron, it flips back, and you have an electrical component given to you, and you can have as many of these sets, duplicate sets of energy as you want. There's no limit to them.
So your concept is that the electron kind of flips between two states, or
yes, the electron flips between the magnetic and electrical impulse, and it sends out waves, and the magnetic waves are not quenchable like the electrical component is dead almost immediately. It's absorbed, but the magnetic component is not absorbed. It's either reflected or deflected, and at that point, when the magnetic component is passing, it flips additional electrons, which would go back to the electrical deal, and that way you have an endless output from the magnetic resonance, and that's why I call my devices the resonance energy methods.
To get back to your device that was in the book, use the L1 and the L2 coils.
Okay.
Are we talking about a different device now?
I have dozens of different devices.
most of which you've probably never seen.
Okay.
The dipole transformer thing I'm talking about, you've never seen it, most likely.
Okay. So that's very different than what you had published in your book then?
Yes, they all work on the same principle, however.
Okay, and that's based on this understanding of the electron and how it really functions.
Yes, and what the magnetic flux, how it differs from the electrical flux. Magnetic flux is not quenchable. It doesn't die out. It basically is unstoppable.
Okay. Now,
and each time it passes another electron, it flips it, and the energy from all of those electron flips added together ends up being a huge amount greater than what the electrical flux could provide.
Now, when the electron is sort of excited into the electrical mode, does it have to be near a wire or something to collect that?
Oh, let me say this. Most people don't realize that every electrical device that you have, regardless of what it is or where it is, and that sort of thing, is giving out a huge amount of magnetic flux along with the electrical flux. And most people think that it's inconsequential and it doesn't really mean anything. But if you have a Gauss meter and you map the electrical flux area and then do this right angle component on it, like I was talking about, you can turn any device into a generator of electricity.
And physically, how big would this machine be for comparable or particular size output?
Comparable to what?
Well, if you pick a number in terms of kilowatt output, how can you...
Kilowatts, what's the potential? It depends on the electrical output of your dipole system, which we agreed that you could use a Tesla coil, so they come in all sizes.
Okay, so if you had, say, a 10 kilowatt generator, how big would that be?
It wouldn't be very large at all. It'd probably sit on an ordinary desk with a lot of room to spare.
Now, in your book, you said that there's kind of a magic number of 20,000 hertz, above which things seem to change in terms of the way electricity and magnetism seem to work. Would you explain that a little bit?
I didn't completely understand you.
Okay. You said that above 20,000 hertz, when you get a frequency above that.
Okay, the higher the frequency, the more often your off and on component is coming on. So each off and on component is added to the composite of the energy that's present. So if you're like 60 cycles, you're not getting very much. If you're like 400,000 cycles, you're really beginning to add up. And when you go up to about a million, the curve on that type of thing is about a 90 degrees slope, I guess, when you get up to about 200,000, and then when you go above that, it goes to almost straight up. It's infinite from then on.
So is this obeying the square law that you said in your book?
Say again, please.
Is the output proportional to the square of the frequency? Is that the concept that you're talking about here?
Yes. Whenever the frequency goes up to a certain level, the energy is infinite. It's you're basically plugged into the universe, I guess you might say.
Now, is it necessary that this high frequency be also at a very high voltage, or does it not?
Well, the voltage, of course, is a variable, but once you get up into the higher deals, in order for it to be useful, you have to bring it back down to pulsating DC, and then you can change it to 60 cycle or whatever else you want. Because at high frequency and high voltage, which is the basic idea, you don't have good control of it, and you have to change it to something which you can control better.
Okay, now, also in your book you mentioned about this magnetostrictive rod at one point.
Yes, magnetostrictive rods. Okay, the curious thing about electricity is the fact that whenever you have magnetostrictive materials, the resistivity becomes enormous. And basically it's like when you, I can't think of what I want to say just now, but it's playing a trick on materials, and it's the exact opposite of anything that would conduct electricity.
Okay, now when you put a field around one of these rods, it in effect...
The fact it doesn't conduct electricity, it becomes a perfect conductor for magnetic fields.
Okay, so you put a magnetic field around one of these rods and it actually grows longer, right, by a little small dimension?
Say again, please.
When you put a field around one of these magnetostrictive rods, the rod physically...
The idea is to put the magnetic field there, and it's... they talk about getting zero resistance or even more so. Well, in the case of magnetic stuff, you have this way beyond zero. It goes into the millions of times on the zero side, where if you did that electrically, you couldn't do it.
So the magnetic component
works just the opposite to the electrical.
So instead of having, as we would think of ohms resistance in something, you have actually an enhancement of the magnetic traveling through this rod?
Yes. The idea is to get make the magnetic field work for you.
Now, when the rod sort of, as I picture this rod, it goes through a cycle every time you change the field around it. It goes from... Okay,
that's your off and on component you were asking about. You have to have something that's breaking the circuit and alternately, and that's necessary in order to start the action.
Okay, and these rods can accept a very rapidly changing magnetic field?
Yes. They have enormous magnetic field. That's the reason for using them.
So when you pulse this rod and make it go through one cycle, it takes energy in and then it gives it back to you in a different form?
The idea is that you're taking something out which has some resistance to it, and you're putting it into a system where the negative resistance is almost infinite, and at that point you're swinging the system around so that you're taking advantage of the negative resistance.
Okay, I'm beginning to piece this together a little bit here in my head.
By the way, those drawings are to give the general idea. They're not the absolute way to do it. That was the simplest way I could demonstrate it without getting overly complicated.
Okay, I understand that. That's part of the art of this whole process. Huh?
Yes. Everything I do, I try to simplify it as best I can, so it may look like I'm a fool, but actually I've been very careful to try to make it so people can understand it. If people don't understand it, it doesn't mean anything.
Are there other devices besides these magnetostrictive rods that make sense?
Actually, I have a system which I don't want to talk about very much, but I can take the magnetic field and convert it directly into energy without going through all these gyrations that we were talking about.
Can a simple air coil do that?
Let's see. I'm trying to figure out how to tell you what happens without giving my secrets away. But I take an actual magnet, and just like it's a battery, and I take the energy directly from it, and the idea there is that the magnetic flux or the magnetic field is embedded into the magnet, and when you take it out, it supplies itself immediately, so it always maintains the same level regardless of how much energy you take directly from it. So one of my inventions, which you don't know about, is a device which uses a magnet directly without any complications much, and takes the energy directly from it in any amount you might want.
My question is for your magnetostriction rod. I believe, if I remember the diagram, it was similar to an autotransformer in resonance.
Okay, I'll tell you what that is. That's the basic thing that's used by the submarines for their sonic system. It's identical materials and the wiring diagram and everything else. So when you have a submarine and you're listening for like 50 miles away, and it comes back and you pick up the energy and you can see what's out there. It's the same energy system that the submarines use.
Oh, what frequency works better? Because I mean, different.
Frequency?
Yeah.
It's magnetostrictive material, which I would get that the frequency is probably about 50,000 cycles per second.
Okay. Yeah, in your book.
Depending on the chemical composition of the particular material rod, I might tell you that stainless steel rod works magnificently.
Would this be a hollow stainless steel rod then, or solid, or?
Stainless steel has a dielectric component in it, and it's very sensitive to magnetic things, but not very sensitive to electrical.
In the latest issue of Faraday Labs magazine, they do a time machine experiment, and they use magnetostrictive material. And I just thought that was...
Basically, depending on the size of the object and how you're going about it, it works just like a big Tesla coil, so to speak. The mechanics of it, or what's happening, is related to the one coil and the two coil and the Tesla coil.
This type of device normally it has an enemy of heat. If the heat is involved in the process, it kills the magnet system off. So we had to have a device which did not have that heat killing aspect in order for the magnets to continue on for long periods of time. In this system, the way it's constructed, the magnets will last basically forever from a human standpoint without needing to be replenished. But
what most people are not aware of is the fact that these magnets have hundreds of Gauss in them, and a Gauss is an energy equivalent of about 100,000 watts of electricity, and that's on the basis of a temporary exposure. When the system rotates, it has a shielding thing inside it, which breaks the magnetic contact in part, and by constructing it the way I do, it doesn't kill off the magnetic system. And this is when I was developing a shielding device, I had to make it myself because what we have there is a sheet of plastic, and we take the cover off the paper cover off the sheet there, and we spray shielding material, powdered metal shielding material over the thing after spraying it with rubber cement. And I do several layers of that, and the part of it is going to be when you pull up the mass there, the center part, which you see right now with the paper on it, will disappear, and so will the shielding material, and there will be openings inside the mass there that allow for the magnetic flux to pass through it. Okay? You're seeing the same thing up closer, and there's going to be a point there where we can pull some of the shielding material off, and you'll see how it works. July the 4th with a huge cause that he builds, and all the news media and everyone from all over the world will be present for that, and I get a front row seat. But he's building a very special testing coil for me, and it's actually 3-layer testing coil, and with one energy source running 3 coils. It's 40 inches in diameter, and the wire is much larger than your thumb here. It's a type of welding cable, and it's multi-stranded. The reason for multi-stranded is that it causes the magnetic flux to multiply in such a way that is very beneficial. So this type of coil, the diameter of the coil divided by the diameter of the coil times the number of strands available is the multiplication factor in the coil set. So if you put 500,000 watts into it, the magnetic flux will end up being, say that it has 30 turns on it or something like that. We'll be having approximately 30 times the output in usable form, magnified to the 30th degree. Okay, this is a diode bridge that goes with the flat coil we just saw, and it was built since the frequency at which this thing is running is down within an easy range of what diodes can do, that sort of thing. You can actually extract the energy very easy and see the multiplication factor. This is a pressure-sensitive type device, which when you put pressure on it, it generates electrical field. And with that in mind, most people don't realize that electrical current or alternating current coming into something like this is the same pressure type deal. So you're generating electricity with a piece of solid state device. And the project, if you follow the put it together, and there it is complete. So the idea was I put energy into the center part there, and it was producing energy out on each side there, a great deal more than what was put in. For example, if 5 volts was put in, it might have 10,000 volts out, that sort of thing. So you got 2 sides there, and times 10,000, that's 20,000 volts coming out of that thing. And what really happens there is that volts and amps, of course, are very different things. But amps only occur when you have a grounding. So in order to turn this into useful energy, it's the way in which you ground it will determine whether it becomes a practical source of useful energy. But it turned out very successful and a very high rate of amplification. And we'll look at some more parts when I was putting it together. Okay, this is a diode bridge which I designed myself for my plasma tube experiments. In plasma, if you have a way to measure magnetic flux, which there's a number of ways, plasma tubes put out such huge amounts of energy you can't believe. So you put maybe 20 volts in or 10 volts in or whatever, and out of the plasma tube, it's eliminate the energy coming out is maybe 50,000 or more units of energy that's going in. So a great deal more than that actual. So if you have a way to capture the energy from the plasma tube in a practical way, and you work it down in the frequency zone where the diodes work for you instead of against you, you can get a lot of useful energy directly from the plasma tubes. Go ahead. This is sort of a stranger got in between. It's one of the 200 or so devices that I told you about. Go ahead. Okay, this is inside of one of the more sophisticated zones, and that thing in the center there with the coils on it was intended to correct the frequency so that you could control it properly. And it turned out that I had calculated everything such that it didn't need that part of the device. So go ahead. Okay, this is where the energy passes through one side of it there. And the magnetic flux feeds onto a secondary coil there, which is the feedback coil, which means that the device, once it's started, it can run on its own and generate electricity basically forever. Okay. There's some more views. Go ahead. And more views. And that's the details on some of the capacitors and things that are there. Go ahead. Okay, this is a device which you'll recognize for measuring DC current, flux, DC flux, and it's something you use in combination with several other instruments. Go ahead. Okay, this is a high voltage, a high frequency device for measuring energy. Go ahead. This is one of my early devices with the shielding material on it, which keeps the
flux inside the box. It's aluminum. Okay, this is one of the plasma tube devices with the double bridge thing intact there. And back up, Mark. Okay, see that pyramid there? The people in Egypt there and their pyramids back several thousand years before Christ had energy devices, and what you're seeing there is a photograph of the energy flux in the area of the pyramid, and it's enormous. And the triangular shape is what contributes to that. And the base material there would be one type of mineral which had electrical characteristics, say, of one type, and then the pyramid itself is made of another kind of material which has a different electrical component. And between the sand which is sitting on and the pyramid material, which is a different material, and the triangular shape of it gives us this energy flux. And mountains do this all the time. If you're in the mountainous area, you can see the electrical display coming out from the mountains. So the triangular type system relates to the energy which you see in mountain chains and such. In Central and South America, you can see that quite good at night. It lights up as a type of lighting which comes from nature. Okay, Von Däniken built some of the electric light bulbs that were shown in the pyramids, and they worked. It's documented in all of your information sources. But he actually shows photographs of electric light bulbs which he's duplicated, which look exactly like the ones the Egyptians were building 3,000 years ago. So electricity has been around in useful form for quite a while, and we just didn't understand it, and we're getting to the point where we're beginning to understand it. When you leave here today, you'll have a much better view of what's out there, because you're not getting something for nothing, and you're not creating anything. You're just simply changing it from one form to another, and in that change process from one form to another, you have useful energy. If the energy is static and not moving, or is mass, or other forms of energy, you don't really see anything useful. It's only when it's going from one form to another that it becomes useful. And you capture, just like the water running down from the mountain to the back to sea level. In between, you put a paddle wheel there, and you've captured the energy. And this is true of all forms of energy, whether it's electrical or whatever. Okay. This is one of many, this is 14-inch Tesla coil which I built and engineered. And unfortunately, when I got it built, if you know how to place the coils, Tesla coils have a lot of useful energy. And in this particular case, it was totally engineered from a computer before I did it. And what increases the energy available there would be the diameter of the coil, the amount of turns on the coil, and a number of other things which will tell you what your amps and volts and things are going to be. This thing came out, when I finished it, I got a surprise because the computer program is very wrong. But it was very wrong in a way which meant I would never be able to use the coil, because there was so much amps that the thing would burn up like a flashbulb. So I calculated everything and checked it before I turned it on, and I found out that I'd built a device which would be like a flash bulb if I turned it on. So I actually never got to use it. A big disappointment. Okay, we can go ahead. Okay, this is one side of the pancake wall again. Some of these have a sequence, so we just skip by them as we go. This is a set of light bulbs which had 10 100-watt bulbs in it, which I demonstrated at Tesla convention back in, I think it was 79 or somewhere along through there, and it caused quite a stir because they had the thing turned on. It was running at full force for a better part of several hours, and based on the amount of energy there, it would have only lasted a few minutes if it was not something unusual. And it caused quite a flap, and to this day there are people that still talk about it. Okay. This is one of the couple hundred devices I've done. And this one on the blue part down there is where you plug into it, and the output is over on the output. The input is over here. See, it's 12 volts. And here's the output. It's 120 volts at however many amps you want. It was good for about 4 or 5 kilowatts continuous from a 12-volt battery. So that must tell us something. And it's not something for nothing either. It actually happened. And someone bought this from me, by the way, and paid me good money for it. And they took it home with them. And you can see on it, you can see every part of it. There's no need to tear it up to find out why it works. But they did tear it up, and they got, when they couldn't put it back together and make it work, they got very upset with me. So I told them that if they would give it back to me the way they received it, I'd be more than happy to give their money back. To this day, I've never heard from them. So that was quite some time ago. Okay, we can go ahead. Okay, these are, you notice 500 microfarad coil there, and another coil set. Those are just some of the things that I worked with at different times. Okay. This is a capacitor set. This is 35 kilowatt device we're looking at here, and you'll see it from several angles. Go ahead. Okay, this is a 50 kilowatt capacitor, and I have them this same size, this shoebox size, by the way. I have these from several manufacturers, and they go up to about over 400 farad. 1 farad is equal to a kilowatt, so that's each farad is equal to 1,000 watts of energy continuous. So the airplanes and the other things that I'm involved with use this type of thing in order to run electric airplanes and various other devices, and very, very successful with it. Special device you're being introduced to here, which takes in, see the metal rod in the center there. You can't see the metal rod, but it's inside the plastic, and we'll see some more photographs of it a little bit. But this is where you use it's from the submarines where you have a resonant device, a resonant rod. In this case, it's terpinol D. And these things are $3,000 each, and I had about 4 of them that I was playing with at the time. And this is one of the devices I built with it. And basically what it does, those are capacitor plates in the center there, and a right angle component of electrical, the magnetic flux is useful energy. So those rods are set at right angles to the magnetic flux put out by the terminal D rod. And this is about at the frequency it's working at and everything. We can use smaller cables, which might surprise you that the energy present there is about 50 kilowatts. And your input is maybe about 20 or 30 milliamps with 50 kilowatt output. And that should get somebody's attention. And the device does not exist. I have a patenting thing in process, and I work through the European Patent Office and the Russian Patent Office, and one's in China and several other places, and avoid the United States religiously. So it's a new technique, and it's a new system completely, and it works magnificently, and it appears to violate a lot of laws of physics. But it was based on the fact that terminal D was what the submarines use when they make their sonic signals that go 50 miles out and come 50 miles back. And sound is a form of electrical energy, magnetic energy, and just like radio signals and a lot of other things. It's just a different wavelength. Okay. These are simply, if you notice the devices here that tell you that there's magnetic flux present, I use those, and I have very sophisticated instruments also, but I follow the magnetic flux, and anywhere there's a large amount of magnetic flux, I consider a source of usable energy. Okay. Okay, this is something you're going to see me use a little bit. When we get through the speech, we're going to demonstrate the ambient energy background and the amount of it out there where you can visibly see what I'm talking about when I say that all this energy is everywhere all the time and is available to you. And it's a very simple process to collect it. And I'm going to show you how that happens. And that's coming along at the very end of the show. Go ahead. This is one of the 200 or so devices that I did. This has a very unusual transformer there in the center. Unlike coil type transformers, this is heavy sheets of copper, and it's special made in India for me. And okay, this is one of my plasma tube devices, which I specialize in. But you see the metal plate there, there's a copper plate and an aluminum plate looking at you, and there's a copper plate underneath there that you don't see, and these points here are where the contact of the different plates are. The aluminum plate is this side, copper plate is the bottom side, separated by plastic sheet. This device here has a milliwatt input on it, and it has 65,000 watt output, and it's at a frequency which your diode bridges work, and you can tap it directly. And again, the reason why this energy is because of the ambient background, which is everywhere, all places at all times, is part of the Earth's resonant background. And so you're not getting something for nothing. You're simply tapping into what's already there and using a catalyst in order to arrange that tapping sequence. Okay. There's some more views of the same thing. Closer up view. Okay, this was one of the first devices that I built, and the object of building the device was the fact that each one of those coils there, one of them is the output coil. The center one, see, this one here, hold on a moment. This one is the center one, and it's the output coil, and whatever energy you put into this thing shows up in however many other coils you might put around there. And these coils are independently separate from the other one. They're not electrically connected in any way. So it's magnetic flux which is controlling them. You can have thousands of these other coils, and each one of them will duplicate what's there from the other thing. So that tells you something about the fact that you can get from the same source of energy, the same amount of output, you can get thousands of copies of it. Because here we got getting 3 copies of the same thing, and if you notice real close here, there's little light emitting diodes on these, part of the tuning process here. So it's real easy to tune the thing so that the lights light up, and that tells you that that coil is active and producing the same energy that's coming from the other one, from the output. Okay, this is looking at a 35 kilowatt deal. You see this is a neon tube transformer here, and you see the heavy diodes here, and you see them coming together in the current source. So you've got the output here from the capacitors feeding the 2 output points. Okay. Here's another view of something we've seen before. This is a high voltage, high frequency testing device, one of them. Now this is a different device, which if you notice that it's a testing coil wound around a toroid. And the benefit of this is once you get the energy into the toroidal system and it's circulating, you can have however many, you can't see it very good, that there's a tap off of it. You can have as many taps off of that as you want, and each one of them duplicate what this tester coil is putting into the, here is a neon tube transformer running the testing coil, and here's the red thing is the L1 coil, and the L2 coil is the larger coil on the outside. So that was one of my inventions, is a testing coil that ran off of a large toroid. These toroids were from the Los Alamos laboratory. I had about altogether about 6 or 8 of them, I think, that I got as military surplus. But it's very special metal. It also has it's nickel with another mineral which I can't think of just now, but it has very interesting characteristics, which are tend towards the over unity type results. This is a close-up of the Japanese energy device for the Coke machine, if you want to see what it looks like. Okay, the input part is over here. This is a milliwatt high voltage Tesla coil type device, and it's like I say, milliwatts, and it's coming through this diode bridge, and it's coming out into a capacitor here that has a certain level of energy in it, and from that it goes into this system here, which you notice these are heat shields, and a very special type of diode here. And what this does, it makes the energy into pulsating DC, which in turn goes through this toroid here, which smooths it out and makes it into alternating current, which can run the Coke machine. And to the Coke machine, after that diode thing there, I mean the coil toroid, it's almost a perfect sine wave, which means that the Coke machine doesn't know the difference. It's still pulsating DC, but the Coke machine seems to think it's alternating current, and it runs on it just fine. So here we are with milliwatts in, and we got about 2 kilowatts out, actually, continuous. In case of capacitors and what they do in regard to energy, this is part of the secret as to how we can utilize the energy to our benefit. For example, a capacitor is a blocking device. Energy cannot pass from one side of the plate to the other side of the plate. But the second side of the plate, due to van der Waals and Kashmir forces, duplicates what's on the first side of the plate, even though there's no way for that energy to get past the plate. This duplication is due to the ambient energy background. And with that in mind, the second capacitor plate, which is not part of the system, as I'm going to be showing it very shortly. If you have a diode bridge, for example, and you have the energy coming out of the diode bridge, you put the charge onto one of the poles of the capacitor. The second pole will duplicate what's on that first capacitor without having any reason, obvious reason to do that. And that is the ambient energy which is available through the capacitor, second capacitor deal. And if you ground that properly, it becomes useful energy almost immediately. So we're going to actually demonstrate a case here so you can see it working with your own eyes. So it's not very complicated. It's much simpler than anyone would ever have imagined. And the energy which we're using is the ambient energy background which spins the Earth around. And the handout which I gave you is telling you basically what's going on there. And in nature, all things are simple and uncomplicated if you truly understand them. And the energy source is available to you in unlimited amounts. With the device as presented, the energy available would be equal to the amount of the energy put into it, whether it's a million volts or 5 volts. So basically you design the output device so that it runs at the rate which you want to see at the collector point. So if you're running a scooter or you're running an airplane or whatever you happen to be running, an electric motor or automobile motor or steam ship or any other type of energy device, the amount of energy you want is the amount equal to the energy on the plate, the first plate there. So with that in mind, we have a device here to demonstrate that, and if you will set it up, we'll let you actually see it with your own eyes. These are two capacitor plates, and bring the high voltage device over where you can touch it to the copper side there. And what we're going to do, we're going to put, this is a dielectric tester device which is used for certifying the electrical durability of films and other kinds of things. So we're going to use it for a purpose which it was never intended to be used for. I'm going to put 8,000 volts on one side of the plate, and you're going to see the same 8,000 volts show up on the other side without any input to it. And with that in mind, the grounding that you do from that second plate depends on how much energy you want into the device that you're going to be running. Okay, I'm going to put it on the edge there. Okay, is it turned on? Okay, we're going. It's turned on 8. Okay, and what I'm going to do is put 8,000 volts on this plate here. You see those sparks there? Okay, what we're going to do, we have a thing worked up with the earth ground only present on it, and the green wire is the earth ground, and what you should be seeing the sparks on the other side. Are you doing that? Yes. You see how loud those are and how warm they are? I'm about half an inch or maybe an inch here from
You're noticing the plate in the middle. There's no electrical connection. So the energy must be coming from the ambient background.
So there's no connection there between the energy on one side and the other side. So the second side has to be your ambient energy background, which is present everywhere at all times.
Are you putting alternating current 8,000 volts?
In this case, it's alternating current, but it turns into pulsating DC on the other side, which can easily be changed so that you can use it as alternating current. See how long those sparks are? How many volts is that? A quarter of an inch is about 10,000 volts. So this thing is up to 1 inch separation here. So between the two plates, we're developing from the ambient background about 40,000 volts. It's a little bit hard to deny it.
Now there's so much voltage that the spark gap is such that you can almost get it with the wire at the top.
it's set for only about 10,000 volts, so it's greater than what somebody sleeping around maybe.
Yeah, if you saw my finger jerk, it's because I moved my hand too much to one side, and so I got close enough that the spark gap got me. But otherwise, yeah, there you can see it occasionally spark.
If you were grounded, it would toast you like a marshmallow. The amount of energy available for useful purposes is equal to the degree of grounding.
You got alternating current going in one side and pulsating DC on the other.
Yes, pulsating DC.
We got to come closer. Yeah, there you go.
Why is it not alternating on the other side?
The ambient background energy is more related to the DC. Place there is the second phase is a forever source of energy. There's no energy expanded off this side.
Would it matter if you had copper on both sides?
No, it's just a slight electrical difference between aluminum and copper makes it more choice.
So if it was copper on both sides, it still works?
It will, sure.
Or aluminum on both sides?
Yes.
What's your dielectric? Looks like wet sand.
Is
polycarbonate?
It's polycarbonate.
That side is still taking some amps, some watts, right?
It's very nice to watch. It's nice to watch the years, and the output depending on the grounding you have will determine the amperage for the output.
Now how do I ground it if I'm doing it on an airplane?
Well, the airplane has air and earth grounding. In the case of air grounding, you have different degrees of air grounding. So that's
in device 9, you used an acrylic plastic sheet and a powdered metal shielding.
The powdered metals come in molding metal projects today. Most of the metal molds are made from powdered metal. And how they accomplish that, they have a cylinder which is under pressure and they heat it up, and when the pressure is a certain level, the particles all are dispersed like powder, and they cool it down in that state, so they end up with powdered metals in any quantity you want. And if you want to build a solid device, you take this powder, put it in a mold, and you center it. You bring it up to the point where the metal begins to, where it touches, begins to grab onto each other, and you have a solid device.
Oh, so
any shape.
Was this out of a spray can?
Out of a spray can?
Yeah, where did you get the powder? What is the name of the powder?
No, when you get the metal, it's already been made into powder. The companies, this large industry where they supply unlimited quantities of all kinds of metals, rare and unusual. And
what type of metal was that?
What kind was it? Well, just as they say, it's something that electricity doesn't, magnetic flux doesn't like.
That airplane capacitor at 400 farads, what voltage was that rated at?
What voltage was the capacitor rated at? 400 farads. It usually is 24 volts or something like that.
How did you reduce the output of the Tesla coil to be able to accommodate only 24 volts?
Well, actually, what we're seeing here is an extreme case of what happens when you do this. You can do it to all voltage levels. So a 24 volt output at, say, 200 amps or something is quite accessible, because the amps don't show up until you do the grounding thing. If it's a dead ground, you don't have anything left, If you ground it properly, you can bring the amount of amps and volts in that you want. You can custom make it.
In the plasma tube device, you said the copper and aluminum plates are in the frequency range of a diode bridge.
Well, the frequency range will be whatever the plasma tube itself is putting out, which is from, say, 20,000 volts. 20 to 40,000 volts, for example.
You mean hertz? You mean cycles?
The frequency will also be about 15 to 20,000 cycles
that's great.
per second.
Because your diodes are rated for about 25 kilohertz?
Well, they go into megahertz.
Power diodes.
But you don't have to, if you pick your battles so you can win them, you try to make the energy source at a level which is easily accessible to the off-the-shelf diodes.
Right. That the toroid is military surplus material. Is there a name for that?
The particular material?
Yeah, the nickel something alloy.
It's a nickel iron alloy.
Stainless steel.
And there's a name for it, but I can't think of it at the moment.
Okay, and the last question is on the Coke machine. You have a diode device that's on the output of the first set of capacitors. And could you specify a little bit more on what that is?
Say again, please.
Could you specify a little bit more of what that diode device on the output of the...
Well, any diode bridge type thing will set it up so that it'll work.
Oh, so it's pulsing DC and it goes into the toroid.
Yeah,
that smooths it out.
We're using a pulsing DC when it comes through the toroid there, and when it goes through the toroid, it smooths out the thing so that it comes out almost perfect sine wave, which is a very simplified version of an inverter. Inverters are hardly complex, but they don't have to be. They can be hardly simple. And that's what I've done. I've simplified the inverter so that it has very few pieces, and you can see the Coke machine is running beautifully, so it must work.
Thank you.
You're welcome.
The question is about the demonstration we had previously with the two plates. Do you need the electrical arc to have the thing work, or you can just put the high voltage on one side?
Well, actually what we were seeing here is totally unnecessary, because if you, any energy source which you can put on a capacitor plate, which is not going anywhere, when it hits that capacitor plate, that's the end of the transit for that energy. But the other side duplicates through the van der Waals and Kashmir effect the first side, and the second side is an open circuit, totally independent from the first side, and you can the degree of earth grounding you put on that second side depends on the amount of useful energy present. So you adjust that so that it matches your requirements.
Okay, and to have the circuit work, do they have to share the same ground from the input and the output, or they have to be totally separate?
They don't share. Now, you can have the amount of energy actually physically used is very tiny. It's in milliwatts or less. And you can put a feedback thing on there which will make up for the difference there, and it will basically go forever.
Yes.
Is that your question?
Yeah, well, I will experiment and I will find the answer just to make sure that they understand.
Well, I tell you, it's so simple as to be ridiculous, and it's not complicated, and that's my kind of advice. I like things that are simple and easy.
Okay, and you don't have to go at 10,000 volts to make the thing
no,
work on the first
you can work it on 10 volts or 5 volts or whatever.
Okay, thanks.
It depends on if you have a capacitor and handle you got a huge amount, or you have a small capacitor, it will work just the same. Okay, you're welcome.
So, the question to continue his discussion about the voltages necessary. You can buy these 1 farad capacitors for $4 or $5.
Accessible today.
Pardon?
They're quite accessible.
They're quite accessible for $5 or $6 or whatever they are. They're about that big. They're about that thick.
Yes.
1 farad,
Yes.
but they're low voltages.
1 farad is equal to a kilowatt.
So, but they only take 4, 5, 6 volts or whatever else. But you can
That's
use that.
okay, but you can use if your final output, terminal output is going to be 5 volts, 10 volts, or whatever, you adjust it accordingly.
Got it. Thank you.
You're welcome. So that's how, if you run a motor scooter, if you want to build a motor scooter that does this, just look at the capacitor that's already in that motor scooter and figure out how to wire it slightly different, and you've got a motor scooter that will run forever.
If you don't mind, Don, tell us a little bit more about the material that you put on the road. You say you use it in some of your machines. Some sort of material that creates
the one that knocks the magnetic flux out.
Yeah, they put it on the road to count the cars, and you use it in some of your machines.
Oh, you're talking about the
is the electric material? You know what I'm talking about.
Yes, I do.
It's like a rubber or plastic or something like that.
Yes, it's available off the shelf. It's commonly used for counting automobiles and things like that.
Okay. Okay. All right. Thank you.
You're welcome.
Don, on your very first device, your picture you showed us with the coil and the 3 coils around it, right? Those small coils would suggest a very high operating frequency.
Yes and no. You can run it at quite a number of frequencies. The frequency depends on how fast the thing is spinning, because it's got an off and on device there where the magnetic flux has been cut off and it's turned on, cut off, turned on. Each time the part of the whole passage there that is open, see, it blocks the magnetic flux normally. And there are holes that are cut in the thing, and when they pass the magnet, the magnetic flux comes back, and it causes an energy surge. So it's not like the Dennis Day I'm talking about is not the one that's here visiting today, but the devices that Dennis Lee did came indirectly from me, but he refused to use the system which I asked for, and the net result, those devices are killed by the heat factor. When they run, the magnets will last a very short period of time, and that's why you won't find it demonstrating in the devices over a long period of time.
A question about the frequency. The input frequency you said was very high in the example you gave us. Is that critical? Is that matter?
Okay, the natural frequency of magnets, they have just like everything else, every substance, it has a natural frequency which is built into the system, so to speak. So the magnets themselves can be very low frequency or very high frequency, but they're more inclined to be high frequency. And it's more likely to be out of the range. It's like your megahertz. If you see the energy spectrum from the electrical display that is available, I'll have to tell you about it on the internet. But all things, all substances, materials that are solid or otherwise, or human or whatever, everything has its own natural frequency. And most of the frequencies we're running into on magnet type stuff are actually in the gigahertz or something along that line. And if you know what those frequencies are, you can actually make an energy device direct without having any moving parts, and I've done that. And it was very successful. And say you have a 50 my mind's going sideways, on the amount of magnetic energy out of the magnetic flux energy.
Gauss?
It was into the hundreds of Gauss. Okay, thank you very much. And one Gauss is equal to 100,000 volts worth of electricity. So you can see the magnet with 100 Gauss in it. It represents a considerable amount of energy, and the magnet itself may be the size of a peanut. See? So if you can access that energy properly, correctly, you have the equivalent of that amount of energy accessible to you. And I've done it, and it works beautifully. And it doesn't deplete the magnet because the magnet works like a sponge. When you take the energy out, it immediately rebuild itself. So the energy is coming directly at you and can come out with unlimited amounts without depleting the magnet. Okay, we have a pancake device on the top there. This one, small pancake device, and it was one of about 4 dozen different devices that I've done. With the pancake device, you get an amplification of the energy such that you actually physically can generate through inductance and other things that there's an energy gain. And the energy gain is coming from the ambient background energy. It's not getting something for nothing. And we'll go into that in more detail later. Go ahead. Down below there. Okay. When I first started doing these things, I had one of Nikola Tesla books by Thomas Comfort Martin, and it's the official authorized biography of Tesla. And from that, there are a number of experiments which he shows in the book. So I went through every one of those experiments and in great detail. And that was my learning process for understanding what Tesla had done. And at the end of it, I realized that technology had advanced quite a bit, and a lot of new things which were available, which were not available at the time Tesla did his work. So all the things I've done are extensions off of Tesla. And they're beyond, in many cases, beyond where Tesla had arrived at when he had completed his work. Okay? Okay, I like to play with plasma tubes and that sort of thing. This is one of my early experiments where I took the ambient background energy using the test instruments that are used for plasma, and it worked beautifully. Okay, go ahead. Okay, this is something which I brought to the 1989 Tesla convention.
and it was my black box that I brought, and it caused quite an upset and quite an uproar. But basically, it's a very simple device, and it was working completely off of the ambient background energy, and it could have basically ran forever if anyone wanted to look into it. Okay. Okay, this is one of the other devices. This one generated about 35 kilowatts, and that seems impossible with a small device like that, but it actually did. Go ahead. Next, please. We're seeing some of the other views of that particular device up close, so we'll skip along until we get through that. Next, please. Okay, that is actually turned up from where you're looking is probably okay, but what we see here, if you can read the things, this is a 35 kilowatt system. Okay, this is where I put a Tesla coil onto the toroid there, and use the Tesla coil to generate additional energy which was not present there originally, because again, all this stuff that comes from the outside or the ambient background is added into what you have, so it appears to be that you're getting energy from nowhere, which is not correct at all. You do not get energy from nowhere. It has to all come from somewhere. This is one which is currently being manufactured in Russia successfully in large quantity, and it's one of the devices that appear to get quite a bit of attention. There's eight different power sources there, and they're not intermingled. So each one of those power sources will do about 50 watts. About 50 watts. 50 kilowatts. Okay, we can go ahead. Okay, this is something which I have a patent on, which relates to getting a huge amount of energy out when you put a few milliamps of energy in, and you end up with like 100 kilowatts of energy out. And that won't make sense to anyone who thinks like an electrical system. You have to think in terms you have to think in terms of the magnetic flux, because if you're using electrical flux, everything is dying a heat death, and you lose the energy almost immediately in electrical flux. But in magnetic flux, you can make as many copies of the original as you want without depleting the original at all. So if you're chasing electrical flux, you're chasing the wrong rabbit. You need to be chasing the magnetic resonance flux. Okay, this is a early stage of the 8-cylinder thing you saw just a moment ago, where it was demonstrated as to how simple it was and how well it worked. And this particular thing has been duplicated all over the world. And
okay, this invention relates to the dipole antenna system and their electromagnetic radiation. When used with a transformer, an appropriate energy collection system becomes a transformer generator. The invention collects and converts ambient energy, which with conventional devices is radiated and wasted. This is more of like the Morey flux valve or the Morey valve or the Tesla valve. It's in concert with that similar technology in that what it does is when tuned to the proper frequency, you can pick up the strong ambient resonant energy that's available in your area, and the frequencies vary from place to place. A system that's assembled at your house may not work 10 miles away as well. What you have to do is tune it to match the work in your area. There's a gentleman in New York that has a system that 4 blocks away, when he moved from one house to another, almost was unfunctional until he retuned it. But basically it's picking up ambient resonant energy, and some individuals would tend to call that, well, I'm depleting the ambient RF that's produced by my radio station, and I'm sucking a black hole of the RF in, which you can do. In fact, we've run tests where we've set up everything from a regular monopole to a dipole to a ground plane in Yagi, and with signal strength meters located just 1,000 yards away, we've figured out how to suck down a specific frequency so that we can convert it to usable electromotive force to charge batteries and run things, and we've watched the signal strength deplete just 1,000 yards away. But Tesla ran his 1931 Pierce Arrow. There were very few, if any, commercial radio stations in some of the areas where he drove that, and it drove just fine, which proves that there's still plenty of magnetic resonant energy out there to be had. The dipole basically uses that. Sometimes you need to excite. I'm going to pass through some of the, because I'm explaining it, sometimes you need to excite the ambient magnetic field. You can excite it or disturb it like water in the pond, and as the ripples pass through, say, a wave generator, you can, if you have a small wave generator there, as it just afloat on the surface of a pond, with a magnet in it, floating up and down over a coil, you can generate electricity just from some child jumping into the water. And all you need is a rectifier transformer circuit for each one of those that are in the water. You can disturb the magnetic field in different ways. If you can disturb the magnetic field in such a way that you're using little or no current or reduced wattage to do so, while disturbing the magnetic field, anytime you disturb it, you create a flux or a disturbance in the flux field. And when you disturb the flux field, 10,000 lines of flux over a conductor constitutes 1 volt amp or 1 watt. You have usable electromotive force. The dipole turns out to be one of the more efficient methods that Don's invented and worked with. Actually, he's invented applications that use a dipole that some of them he's not even shared with more than 2 or 3 people. Sometimes I've visited him and he's been thinking and explained inventions that haven't even been put to paper yet. But what you'll see here is that the dipole creates a disturbance. With a coil on the bottom, we create a disturbance in the magnetic field, and the plates are our inductors so that we take through the transformer rectifiers that make it usable. The dipole generator here, you can see the plates. The top plate is an inductor. The bottom plate's an inductor. The middle plate is an insulator, and there's your dipole circuit with your exciter coil. Much like the 8 coil device that he was explaining earlier, the disc in the middle, all it has is just voids with a material like bismuth, neodymium, or there's actually another material that even works better that are sprayed on something as simple as a plexiglass disc or a phonograph record. And in one of those, he actually one of the prototypes that he still has that's working. There's still a phonograph record in it. This is an assimilation of the plasma with the tube that all it's doing is disturbing the magnetic resonant field, and you have your inductor coils or inductor plates in this case that also qualify as a capacitor, plate capacitor, to 17, where your terminal block where you go to your transformer rectifier. There's many different applications. The one that is now on your screen, let me see if I can, I'm going to shrink that down a little bit here. We're going to reduce that so you can see it at this one, 21 and 20 there is a series of plates that are assembled. You'll see in a moment that on Don Smitha's website that he has a product gallery that he numbers many of them 1 through 9. And let's see, this one isn't on the website, I don't think, Don, but www.altenergy-pro.com, and a little bit we'll put it up. But this one right here is similar to the plasma tube, but there's number 1 is a dipole with north facing up, and I told myself I wasn't going to do this. I was thinking about getting out that funny green laser, but Don has a laser pointer there. Well, here, I'll just use the pointer on the mouse here. Okay, that's the North Pole. Down here is the South Pole. There's an exciter coil that all we're doing with this coil is using that dipole magnet. We're creating a disturbance. We're not producing a generation of electromotive force by sheer mechanical effort and magnets passing over induction coils. This is a different approach. It's creating a resonance that's allowing, in this particular case, 20 and 21 constitute a group of 11 plates with 20 insulators plates between them.
Okay, this device is one which, if you don't have any good working knowledge of resonant energy, that you would want to purchase. It costs about $50, and it's supplied through one of the services. You can get it through several science services, but basically what it amounts to is that you have a transmitter and a receiver. And of the transmitter and receiver, you can have, like in a radio station or television station, you can have hundreds of thousands of people tuning in, or thousands of people tuning in, and it doesn't deplete the system at all. So in magnetic resonance energy, the output and the receptor things is a multiplying method which works very well, and almost all of my devices depend on that system in order to get the extra energy which apparently was not there originally.
That was a letter from Don recommending recommendation for a submarine power system. It uses a very unique material called terphenol D, which also happens to be it's extremely expensive, but the most optimum material. That one device that you looked at earlier that had the 8 coils on it, it's probably as good a diamagnetic as you can obtain. In this, let's see here. In the picture before you, there's an example that the one device that he talked about earlier that well, I can't get a good display of it. I was trying to, but the disc in the middle if you use terphenol D and just make slots in the disc so that it interrupts the field between the magnetic coils, you deflate and inflate the magnetic field between them, and the field inflating and deflating constitutes a magnetic field, flux field passing over the conductors and produces the electromotive force. In this case here, the rod that you're looking at is made of terphenol D, which is extremely expensive. You can use the inductors in the ambient magnetic flux field that is not stagnant or stable on its own, induces a voltage and a current in these coils, and therefore provides usable electromotive force.
This thing you're looking at here is an offshoot from the military use of sonic methods for submarines. In that case, the energy goes out about 50 miles and can come back about 50 miles, and you can read what's going on with the instruments. In this particular case, we're using a rod, terphenol D, which is similar to what the military use would have been. And the terphenol D is very highly, it's titanium zirconate, in case you want to know exactly what it is. And it has very unusual electrical characteristics which you can use to your advantage in building these devices like I like to build. It's also a little bit expensive. When I originally started on this, those rods you're looking at there were about $3,000 each. So there's other types of material that you can use that will react somewhat similarly, and certain types of stainless steel will have some of those same characteristics. So you can pick and choose and get something which does not cost so much, maybe.
Okay, we apologize for this one being on its side, but this is actually the schematic that was inside the black box. And if you look up at the top right-hand corner at number 1, that's the lead that came out of it that was actually the ground lead. Much like the crystal radio set or the Tesla valve or the Moray valve, you had to have a ground lead. And in this case, it's not quite the same as the Moray valve or development, but what happened is it produces electricity the same way. It gets there by a different route. Two of the devices that we saw earlier, that we saw the wire induction coils, are basic forerunners of, or similar to this system. But the suitcase ran and ran and ran, and the suitcase is still somewhere today. I don't have permission to tell you where it's at, but it is somewhere today. Do you have any comment on that one, Don?
Well, there's several different devices represented here. Here's the alternator part of it here, and of course this is your bridge system here, and this is the input part back here. This is basically your L1 coil right here. This would be your electrical system of input into the L1, and this is a timing device. It adjusts the timing so that you're getting the frequency that you want on your L1. Okay, this is basically the L2 system here, and it's split up in two different parts.
for reasons of getting a better signal into the deal. This, of course, we mentioned was a diode bridge where you're taking the alternating current system here and changing it to DC so that you can reform the waveform here and through the electrical system here. And of course this is the output transformer here. And when you end up with this thing, you end up with a waveform that you can use in any system that's out there, including your computer or whatever else. Go ahead.
Okay. I'm going to go ahead and pass through the most of the text for you, Don. You can just explain it. Okay.
Okay. What we're seeing here is the right angle component of the different factors that are involved in an electrical system. The magnetic effect and gravitational seem to be related in some respect. The electrical thing is on its own. Okay. Okay, this is explaining the separation of the block wall in regards to the electrical component and the magnetic component. If you're going to go the electrical route, you lose the battle before you get there. If you go the magnetic resonance route, the world is your oyster. This is explaining how the different parts of the electrical of the Tesla coil is separated so that different parts of it perform different functions. The ideal Tesla coil is one that eliminates the magnetic part and dwells on the electrical end of the system. But that's a mistake. If you really want to get in business, you have to go to the resonant magnetic flux. Sorry. Go ahead. This is explaining how the amplification factor, which actually in fact is the Fibonacci series, showing how things increase with resonant energy. You have this same resonant energy showing up in the growth habits of seashells and all sorts of things. The energy is amplifying as the system multiplies, and the output is much greater than the original input. Okay. These are simply some mathematical notations in regards to the various things you run into in the electrical system and magnetic. Okay, these are some early experiments I did which show how simple this sort of device can be. There's several different versions of it. Okay, this is showing the electrical and magnetic interplay and how you go about achieving certain frequencies that you might be interested in incorporating into your device. Okay, these are some various devices that have lots of amperage, you run into the problem where people think you have lots of volts but no amps, that sort of thing. That's not necessarily true at all. If you know the right way to construct your Tesla coils, they'll have an amperage equal to, if not greater than, the voltage. This is case in point. And this is showing how the systems break down, and the power out of the plant here might be like 5,000 or 50,000 volts, and as it comes along, get into where it starts coming down the system, and you start transformers reducing the power, and when you finally get down to your house, it's maybe a couple of thousand volts in this general area.
Okay, let's see.
And this is all using electrical resonant systems. Anytime you have alternating current, you have a resonant system. And if you use the magnetic flux component of it, you've got the full force and effect of it. You can multiply it and do things with it that you cannot do with electrical flux. You're wasting your time if you're going the electrical flux route. It's not going to take you anywhere except to heat death, which is a normal system which you are taught in physics in the university. They don't bother to teach you about the resonant magnetic flux for obvious reasons.
This is one of the devices that's, there's a neodymium magnet. There one each in each of the PVC cores there that have a counterpart on the opposite side. The rotating disc inside this particular one happens to be a phonograph record with holes drilled in it so that the field is disrupted, much like the drawing earlier. And the small motor turns on 28 milliwatts at 12 volts. And just rotates the phonograph record so that it creates a disruptor or interrupter. Terphenol D is the most advantageous material, although bismuth or powdered neodymium will work, and spray adhesive on an old phonograph record and sprinkle it with the even the neodymium dust is enough to disrupt it, and you have the holes equally spaced. There's little or no load on the phonograph record while it rotates, disrupting the field.
Okay, we're going on into actual demonstration here of some of the things that relate to what you're interested in. And I'm going to also need someone to come and help me with the
Okay, I just had to get a microphone on so I could come over and give you a hand. Hold on here. I got to make sure mine's set the right height. Okay.
Okay, let me tell you what these devices are here. This is a Tesla coil with an output on it. This is a dielectric testing machine that we see here. And what we're basically going to do in electronic gadgets like capacitors and resistors and all this and that, they have their own characteristics. In this particular case here, a capacitor is a blocking device. I don't know whether you're fully aware of that or not, but when something goes into one side of a capacitor, it does not pass through that capacitor at all. What does pass through there is the reflection of it, which is from the ambient energy background caused by the Casimir and van der Waals forces. So what I'm going to do is put 8,000 volts on this plate here and let the fellow with the earth ground over there play with the other side. So with that in mind, let's see if I can turn it on here. Okay, I think they're on there right now. Okay, we've got 8,000 volts here, and you should be seeing sparking up there, very noticeable. Right toward the middle. And okay, when this is sparking, what's happening on the other side? Move it away from it as much as you can.
Yeah, just hold it close enough to keep it going all the time.
None of the energy from the side that I'm on is passing through the other side. The other side is reflecting the ambient background energy, which some people call 0-point energy or whatever. But you can see that 8,000 volts is putting up quite a fuss on the other side. And we have a sheet of plastic between the two plates here, so that none of the energy from the side that I'm on can go through the other side. And if you don't believe in ambient background energy, which some people call 0-point energy, but I consider that an albatross. Ambient background energy is a much better term.
Many of you are familiar with the fact that AC sine wave passes through capacitance plates like this, but what about a DC? DC voltage doesn't pass through the capacitor. In this case, what you're looking at, if we were using pulse DC, you can excite a field on the opposite side with very little, and just like Tesla did, put a load on the opposite side, and it doesn't make a difference which way the anode or cathode is. On this particular, you can set it up so that if you're putting a pulse DC signal into it, you can extract a pulse DC signal out and put a load between the ground and your anode or cathode, whichever you've chosen to use. Now, if you buy the regular, like Mallory or one of the other DC capacitors, those are very anode cathode specific. You have to be careful which one you use. But right now, using the Casimir effect, that's basically how all capacitors work. Is Casimir, he did some excellent work in defining. It wasn't that he was the first one, but he did some excellent work on defining what it is, and they call it the Casimir effect now. This is not a closed circuit to ground. The power source to run the exciter is actually coming from the little light-off pack in the back there. We are using earth ground through the grid house system here because they, at one building over, have a 1-inch diameter, 8-foot nice copper ground stake driven in, so that there's no way you can see that as developing a closed loop system. On DC, you can actually put a load. You can dike this white wire and put in a load. We've had a situation where we've had a 180 volt DC motor, 3 horsepower, with 26 milliamps exciting, spinning, no load, but it did spin at full 3450 RPM.
Okay, the commercial version of this is already being used to power electric airplanes and scooters and all sorts of things.
Okay, we're going to open up for questions. At this time, okay?
That's strictly hooked up to the battery?
The power source to run it is coming from the battery, yes, the light-up pack. So it's not coming from grid. There's no closed loop there. And that was done specifically to ensure and demonstrate that there was no closed loop. Okay, first question.
Yes.
Oh, is that mic on, or let me double check it. Let me make sure that. Okay, try it again.
Hello? Yeah, okay. Yeah, do you use Casimir cavities or maybe 50 nanometers wide to extract energy from the ambient energy that you speak of?
Well, the Kashmir and van der Waals forces are very much apparent in this particular type of device. Very little is known about them. There have been relatively few publications, and most of the people who have published add to the confusion rather than help.
If you had the second side plate twice as big as the first one, would you get twice as much reflected ambient energy into your secondary circuit?
In this type of system, as you noted earlier, I showed you a demonstration where there was a multiple, one transmitter with multiple receivers. Well, you can do this with resonant energy, and you can have as many receivers as you want, and they'll all have the same output as the original had, in addition to the original, and you won't deplete the original in any sense.
Okay, the second part is... They shut me off. Could one of these be purchased to power my home?
And these be purchased by someone today?
Right. Here in the United States.
The financial control over it is out of my hand, and I can have influenced the possible purchase, but the rights are in someone else's control at this time.